Room. All right, we will go ahead and really get started this time. Sorry about the false alarms there, but welcome everybody to the fourth workshop and challenge on the computer vision in the built environment. This is really focused on the design, construction, and operations of buildings, and there are a lot of people that were involved in the organization of the conference. We won't go through and talk about everybody in detail here, but Iro has been our main ringleader in this over the last several years and keeping us organized in getting this workshop together. And we appreciate all of you for being here and having this opportunity to kind of connect as a community here. So basically kind of some background and the motivation of where this workshop came into being is we've seen a lot of advances in computer vision, particularly 3D computer vision applications. And so this is an example of the PointNet, which is one of many algorithms now that can do point cloud classification and segmentation. And you can see just how much the citation rate goes up and just how popular these papers are. And so we're seeing a lot of growth in new techniques and new approaches to doing that. Likewise, in the AEC, architecture, engineering, and construction communities, we're seeing a lot of traction in 3D point clouds. And well, scanning has been around for quite a while, a few decades now. We're seeing more and more traction and adoption and integration into their workflows. And in particular, a lot of the AEC community revolves around the models that are generated from the point cloud data, but we're seeing more and more direct use of the point cloud data itself. And I think that lends itself very well to a lot of the exciting things happening in there. But that's one of the challenges we're currently faced with is, well, the AEC community is starting to see the value behind the point clouds and adopt them more and more in practice. A lot of the software is lagging to catch up in order for them to be able to use it. And they still need models in a lot of applications in order to run their different analysis. They need that topology and that connectivity between the points. Then the other challenge that I think both communities are faced with is that challenge of data explosion. How do you manage and work with the data? And how do you get that data out and shared within organizations? We've been conducting a lot of interviews with departments of transportations lately on their use of LiDAR, and that's a common theme. They haven't found a cloud services that works for really getting the data efficiently that they want. Some of them are still using hard drives to send data back and forth between people, and there's obviously a lot of inefficiencies and challenges associated with that. So there's a lot of opportunity there. We're also seeing a lot of explosion in terms of how data can be captured and used. And so these are some examples of Zillow using the Matterport system to basically create photogrammetric models of different structures with ease. Very popular with structural engineers. I know a lot that like using this for getting analysis and good data and geometry for buildings. And then we've seen the introduction of pocket LiDAR with Apple's iPhone technology, where you can pull out your phone and scan objects and create 3D models that for relative accuracy purposes are actually pretty good. We're doing a study for federal highways where we're seeing, a few millimeters, about 5 millimeters, and detecting, say, the radius of a culvert. Now, over a large area, these algorithms start to break down, and there starts to be drift and other things that, they're not at the point where they can replace our current scanners. But we're seeing a lot of developments with Apple's Room Plan in detecting objects and so on. And then they just announced the area mode for object capture to improve the capture of objects outside, such as trees and things that were a challenge with the previous model. We're going to hear more of that today with one of our keynote speakers. So why is this workshop put together? Well, really the goal is to bring these two communities together. So we're not operating in silos from one another, where there's a lot of exciting developments going on with the talent in computer vision. There's a lot of really exciting algorithms coming out that have a lot of potential. But at the same time, there's a lot of really great use cases in the AEC community that I think it's really helpful for the computer vision community to be aware of those, so that as they're developing the algorithms, they can have kind of that end product, so to speak, in mind of how would somebody actually use the results of my research. So that way it gets more traction. There's kind of more opportunities with it. So I think in the AEC community, there brings a lot of challenges in the scan to BIM, and especially the accuracy level that's needed and required with that. So I had a lot of very conversations with my friend Ron Singh in the early days of laser scanning, and everybody would come up and offer to sell laser scanning services. They had the best solution, and he'd go through and talk with them and say, well, that's great. I see that the data looks good. I see that these metrics are checking out, but are you willing to stand behind it to the point of the liability that if your information is wrong, you're going to be sued for a whole ton of money, or it could mean the death of somebody because something wasn't designed quite right in the highway. And at that point, they started to rethink, oh, that's a little more than we kind of bargained for at this point. The technology is catching up, and I think there's a lot of value and accuracy with it. And of course, our traditional methods, I think that's always one of the challenges. Everybody says, well, it's not quite as good as our traditional method at this one point. Well, we had a lot of errors in our traditional methods that we could just never detect because the data wasn't high enough resolution, right? So I think there's a lot of opportunities to educate people in the AEC community that, yes, this may not give you quite that same accuracy at this one particular point, but it gives you a whole better interpretation of the scene that overall gives you much more accurate and complete information that in the end is beneficial to you. So I think the AEC brings a lot of benefits in the data that they've collected and so on, which is some of the data that's been shared, and I'll talk about in a moment. The high societal impact in terms of energy efficiency, climate change, hazard resilience, and so on. There's a lot of great applications associated with those. And likewise, in the computer vision community, there's a lot of robust databases and training that can then be applied and leveraged into that. As well as appropriate methodologies and metrics for evaluating the outputs of these systems to really help the AEC community know how good are these products coming out and at what point are they going to be useful with that. So the image at the bottom is really let's bring these two communities together and do our happy dance, right? And really find ways that we can work together to really tackle some of the ground challenges facing society today. So in this workshop, we've got a great lineup of keynote speakers throughout the day. So we're going to have two of them in the morning, or sorry, 3 in the morning and 3 in the afternoon. And they're going to represent a lot of different entities. So as we put together kind of the list of keynote speakers, we wanted to have a mix of people working in the industry, as well as professors from different institutions and kind of different stages of career. So you get kind of a good cross section of people working across in the different areas of AEC and computer vision. So we'll introduce each one of these speakers before their presentation. So another new thing that we've added to this workshop from previous years is we've introduced short papers. And so we had a good response of 10 short papers that are included in with this that are going to be presenting to you as well. They're going to do some lightning presentations just before lunch, but we looked for a lot of kind of papers on a wide range of topics. Floor plan reconstruction, indoor layout synthesis, activity recognition, semantic segmentation, 3D reconstruction, a whole ton of different areas and change detection and so on. And so you'll see a lot of kind of innovative approaches that are coming in the kind of the current state of the art through those different approaches. One of the key highlights today in the workshop is going to be the Scan to BIM challenge. So this is our 4th year of introducing this. So basically we have a database that we've compiled and put together that people can test out their algorithms on and then kind of see their performance relative to other algorithms of people that submit it. This is our 4th year of doing it. Our first year, we made the mistake of not declaring that it should be automated. So we had a lot of really beautiful models that people turned in that were manually created. And we're sitting there saying, how on earth did they create these models? I didn't think the computer vision algorithms were there. And then sure enough, after a little bit of exploration, oh yeah, they used Revit or they used some other software and just manually created it. So we've made it clear in recent years that it needs to be an automated algorithm. And that's kind of the goal, is to test those out. But that being said, if you have a lot of manually created models, share them with us. We can add them to the database and kind of continue to expand it. And so I think there's a lot of opportunities in using that development project. And so this is just the folks that worked on the Scan to BIM challenge. There's a lot of challenges in working with the data, getting the data. Initially you always think, oh yeah, somebody says, I got this database, and they hand it over to you and you realize, oh wait, the CAD models are not in the same coordinate system as the point cloud data, and you have to reconcile a lot of things, right? So there's a lot of work that goes into correcting some of the challenges with the data. So the data from this fortunately came from Dr. Paul Platos. She's with the Oregon Department of Administrative Services, and they've been scanning all of their buildings for a lot of different applications for space management and utilization. They have a very detailed inventory of all the buildings for all the state-owned agencies. And so they were generous to share this information with us. This data has been scanned with the BLK 360 or the Focus 3D scanners, depending on the site. In the 2D section, they had 91 floors with the point clouds. So 91 floors of the different buildings. There's a lot of different complicated layouts and different types of structures, ranging from facilities to garages to office space and all sorts of different places. So we definitely want to kind of acknowledge their contribution. But one of the things that they wanted is the data to be anonymized, so you don't know which one it represents. So you don't know which building in particular for security purposes. So from those, we've been slowly building up a repository of 3D building information models. And so the information they provided was all 2D floor plans. And so from that, we needed to basically reconcile that with the point cloud in order to create these 3Ds. So we've had some students work on this, as well as we've hired an architecture firm to go through and build this up. as we can shave off a little bit of money here and there to kind of keep that going. So the goal is to kind of continue to build up this repository so that the data are available. Here's some examples of the 2D data that's provided. So, talking to some folks in industry, they're like, well, the 3D is great, but if I could just get a really nice floor plan out of it, that would get me 90% of the information that I need. And especially since there are a lot of responders, for example, that aren't really ready to ingest the 3D information. So while it may not seem as exciting to maybe some of you in computer vision, it's still a very practical and useful application. And there's still a lot of the world that's thinking and working in 2D. And so there's still a lot of value in those products. And so we spent a lot of time getting these corrected back into the same coordinate system and scaled so that they would match the point clouds. We noticed about 1 to 2 centimeter differences associated with those. And then we've converted them to JSON formats and so on so that you can ingest them instead of the DWG. So in the challenge, we have to have some way of making sure that we consistently rate the different algorithms and the different approaches. And so we kind of went with a holistic approach to this. We could all argue the whole day long, and we spent a lot of time arguing as a committee over what sort of metrics should we use. And we ultimately decided to use kind of a combination of point metrics, area metrics, and topological metrics in order to kind of come up with the final scores and assessments with those. So the 2D metrics have kind of stayed the same since the first challenge. We do what's called endpoint precision recall. And we basically look at the ground truth endpoints and compare those through Hungarian matching to the predicted endpoints. And we do this with 5 centimeter, 10 centimeter, and 20 centimeter thresholds. When we first started, I was telling Fusion that, hey, we wanted to look down at 1 centimeter, and he's like, we're not ready for that yet. So we kind of relaxed those thresholds yet. And, too, some of the source data, sometimes, even though it was quote unquote done by experts that do it all the time, you could notice some deviations sometimes where they were off a couple centimeters, right? So sometimes the ground truth data isn't quite that accurate too. So we had to relax that. We also looked at the intersection over union. So kind of that overlap between the different polygons represent the different rooms or the different columns and doors and those kind of features. What was that percent of the area overlap and use that as one of the metrics. And then we had some topological metrics, one looking at warping error, distortion in the shapes of the different objects, and then the Betti number error that basically looks at the connectivity between different objects to kind of look at that completeness. And so ultimately, the final ranking, we basically average those scores together. We could argue again all day long about the weighting, but this has tended to work really well. In all of these, we kind of go through and do an assessment to say, here, let's visually look at the model as well and make sure that we're comfortable that the numbers actually represent the quality with that. 3D metrics, it gets a little more challenging with 3D walls and especially dealing with corners and junctions. So we had a lot of different working groups to kind of converge on the set of 3D metrics. For walls, we use Autodesk Revit to kind of approach to look at the center line for the walls, and then we define a thickness around those for the representation to make the volume that we need for the comparison. So in the 3D, we look at endpoints. We can look at endpoints, lines, surfaces, volumes. Those are the things we looked at. Lines, there were a lot of difficulties in the junctions, so we're not looking at those. We're looking more at the endpoints and, kind of the overlap between it. So again, we're doing the same process as we did with the 2D for the endpoint matching, coming up with precision recall and F1 score. And then we're also looking at that overlap. So between the walls and the doors in 3D, looking at the overlap of those surface volumes and calculating that area of intersection between the two of them. So this is an example of one that did not work very well, right? There's very little intersection overlap. Ideally, those shapes would be the same. So again, we're doing visual checks on this as well. So we've done visual checks on the ground truth data to make sure we've kicked out some data sets that didn't work. And sometimes there's some that kind of slip past us on some of the floors, and those of you in the community have been helpful in kind of identifying some of those issues so we can kind of remove those. But we basically look at this, and one of the key challenges that we have is the AEC community works in very different file formats than the computer vision. Right? Computer vision loves JSON, right? The AEC community, there's not really a lot of software that can really read in those. So just really working with DXF, for example, is kind of the main format. So we spent a lot of time trying to make sure that those results are consistent between those two, because sometimes in that file conversion, something goes wrong. So excited to announce it's our challenge winner results, and they're going to have some time later today in the workshop to talk about what they've done in their different approaches. And so in the 3D challenge, basically we had the HQU iLab that kind of was the top score. So again, in the score, lower is better in determining the ranking there. And so they overall produced the best results across the board. And so they were the winners. And then second place was KUL FBK. And then third was DFKI RPTU. So you guys know who you are. And we're looking forward to seeing your presentations. But one of the exciting things is we've kind of been keeping the running total of those different scores and so on over the years. And we're seeing them creep up each year, which is a good indication that there's progress happening in the community as this challenge goes on. I think it's a good chance for people to test and improve their algorithms and build in some of the advances over the last year. So the good news is things are getting better. And the 2D challenge results, we didn't have a lot of submissions in that this year, but we gave out the first place award to Singuis CBIMS. And, again, across the board with the lack of competition there, nobody wanted to go up against them, I guess, this year. But again, we're seeing an improvement over the previous years in terms of that algorithm result. And so we'll be looking forward to later today to get to hear about what approaches they've used and how their algorithms are working. All right. So you're probably all getting bored of hearing me talk here. So I want to kind of give you the just kind of a general introduction and kind of just lay out what's going to happen for the rest of the day. So we're going to have a couple keynote speakers in the morning. So we'll start out with Derek Litchie, Francis Engelman, and then Catherine DeWolf. And then we'll have a coffee break around 11. And then after that, Ashvin Degan from Apple will come and give a presentation. And then we'll have an oral session. And so those are those short papers. So we have a lightning round of presentations for each of those. And then after that, we'll have a 90-minute poster session and lunch break. And so there's posters affiliated with this session that you'll get a chance to explore as you enjoy your lunch. And then the challenge winner presentations and awards will be given out after that. And then we have 2 more keynote speakers, Caitlin Mueller, Yuan Bo Zhanli. And then we'll have a chance for kind of panel discussion. Since each of the keynote speakers have about a half hour, there's not a lot of time for questions in their presentations in the morning, but we'll have that kind of formal panel discussion and really with the goal of understanding the 2 communities better between all the people there. And then we'll wrap up at around 5 o'clock and give you plenty of time to enjoy the fun city of Seattle. So with that, we're going to now turn the time over to our first keynote speaker, Dr. Derek Litchie, who's at the University of Calgary as a professor in geomatics there. Prior to that, he was at Curtin University, and he is one of the world's renowned experts in photogrammetry, remote sensing, and everything else. Figured I'd embarrass him a little bit. He's an expert, particularly in air theory and calibration of devices, amongst many other things. And so, to be honest, when I first kind of read his papers and so on, I was very intimidated by him because, he's somebody that's so detailed into all the uncertainty and error analysis that, I figured if I present in front of him, he's going to spot every flaw in my presentation that kind of goes forward. But the good news is he's one of the nicest people you'll ever meet. He's very brilliant and so on in his work that he does, but also very, very kind and nice and encouraging, especially of young faculty, and has been really a good role model for me throughout kind of my career here. So very excited to have Derek here as part of our workshop, and he's going to basically talk to us about the terror of the errors and different issues and uncertainty in point cloud modeling. So let's give Derek a warm welcome.
You were too kind, Mike.
All right, I'll relinquish the podium now.
That's okay. All right, okay. Oh, absolutely, sorry. All right, no, I was just thoroughly embarrassed after Mike's wonderful introduction. So, okay, thank you for the kind introduction and the invitation to speak here today. I'm very pleased to be able to do so, and I want to tell you about some of the work my group has been doing over the years in trying to better plan for large scanning jobs of the built environment. And so I'll start off with introducing what umbrella term for reality, describing what is reality capture, because I really see it as an umbrella term for simply imaging techniques that are used to create models of real scenes, indoor or outdoor, whatever objects, or even living beings in this some sort of scan to BIM workflow. And the example I'm showing here is one from a project I've been involved with led by a colleague of mine, Peter Dawson, who's an archaeology professor in Calgary. And the purpose of it is to document Indian residential schools in southern Alberta, which are very much a black spot in the history of our country, and for the purpose of aiding in storytelling. And so this is the Old Sun Community College on the Siksika Reserve in southern Alberta. And it's now a tertiary education institute, but it used to be a residential school. And so the purpose of this project was to document the existing basically geometry, the current state of the building. And so the scan to BIM process is taking that composite point cloud that you can see there produced from terrestrial scanning and UAV photogrammetry and producing a model that is then shown on the right and is 3D printed and used by elders for storytelling to inform the next generations about what took place in the Indian residential schools. So, yeah.
Do we share the screen?
Okay. Right.
Okay, now we can see.
Yep.
Now we're good.
Not good?
Can you get?
Great. Sorry, folks. Okay, and so that reality capture process may be done using a number of different technologies, point clouds, wide range of sensors on a wide range of platforms, of course, that might be static or kinematic. And here what I'll talk about will be confined to terrestrial laser scanners. So we define these as being tripod or kinematically mounted instruments that have 2 rotational degrees of freedom and use 3D range finding to build up a 3D image of the site within their field of view. Okay, and there are a number of examples of those. These are some of the older ones, but many embodiments of terrestrial scanners are available. So let me talk about a couple of reality captures examples that we've done in our group in recent years to motivate the discussion that I'll come up with later about the data quality. And both coincidentally were done by a very clever person who's now a professor in Karlsruhe in Germany, Reza Malik. So he was a PhD student, and his PhD work was focused on construction site progress monitoring. So he wanted to be able to go to a site at regular time points and scan it and determine whether or not the site is temporally and dimensionally conformal. So is it on time or is it behind schedule or whatever? And does it meet specifications? And so this particular example, top left, was a residence building built on our campus. And he would go there about once a week and collect as much scan data as he could to track the progress of the construction. And his real, I guess, scientific contributions were methods using robust statistics to identify all of the salient features on that site. So all of the planar and linear segments. So the planes would, of course, form the ceiling and floor slabs, the walls of the columns, the elevator shaft, and so forth. And the linear elements were the rebars. And so the second row there of colorful figures each color indicates the different surfaces that he's been able to find, and then he puts those together and comes up with the model, which is what we see on the top over time. The colors are just indicating whether or not something is behind schedule, ahead of schedule, or on schedule. And then you can do the dimensional analysis as well. And that dimensional aspect is what we see at the bottom. So the figure on the bottom left is a CAD model of a pipe and flange module. And that would be something installed at what's called a SAGD facility in northern Alberta. So I'm from Alberta and we produce energy and we produce pollution in the province, and this thing contributes to both. So the SAGD facility is steam assisted gravity drainage, and the purpose is to extract oil from the tar sands, from the bitumen. And this pipe and flange module will be assembled in Edmonton, so several hundred kilometers away, and then shipped to site. And what's critical is that the flanges that you can see circled in red there, they have to match the existing infrastructure. And if they don't, that means rework. It means cutting, welding, time delay, and loss of money. And so the company we worked with, they were, yeah, Mike, it was. There, remember. So company we were working with was interested in changing their workflow and the dimensional control of these assemblies in two ways. So one, they wanted to move from the traditional total station type of measurements, very accurate measurements, but very sparse. And then they moved into laser scanning, but then they needed a way of trying to automate the analysis, because now they had this flood of data like Mike was talking about. And this isn't even a large point cloud, but it's very complex, that center bottom figure. So the task was to, from our perspective, locate the approximate position of each of those flanges. Then first identify the cylinder. So that's the pink thing. Okay, so you're using robust statistical methods, and then find the front facade of the flange, which can be modeled on a plane, intersect that with the cylinder axis, you get 3D coordinates of the center of the flange. And so that whole set of coordinates can then be used in a congruency test to determine whether or not it's going to fit. So is it dimensionally compliant? Okay, and so for these processes, and really any other sort of reality capture, we can encapsulate, or we can consider the whole reality capture process from question to some sort of model to give us an answer as this sort of flow chart. It's simplified quite a bit, but I think it's sufficient for this discussion. And there are three distinct phases I've identified here. So there's data collection phase, where we have to collect the scanner data, and it might be from multiple locations. We may have the assistance of auxiliary sensors to do that. There's a registration process. So top right figure, that's just a scan in my lab from 3 different locations, and we need to unify those 3 scans into a common system, which may be one of those point clouds or maybe an external coordinate system. And there are many ways of doing that. We might use primitives like artificial targets, or features within the room like planes, or we might just go for ICP or direct georeferencing with auxiliary sensors. And then once we have that complete point cloud, then we can proceed to the modeling phase, and there are many options for that. I'll focus more on geometric form fitting here, but hopefully at the end of that, we're able to use that model and make some sort of decision about whether or not the site is dimensionally compliant, for example. Okay, what I think needs to be underpinning, and sometimes it is, sometimes it isn't, this whole process are quality measures or quality processes. So I've identified quality assurance and quality control. So the assurance aspects, these are things we do beforehand in the planning or the design stage, like modeling the sensor and calibrating the sensor and doing geometric network design or viewpoint planning, as it's sometimes called, modeling the atmosphere if necessary. Not so much for an indoor room, small environment, but outdoors, probably. Okay, and then the quality control are things we do after the fact. So at every stage, we might have metrics like what Mike was talking about, metrics about the point collection, metrics from the registration to tell us the quality with which it's been performed, and metrics from the modeling. So residuals telling us how much the data deviate from an idealized cylinder or plane, something like that. And so I think these are really important, but it's obviously tempting to say, well, why bother? We get lots of data. It looks good. And today I'll focus on this network design piece. And the reasons are, some of them are here. So why is it important? So on the left, what we see is it's a plan view of some data captured in downtown Calgary. And you can see the top left, there are large registration errors. To give you an idea of scale, those are decimeters, a couple of decimeters, the deviation between the red and the green point clouds. In the bottom, the registration is a little bit better. There still is a shift to the right in the yellow one, but these data are actually from a testing facility that we constructed in partnership with Novotel, and they wanted a facility that they could take a kinematic system in a urban canyon, drive it around and compare the point cloud data they collect with that kinematic system with ground truth. So we have a very dense terrestrial laser scanner data set of this urban canyon. And so they can make comparisons at various locations between the two point clouds, determine how much errors, how many errors, what the errors are. And they can tell a client, okay, with this IMU and this LiDAR, you can expect this sort of data quality. Okay. The top right one is another problem that we encounter with poor planning, I guess you could say, of missing data or holes. Now, this is another residence building. We scan residences at Calgary, it seems. This is scanned from the ground, and it's a 9-story building, so it's going to be very difficult to capture the entire building, especially up at the top at high elevation angles. But it's a nice example to show that without the proper planning, we miss the data up at the top. Okay. And down at the bottom, and this has been a big focus of my work over the years, is modeling the instrument and trying to account for systematic errors. So instruments are neither manufactured perfectly, nor do they stay in alignment, even if they are. And some of the errors that couldn't be quite prevalent are non-orthogonalities between the axes of the rotating parts. And they're often very difficult to see in the point cloud because the data, the point cloud data will look more or less continuous as you analyze it. And you really need controlled conditions to be able to determine whether or not errors exist, but they can, and they tend to get very bad as you go high elevation angle or high zenith angles. And really only under certain conditions, like this one here, we happen to have a discontinuity you can see quite clearly. It's about a centimeter at 1 meter, 1.5 meters or so. So imagine project that into 10 meters, it's an angular error, it's going to get larger. So this is the thing we're worried about. And this is why QA is important, to try and avoid these things in your point cloud. And there's another aspect to it as well. And I put this because this is some of the inspiration for work we did in the last few years. So this is these are some figures from a paper by a colleague in France, Jean-François Hulot. At the time, he was working for an energy authority in France, and his objective was to scan this big facility. You can see the little cartoon person in the bottom left there for scale. He had to produce a model of this enormous energy facility. On the right figure, you can see every single small dot. That is a scanner location, a viewpoint. And the big green dots are targets. So he had to use artificial targets. And his real concern was how to optimize the collection of data on this site in what he called kilostation networks. Now, this paper is a few years old now. So at that time, networks of thousands of stations were really a big deal in pushing the limits of software and hardware and so forth. And the complexity of the network you can see from all the connections, the geometric connections between targets and scan stations in the center. And so our interest after that was really, how can we optimize this? Because if you have thousands of stations, it's important to capture as much data as possible. You don't have to go back if you miss data, if you miss some scans, and can you remove some? Because even if you save 1% of the scanning, that's also 1% of the data processing, maybe. That can be a big time saving and cost saving. So this is some of the inspiration for what we did in what I would call viewpoint planning. And so viewpoint, well, that's what it's called. It's really geometric network design, but that's how it's known, viewpoint planning, where we want to determine the number and location of those viewpoints that will give us complete site coverage and meeting the quality measures that we've been tasked with, and possibly the path between them if you have a kinematic system, or maybe you just want to optimize how your workers move through the site. Many of the planning methods now assume there's a prior model. So we have some sort of CAD model to work as a basis, maybe 2D, that's the most common thing, I think. And it may also include the number and location of the targets. And the example at the bottom is an electrical substation. So the viewpoint planning there was me telling my graduate students where to place the instrument. There are 7 locations there, and it's a fairly easy one to do because it's a very sparse site. We had to produce a 3D model of the infrastructure on this substation. And it's, even though it's small, there were many intricacies because it's still a complex site in localized locations. So really, even for a site as simple as this, we want to meet the quality requirements and minimize the data, the time required to do the collection, the data processing. And so where we went with that is I had another clever PhD student, Fengman Jia, and she came up with a newer version of the greedy algorithm that had been used by several authors for designing networks for the viewpoint planning. So in this figure, we see a multi-use facility where we have determined through her methodology where the viewpoints should be. So this is the plan we can give to the field crew to go to the site and collect the scanner data. And the circles that you see there, they stem from one of the new contributions she had, which was to make it more of a multi-scale, multi-resolution design process. So greedy algorithm, basically you divide up the work volume or workspace into discrete locations for potential viewpoints. And then you examine each one and determine, well, which one is best, which one has the greatest coverage. And that's the greediest one. You add that to your network and then analyze the rest. And that discretization is usually done at a very fine interval. So her idea was start at a coarse interval and do an initial design and then refine it where necessary. And then she had a weighting scheme as well to place higher priority on viewpoints that can see difficult to intricate areas. So that's where we went with that. And that many authors have made contributions in this area. And if you look in the literature, you'll find that there is a hierarchy to the design process. So completeness is very important. The accuracy, although accuracy is what is desired, but it can only be estimated with precision at the design stage. There's resolution, which is all about information content and level of detail we can see, and then registrability, which is how do you measure the overlap and the geometric variety, I suppose you could say, to allow registration to happen. And if we come back to the accuracy piece, then the most common level of accuracy criterion used is single point position. So it's radiated position. So you imagine instrument here, scanning that wall. What is the point precision from that operation? And that is often even devolved to something much more simple, to range constraints used for the design. So we will specify that our viewpoint planning ranges to objects can only be within a certain range, minimum, maximum, and the incidence angle. And I'll explain that in a moment. All right. And my view is that this is really not a suitable LOA measure at the design stage, because really what we're doing the reality capture for in the first place is to be able to produce a 3D model. And that model may comprise geometric objects like planes, cylinders, tori, whatever makes up that site. And so to me, it's actually the positional precision of those modeled objects that is more relevant than the point precision, because eventually we get rid of the points. Okay. And so really what that needs is some sort of rigorous error propagation. We go variance covariance propagation. And that's what I'll talk about today, is the process we've come up with to try and quantify that to better inform our design of scanning networks. And really, we want this. So my lovely cartoon network here, my cartoon environment has a set of walls that are in blue, a couple of columns that are holding up the ceiling in this artificial environment. And our viewpoint planning has come up with a set of scanner stations, the red, and a few targets. So given this whole configuration, we want to know what is the positional precision that we could expect if we were to go out and scan this environment in that configuration. So the magenta lines indicate the confidence regions at some confidence level, maybe 95%. And so they tell us what is the positional precision of the line, and you can see it varies along the length. It gets worse at the endpoints where we have more angular uncertainty. And we have a confidence ellipse to tell us about the position of those circular columns. So that's what we want to know. Okay, but there are a lot of factors that affect those confidence regions. One is the observation precision. Range is a significant component. The actual effect of range precision, of range on range precision in small environments is very small. It's on the order of parts per million. So it's only on like mine sites where you would see it. But what you can see is that from that red triangle viewpoint, the positional precision as determined by radiation varies quite considerably as the distance increases. So at close range, the dominant error source, dominant uncertainty source is the distance. And then as you go farther away, the angular or transverse component becomes more significant. This is just simple error propagation. Many authors have found that the incidence angle at which we scan a surface, like this plane or in 2D a line, has a significant impact on the quality of the range measurements. And there are more complex models to describe it, but usually an incidence angle model is used where it's like related, the quality is related to the secant of the incidence angle to the normal. Okay, we have to orient an instrument in some external coordinate system, some reference frame. And usually the inherent uncertainty in that orientation process gets ignored. So on the left, we have a viewpoint that's been oriented from 3 targets, and then we've scanned, or it's designed, but we're hypothesizing the scanning of that column, and we get a certain confidence region associated with it, that long elongated ellipse. On the right now, we've taken into account the fact that, well, those targets had to be surveyed, they have inherent uncertainty in them, and the measurements to those targets have uncertainty. So we can come up with the confidence region for the viewpoint, the instrument location, and the column itself. Okay, and that's a larger confidence region. We have less certainty. Okay, the distribution of the observations along the object we want to measure has effect. So on the left, we have a wall shown in line form, scanned at normal incidence, and the observation distribution is more or less uniform. It's a little bulgy in the center because the data samples are closer together, but you can see it gives us a certain nice, that sort of, it's almost like a hyperbolic confidence region. If we scan it obliquely like on the right, we have a different distribution of the observations, we get a different confidence region. So this is another factor. And then, of course, multiple scans have a big influence. If we increase the number of scans that we plan for a particular feature like a column, we can make that confidence region as small as we like, okay? Which is good on the one hand, but there's an economic aspect to go with that as well. We don't want to spend so much money on our scanning. All right. So what is it that we do? We've come up with a procedure to try and put all these factors together. And the first thing we do is when we're doing our viewpoint planning, we take a viewpoint and we analyze the precision of the objects that are visible from that viewpoint in the local coordinate system of the instrument. And one way we could do that is through a simulation where if you see the little red dot in the center, we've done the ray casting to sample artificially the wall and the column, and then we can collect all those sample observations, build our covariance matrix, and determine what the precision of that wall is. That takes a lot of time, so we've actually got a closed form solution method to do that. The next piece then is to determine the viewpoint's position and orientation from the target field that we've designed in our greedy algorithm. And then what we do is we take the contributions from all of those viewpoints with those transformation parameters and their uncertainty, and we come up with the object precision. So on the right, we've got a little example of that. 3 viewpoints. We're planning for the scanning of a column there, and the colors, the blue, the green, and the black, indicate what parts of the feature are actually observed from each of those viewpoints, and then we have the confidence region. And so we can take the semi-major axis of that confidence region, compare it with our LOA criterion, and decide, is this design going to meet our needs? Okay, let me show you a couple of examples and I will finish up. So this is a slightly larger example, or sort of rendering of the example I showed earlier. It's the MacEwan Student Center. It's a multi-use facility on campus, lots of commercial space. And it's a very long building with many occluding columns. And so this is just to show you what we have come up with in terms of the design from the greedy algorithm. Lots of viewpoints, lots of targets necessary to get into all the intricate areas and prevent the occlusions. But the real goods are this. So here we're looking at the same environment, and the walls, the lines, and the columns, the circles are colored. Okay, they are colored green if their confidence regions that are shown in magenta match or meet the LOA criterion that we selected for this project. They are red if they do not. Okay, and now this is useful for us before we go in the field, because the greedy algorithm told us that this design is great. This is what we should go with. But we can see inherent weaknesses in the network where we have some of the columns that are shown in red. They don't meet the criteria. Now, can only be known if we superimpose the network of targets and viewpoints, because there are some geometrical weaknesses, but it'd be too cluttered. But it's a very useful thing to have for, I believe, before we go out and possibly get data that's substandard. Second example is our engineering complex, one floor of it, many long hallways. There's a restricted area that a teal or cyan color. It's like one of these social staircases like you see coming up the escalator here, where students go and don't do work, they do social things, you know. Anyway, so this is the design, and then this is our assessment of the object positional precision. And most of it is green, but some of it is red, and many of the line segments that don't pass the criteria are either in really elongated corridors, which are difficult to scan and difficult to survey through, or very short ones. There are a number of columns that are scanned with very poor geometry. And this one in the center here is interesting. This is actually, the viewpoint is very close to it, maybe about 2 meters away. So we get very good precision in the center, but towards the ends, where we have a high incidence angles, it's very weak. And so that's maybe something of a surprising outcome. But identifying this at the design stage is useful, because then we can fix it before going out. Okay, so I'll finish up now. So obviously, reality capture is important for constructing 3D models of the built environment. And my view anyway is that the QA and QC measures are still very relevant to ensure that the data quality specifications are met. And to that end, I think that object positional precision is a more relevant measure to use, but it requires a bit more computations. It requires a rigorous process to estimate, but we can find weaknesses in the network. However, what I've described here is really a post-design process where we do the greedy algorithm, then assess. And I'd really like to have the two integrated more wholly. So the precision we can expect informs the design rather than all in one step, rather than 2 steps. Okay, I have to acknowledge, of course, Eero for this very kind invitation to come here, Mike for the nice introduction, many former students and collaborators and funding sources. I'll leave you with a nice picture of scanning in the Canadian Arctic, and thank you for your time.
Yeah, we've got a couple minutes for questions, so can interrogate you, put you on the spot.
Yeah,
Any questions for the audience?
Yes, I'm assuming using LiDAR scanning to you account for multi-path.
Yeah, yes, that's the basis of our work is for LiDAR. Yeah, and multipath is this is a problem. This is a type of area outliers, and so it's something that you have to identify and then remove from the data. Yes, but this analysis here is more focused on the random errors, assuming that systematic effects have been modeled and outliers like you're talking about have been removed. Yeah. Back there, sure.
I'm curious how much of it and how it's see it have a column in public.
Yes.
And say for a wall. You have two pictures up that wall and just share the segments, that affects how your approach would
the approach, I think I understand what you're saying. The approach would be basically the same. You would just have many shorter segments, but certainly if like here we've assumed the wall is the full segment, but if you make it shorter, then yes, you're going to have many shorter segments, and you would have to analyze each one to determine whether it meets the criteria. And actually in the greedy algorithm, the wall segments, the walls are broken up into segments, but then for the precision analysis, we put them all together again. But certainly would have an effect, yes. Yeah. Yes.
So reality capture professionals can now buy a laser scanner, click, collect, and they ship this off to the customer. And that's kind of just the reality of the industry right now.
Yeah.
So what is the easiest way to compel them to follow best practice? Like, is there like an algorithmic solution where we just bake these practices into the software and, you know, they just go through a checklist, or is there something else?
That's what I think it would have to be. And maybe it would be something like you do a quick scan of the room and then up pops the quality map to tell you whether it's gonna be sufficient for you.
Kind of feedback.
Yeah, exactly. But it's gotta be real time right there for you. Yeah, we're not there yet.
Mobile scanners.
Sorry?
How do we take this next step to mobile scanners?
Well, I think the thing about the terrestrial scanner, we started with that because it's easy, because the platform is fixed and the uncertainty is much lower. And so to do the mobile scanner, the kinematic scanning, then you have to account for the error propagation in the determination of the trajectory and then how that goes into the propagates into the point cloud as well. So all those error envelopes suddenly get much larger. Yes. So haven't done it yet, but can certainly quite feasible to do. Yeah.
As a follow-on to that, so one of the methods for reducing the error was multiple perspectives.
Yeah.
And that seems to be an advantage that these mobile scanners have.
Yeah.
So how do you balance those two opposing forces in your mind? You know, it's less accurate because of the drift, but it's also more accurate because there are more perspectives.
Yeah. So there's two pieces there. Yeah. So having the multiple perspectives and loop closures and things like this allow you to identify the systematic errors that can accumulate over time. But also there is the effect of having more data. So the statistics of 1 over root n work in your favor. Yes. And so I think if you were to take what we've done here and extend it to the kinematic, then you could plan for that. How much do I actually have to, how much redundant data do I actually have to acquire to meet specifications? Yeah. Oh, yes, please.
And you didn't mention just the fact that buildings move as well.
Yeah.
And that's, does that factor in at all in your error analysis?
Well, this presumes that the building's not moving, but yeah, certainly.
I talked to one of the early laser guys that said he started scanning buildings
Mhm.
and they lean one way and then the other way as the day went on because of the sun.
Yeah.
And he said it was measured in many centimeters,
Yeah, I believe it.
maybe feet.
I believe it.
So like when you did the power plant, I
Mhm.
would imagine as things cool and heat, that there's pretty significant movement.
I would think so too. Yeah. And I don't know what he did for that. Yeah. Interesting.
The next one.
Yeah.
All right, let's thanks Derek for the excellent.
Thank you.
Awesome job.
Thanks, man. I have to stop
sharing here.
I am very excited to introduce our next speaker, Francis Engelman, who will discuss about foundational models for 3D scene understanding. Actually, Francis was one of the first to kind of join this workshop in the past 3 years as a challenge participator, and he won several of those challenges that you will see later today for CVS. And today we have him here as a presenter. It's from the first time I met Francis, he has been working a lot on 3D scene understanding with different projects. And I am very excited to have him tell us about his different works.
Thanks, Sarah. All right, let me quickly set it up.
Can you mute?
All right. Good. Can you hear me on Zoom?
Yes.
Perfect. All right. Let's start. Yeah. Thanks, Hiro, for the nice introduction. And today I'm going to talk to you about foundation models for 3D scene understanding. Mean by 3D scene understanding. So as you've seen earlier in the devices that allow us to very easily capture 3D scenes, the 3D spaces around us that we live in. Here, for example, you see a scan that I took with the Here, for example, you see a robot interacting in such an environment. And in order to make the robot do all, the robot needs to understand its environment. So it needs to understand all the objects in that scene. It needs to understand where. This is pretty much what we understand on the we want to predict the semantic classes. We want to know in a given scan where the rooms, where the doors, so that I can travel. Right. Should work again, right?
Yeah.
Good. Okay, so this is basically what we want to do. We want to be able to detect all the objects, detect the floor plan, and as well people in the 3D scenes. So let's start with a very simple task, a very fundamental task here, which is 3D semantic instance segmentation. On the left, you see, again, the 3D scan that we can just take with a mobile phone these days. And then on the right, you see the semantic instance segmentation. That means we want to split the 3D space that we have into the individual objects and predict for each object a mask. And we want also to predict the semantic class. So is it a table, is it a screen, and so on. So this is important so that the robot, and later on when the robot walks around or interacts with the scene, he needs to know where the individual objects are. How do we do that? In order to achieve that, we proposed pretty much last year a model that is based on the famous transformer model, and that since then has pretty much been widely adopted by the field. Who of you is familiar with the transformer model? I see. Yeah, okay. A lot of people, not everyone, but let me then quickly introduce how this actually works. So we start with a 3D point cloud, what we have seen in the previous talk. This is just, you can imagine, a very long list of points, including its 3D coordinates of each point. We can also have additional features such as the color of each point, or maybe even the normal information of each point. So this is our input. The next thing that we do is we apply a 3D convolutional neural network, where basically the only goal of this part is that we compute higher dimensional deep learned features from the point cloud. So what that does is for each of the input points, we now have a deep feature vector, a learned feature vector. The next step that we're going to do is we apply the transformer decoder. And as you might know, the transformer decoder, what it does, it produces sequence given a particular input sequence. And so here the input sequence is just a randomly initialized list of tokens, and the output sequence is a list of tokens again that if you want, it just represents, each token represents a feature vector, so a long list of numbers. What these numbers mean, we will see in a minute. What the tokens represent, these are the objects in the 3D scene. So each token in the tree that the transformer predicts us represents an object in the scene. Okay. And now, in order to actually recover the masks of all the objects in the 3D scene, we go to the features in the point, what you see here in blue. And how this model works is that it is trained in such a way that the features, we know a point belongs to a certain object if the features of the token are the same or at least very similar to the features to directly extract object masks from a point cloud. All right, so oh, I think we lost the microphone. Does it work? Nope, no. Does not work. Does not work. Do we have another microphone that we can use? Hello? Yeah, it works. All right. That is nice that I can now work. Yeah, so actually we set up a demo where you can try this. You can either scan the QR code or you simply Google for Mask 3D demo. But I will also quickly show it to you. Which is this one. It's oh, you don't have to hold it. Maybe. Right, so here we actually this is what I did yesterday night. I scanned the lobby in the hotel room. So this is what such a 3D scan looks like. Let me move the things around here a bit. So you can see you have the individual chairs that you see here. You have the tables around. So this is just a 3D scan as it comes out of the iPhone. And now we can here visualize the individual instances. So what you see now is each color here represents an object instance. And you can see how well these methods actually work. You can just pretty much scan an environment around you that it has never seen before, and then it predicts you all kinds of classes, windows, chairs, doors. It even obtains it can separate here the door from the door frame. So this is pretty much what these days this state-of-the-art semantic instance segmentation looks like in 3D. Let me quickly highlight another aspect that you see here. So you have here this ice bay in the corner, which is some statue that they put there. You might notice that this is not correctly recognized. We will talk about this in a minute. All right, to the keynote. On the previous slide, this transformer-based model, easily apply it to do other tasks. So here, for example, we used it to predict 2D floor plans, actually similar to what is done here in the challenge. Again, the transformer predicts as a sequence of tokens, and each token now, previously each token represented an object, but here we slightly reformulate now. We split up the sequence of tokens into multiple smaller chunks. And each smaller chunk actually represents, let me quickly switch again. So each smaller chunk actually represents a room in the scene, and then the individual tokens, they are the corners of the polygons that represent the individual rooms. And by predicting the tokens in a certain order, we can then recover pretty much the polygons of the room. And this is then what we get as input. We have a scan of an apartment. And the output of the algorithm is then directly the 2D floor plan, which is a set of polygons then. Additionally, we can also have semantics, so we can predict the type of the room, is it a bedroom, a living room, and so on. And we can also predict doors and windows in this setup. Here's another, just to show you how general this framework is. We can also use it to predict the semantic segmentation of people. So here you see a video sequence of a depth map recorded with a Kinect sensor, where we segment the individual people. So we detect the two persons in the scene and predict their body parts. So each color here represents a different body part, like the left and the right arm, head, and so on. All right. So I showed you this already just during the demo. As you remember, this is pretty much the lobby in the hotel. This works really well for objects that the model has seen during training. So all the models that I showed you now, they are trained in a fully supervised fashion. That means we have a training data set where all the objects that the model can predict, they have been seen during training. Now, of course, I highlighted to you this ice bear. So here you see a picture of this ice bear, what it actually looks like. This was wrongly predicted. Now, people that are familiar with deep learning and fully supervised trainings, they might not be too surprised. The model can only predict what it has seen during training. However, this can be a strong limitation, right? So this means that really our models only work in those environments that we
if possible.
Can you put the camera up nicely? Okay, I think I'm right. Okay, there. All right. We continue. I think it should work. It should work. Good. So, how can we achieve open vocabulary 3D scene understanding? What does open vocabulary mean? We don't want to be constrained to the closed set of object classes that we have seen during training. We really want to be able to detect anything during inference time. Right? During test time, there should be no limitation to us. A closed predefined set of classes. So one approach that is currently quite popular in the recent field of 3D scene understanding is by using large visual language models. So this is a special kind of foundation models that are trained on both images and natural language. Who in the audience is familiar with VLM? So who is not familiar with VLM? So who is not familiar with? Okay, now I'm confused. So who has sort of Clip or Zigbee? So who has sort of Clip or Zigbee? I see pretty much half the hands are going up. So I see pretty much half the hands are going up, so that's good. It's actually quite simple to understand. It's like this VLM, so visual language models, they consist of two parts, as the name already. So they have a text encoder and an image encoder. And what the name suggests is with the one input is text that can be, for example, a cat, and the other input is an image of a cat. And now these models are trained in a contrastive manner so that when the text describes the image, the features that each encoder produces, that they are very similar. So the features here that you see there, again, it's just a long list of numbers that we get either for the image or for the text. And when the text describes the image, these features are the same or very similar. Likewise, when the text does not describe the image, these features are different. That's basically all you need to know for those people that are not yet familiar with VLMs. So basically what that allows us to do is we can check if a particular class is visible in an image, right? So now, if you want to know, is this an image of a cat? We simply compute the features of both the text and also of the image, and then we compare these features. If these features are the same, we know, okay, this is the image of a cat, otherwise not. How can we make use of that for open vocabulary 3D scene understanding? So let's quickly look at how the setup works. So instead of having an image, we now have a 3D scene, and we then have our search query. So we now want to be able to search for a particular object in the 3D scene. For example, we want to search for a footrest, and the output should be all the object instances of a footrest in the scene. And this is really free-form text, so we can have very descriptive searches. We can search for a side table with a flower vase on it, and then it should output that particular table in the scene that actually holds or where a flower stands on top of it, and so on. Good. So this works a little bit different to the models that I showed you before. Before, we simply had one feed forward class, and then the model directly predicted all the object classes that it thinks are in that scene. Here, it actually consists of two phases. First, we need to compute a scene representation that allows us to perform this kind of queries. And then in the second stage, once we have computed the scene representation, we can then search the 3D scenes for arbitrary text. All right, so let's see how that works. We start with a sequence of RGBD images, which means so we have color images and we have the corresponding depth. And from that, we apply a standard 3D reconstruction method that gives us the 3D scene. So this is nothing new, this is just existing methods. And now what we want to obtain is, from this 3D reconstruction, we want to have a segmented scene. So each object in this scene should be segmented. And to each segment, we want to have this open set feature attached to it. Remember, this feature is what the VLM encoder produces us. Okay, so we want pretty much to each segment. Now we no longer want to have an explicit class label attached to it, but we want to have this open set feature attached to it. And then in the second stage, then during the inference, when we actually want to search the scene, what we then do is we take the query that we are looking for example, here chair, we put it to our text encoder that gives us the feature vector, and then we simply compare this feature vector with all the other feature vectors in the scene. If it's the same, we know, okay, we found now an instance of the chair. So let's see now how we actually get these the features attached to the 3D segments. We start with our 3D reconstruction. We apply a standard segmentation method. Actually, we are using here, in this particular work, we are using Master3D, which is the method that I showed you in the very beginning. And we ignore simply the predicted classes. So that gives us a class agnostic segmentation of the scene. Now, in the next step, we want to associate to each of these segments, we want to associate the VLM feature, so the open set feature vector. How we do that is simply by we iterate over all the 3D masks in the scene. And for example, here the chair. Then we check in which of the original input images, remember this reconstruction, it comes from a sequence of images. No. We have one more back.
Can you try again? Not that.
Hello, test. Oh, the other one?
This one's not on.
Hello? No. This one. Okay, this one. All right. Oh no, the Wi-Fi is gone. I think I will just continue and then.
Yeah.
So the next now, what we do is we project the 3D instance into the individual images that we obtain. And as I said, because the reconstruction is based on an image sequence, we have the original RGB images associated to each 3D mask. And then maybe you can already imagine it. Now, in order to obtain the open set features or the VLM features, we can simply put these images into the image encoder part of the visual language model. And that is exactly what we do on a high level. There are a few more technical details. For example, we first check which is the best image. So we have a small sanity check where we compute if the 3D segment is actually visible in the individual frame. So if an object is not visible in one particular frame, of course, then we would ignore that frame and we'd only look at the top K frames where the object is most visible. Then we do some additional tricks with SAM to get a more detailed outline of the mask, because the 3D reconstruction is not always perfectly aligned to the images due to several reasons, like poses that are not too well estimated and also the reconstruction that is not perfect. And then pretty much what we do is we average then over multiple viewpoints and also over multiple scales, and that feed it into the image encoder of the language model. And then yeah, so pretty much that gives us the clear feature for each mask in the 3D scene. All right, so let's so let's do also a quick demo here. Voilà. So here you see a 3D reconstruction. This is from the scanner data set. Maybe you're familiar with that one. And now basically what we can do is so here we have a text field and we can now search for, this is pretty much pre-formed text, right? So I can enter anything here and then it shows me the similarity to this query, right? So red means there's that part of the scene is very similar to my query. Blue means that part is dissimilar to my query. So here I was looking for window, and you can see that we get quite a nice highlight here in the two windows in the scene. We can search for, I don't know, let's say, for example, trash can. So this is really free-form text. I can enter here whatever I want. And sure enough, you see here in the corner, we have a trash can popping up. And similar here, we see another trash can actually in that particular corner. But we can play around with, so we have more scenes here, and now I could even ask you to just suggest me a certain query what I can look for. I don't know how much time I actually have left to. Okay, that's good. So I don't know if there's something that we can quickly look for it. Yeah, we have one. Let's go for shampoo. Actually, here you see it. So this is I hope you can recognize. So this is a bathroom, and you see actually the shower, and the shampoo bottle is actually a bit light up here in the corner of the shower. Let's quickly go back to the RGB. So it's a weird scene. It seems to be under construction. So there's also some kind of boxes in the shower, but also there are these shampoo bottles, and actually the model has found it.
You found it.
Let's go. Yeah, so that also. So I guess this is what you expected. Was that the output?
I don't know what I expected.
Usually people ask for something, you know, like toilet paper or something like that.
What shower door?
I'm sorry?
Shower door.
Shower door, let's try. Yeah, so, okay, it gets a little bit distracted here with the boxes in the background, but this is due to the fact, it's still like the location is somewhat correct. This is, I believe, due to the fact how we compute the features by projecting them into the images. Yeah.
What about rubber duck?
Rubber duck. So there's no rubber duck in the scene, as far as I know.
Let's see it fail.
Exactly. So let me quickly change. So here's now similarity raw. That means it's not normalized. So just for comparison, so this is normalized. That means there's always the highest similarities in dark red, what you see here. However, if I remove that, then we see we still have some kind of highlight there, but it's not as strong as before, which means there's some kind of correlation, but much less. And I think it's actually some kind of bottle, maybe made of plastic, so there could be some kind of correlation. All right. So we can play around with this a lot more. Yeah.
How does it work in industrial buildings? Because mostly they're trained for freezing.
So that's actually the nice thing. So the model that I'm showing you here, there's actually no training happening at all. So we don't train any model here. We basically just project the features from a pre-trained foundational model, CLIP in this particular case. So if CLIP has seen sufficient examples of machines in an industrial setting, it should also work. I just don't have a scan at the moment of something like that, but I'm optimistic that this should also work. Good, all right. So you can actually combine Wednesday. We will show this demo during the booth at Google Research, and then you can try it for yourself. You can also find the code online on the demo. All right, so now basically what we can do is we can search for arbitrary objects in a 3D scene, and that enables us now, for example, to give a task to, let's say, a household robot to perform certain tasks like looking for an object here. But what we have at the moment, is that really enough to perform such tasks? Currently, we can find arbitrary objects in the scene. For example, we could ask the robot, hey, search for a particular object, the rubber duck, for example, and with the methods that we have now, it would probably find it. The question really is now, when you have this robot here interacting with the scene, this is by far not enough. As you see here, the robot does not only need to find this piece of furniture, but it also needs to understand how to interact with it. It needs to know where are the knobs, how do I interact with the knob, do I grasp it, and then also in which direction do I open it. And now we could of course approach it from a roboticist perspective where we try to learn this with reinforcement learning. What I'm trying to advertise here is a slightly different perspective from that pretty much advertises that all this knowledge is already encoded somehow in foundational models. So humans know already when they see a knob, they know that this is something to grasp and this is something that I can pull on. So all this knowledge is probably also encoded in these foundational models. Here, for example, we see the robot pressing the light. There's a light button on the floor, so the robot knows, or ideally it should know, that this is something that I can press on, and then it will turn off the light. So that is currently the state of the art of research is that, so we can, currently we can detect objects in the scene, maybe even parts of that particular object. But what we actually want to do in order to be really able to interact with the scene is we want to predict, we want to be able to understand where in the scene can I do an operation. For example, the knobs here of the drawer, we want to know how can we interact with it so we can pull on it. And we also want to be able to understand what does that actually mean. So here, for example, to open the drawer, so all this knowledge is what we actually need, which is quite a bit beyond simply detecting the individual objects in the scene. And currently, in the field of at least 3D scene understanding, there's not really much that actually does that. So, and to pretty much to trigger the research also into that direction, this year at CVPR we released a new data set. And in this data set, what we actually did is we took an existing 3D data set from Apple, ARKit Scenes, and we labeled it with all these kind of functional and interactive elements. So it's not we have the individual masks of the interactive elements, and we also have for each element we have an interaction label. So how you can interact with it? Do you press it? Do you pull it? And so on. And we also have so that's pretty much the first class that we have here. Second, we also have natural language descriptions of tasks. So here, for example, if the task is open the oven door, we want to be able to detect the handle of the oven and also what kind of action to perform on that handle so that we can perform the task. And lastly, we also have motion annotations that pretty much tells us in which way do we have to move the arm to perform the action. And now this can either be for, as I showed the example, this can come from a robot, but you can also imagine that you're operating in some kind of virtual environment, wearing AR, VR glasses, then you want to be, when you're in your virtual world, you want to somehow replicate the functionality of the real world into your virtual world. So it's not only for robotics, but also for applications, for example, in AR, VR. So actually, this is a paper that is an oral presentation this year at CVPR. Here you can. So the presentation is actually on Thursday. We will also have the poster presentation there when we have a. If you have any questions for this and want to go more into detail, we are happy to answer everything there. And actually, this afternoon we also have a workshop on open vocabulary 3D scene understanding, where this data set was part of a challenge. Pretty much the first challenge that where people could then try to predict to solve this kind of tasks. All right. That pretty much brings me to the end. I want to thank all my collaborators that made these works possible. And yeah, I guess we're done. If there are any questions. Yeah.
It's a very nice talk. So two things come to mind playing with 3D scene understanding. One is that a lot of us assumes we have a pretty solid reconstruction to begin with. A lot of this, and then the second is that having a 3D reconstruction is kind of the final state. And you mentioned floor plans, and like there's a lot of applications where the actual 3D model is really just an intermediate representation before you extract some new layer of insight on top of that. And when you don't have a 3D reconstruction, all of this falls apart. So I guess my question is to you, where do you solve that? Is that at the post level? Like you showed an example with OpenMask 3D where you're doing this in 2D, that posts are going to impact, or thin structures that aren't reconstructed fall apart? Or is it something that foundation models themselves, Duster and Master aside, perhaps heavy memory and all that? How do you solve that? Or where do you see that?
So I don't think there's really a good solution for that yet. And so your first question was actually how it's based on having a good 3D reconstruction, everything I showed you here. So this is absolutely correct. If we don't have a good 3D reconstruction, we are limited in the sense of what we can actually do. What I showed you in the beginning, this is actually all based on 3D scans that I took with my phone. So if you're familiar with this kind of scans, they are pretty coarse, so they're not very detailed. It's not like a professional Faro 3D scanner that gives you a highly detailed point clouds. So I think you cannot get around of using images if you want to perform some more detailed tasks. Actually, in fact, the data set that I presented you now in the last couple of slides, we performed those annotations on scans from a professional laser scanner. So I think this was a Faro laser scanner. Because simply doing this on an iPhone reconstruction, it's not detailed enough to actually include those small knobs. So you're absolutely correct. You need to have more detailed scans pretty much to be able to detect such functionalities directly from 3D scans. So what we provide now to your second question, what we provide with this data set is pretty much a benchmark to evaluate the models. We are not saying you should start from the 3D scan. Rather, we provide all modalities that are available. This can also be only the images that come maybe with camera poses and so on. And then you can, it's pretty much up to you how you want to represent the 3D space, the 3D scene.
So what you'd want is a point cloud and then maybe a folder with 1,000 or a couple thousand images.
Yeah, so
with their pose.
Yeah, so I think that is really the question. How do we want to represent the scene, including the functionalities? Maybe storing all the individual, like as you say, a folder with a lot of images, maybe that is not really practical, especially in robotics applications where you need to have some kind of state or scene representation that you can easily update and also easily share with multiple agents in a scene. And or if you have some kind of low-cost wearable device, you also are somewhat limited in terms of memory and compute. So you need to come up with really an efficient and a compact representation of your scene that really holds those parts of the scene that are relevant for interaction.
But if you could store it, if you had a robot that could easily store 10,000 images, would it be able to, I mean, forgetting how much it takes to compute, is that the sort of thing that the software would like? If it had the resources to process it.
I think this is a question that is maybe a bit hard to answer. My typical answer to such question is, it depends on the application. It depends what you want to do in the end, right? If you want to, if you don't care about memory consumption and compute, then maybe always storing the images as well might be a good approach.
Yep, I want to thank you very much. We are using your works, in our framework. So we build a mobile app. We're funded by NSF and OpenAI Scan to 3D, it's called. And what I found in your work was it doesn't work well when you have blurry images. And most of the time you do have blurry images while you do the scanning because you're walking around. So what's your recommendation to overcome that obstacle?
So now you're talking about the OpenMass 3D
Yes,
method.
OpenMass 3D.
Yeah. So I mean, this is of course I would say a general shortcoming of the method. And yeah, particularly when you're scanning device, usually you move your phone like this.
Yeah.
And so my recommendation is usually move your phone slower.
You can't tell the users to do that.
Yeah, no, of course. I don't think I have a good answer for that. Like we did never really. I mean, typically in at least the academic setting that we're operating in, we are working with the data sets that are available. It is of course clear. CLIP is trained on internet scale images, right? There typically the images are not blurred. So maybe we have to think of training new or maybe fine tuning these foundation models to also be able to operate on such blurry images.
We'll take one last question that I saw at the back.
I'm clear on how and put the CLIP embeddings onto the segmentation masks. So where did the initial segmentation masks come from?
I am. So it's actually what we used in this work is the method that I showed in the very beginning. This is a segmentation model that is trained on ScanNet. So this is trained on pretty much it's trained to predict object masks. Does that answer your question? All right, but basically you can exchange this component. It's a component that you can exchange with any other 3D segmentation method.
Okay, I would like to thank again Francis.
Okay, and Ryan, by the way, Afshin Vegan afterwards from Apple that will come and talk us about Room Plan, he does mention the same issue with respect to how can you tell users to move on a specific way. It's a very interesting talk. Okay, as I set up, I'm going to start introducing our next speaker. She will join us online. It is, so it's Catherine de Wolf, and she's, oh, let me actually be able to share so you can actually see Catherine as well. As I introduce her, give me a second. Here we are, the full screen. Here we go. So Catherine is a professor at ETH Zurich. She is leading the chair. She's the chair of the Circular Engineering for Architecture group, where she's utilizing digital innovations, including computer vision, laser scanning, etc., in order to advance the built environment towards a circular economy. For those that don't know what's a circular economy, I'm sure Catherine would tell us a little bit about it. But beyond that, she has a dual background in architectural civil engineering. And I met Catherine when I was doing my postdoc at ETH Zurich, and I actually worked with her under her lab for a few of those months, and we're still continuing a collaboration. And it's been very exciting to work on such impactful problems. With that, I would like to have Catherine start presenting her work. And in the same time, before we clap for her to start presenting, I want us to all also wish her happy birthday because it's her birthday today. So let's clap for her birthday and for her presentation.
Thank you, Iro. Well, hi everyone. Thank you, Iro, very much for inviting me to give this talk.
1 second, we cannot hear you yet.
Oh,
Let's
okay.
see how we do.
Oh, right.
Okay, now.
Can you hear me now?
Yep.
Everybody good? Yes.
All right. Well, thanks so much for the birthday wishes. And thank you very much, Iro, for inviting me to give this talk on circular construction. I'm very happy to be there. I wish I could be there in person. I'll start sharing my slides and then you have to let me know if you see them full screen. Does this work full screen?
Yes.
All right. Okay. All right. So I'll talk a little bit about digital transformation for circular construction. I have a background in architecture and civil engineering, so it's really nice to come right after these two talks because they touched on certain topics on a more computer science level. And I'll talk a little bit more about from an application perspective of these technologies and how this can be applied for making the built environment more circular. Circular meaning that we close the loops of resources, and I am particularly specialized in the reuse of building materials. Now here on this title slide, you see a scan of a building that is on our campus, or that was on our campus, the ETH Zurich campus. These buildings
Catherine,
are...
sorry, we lost your screen sharing. We can only see you.
Oh, interesting. Let me do it again. Can you see my screen?
It's sharing. Yes, now we can see it.
All
Okay,
right.
great.
Okay. So on this title slide, you can see the scan of the Huber pavilions, which are a building on our campus that had to be demolished. And so before the demolition, my students and my team scanned the building so we could get information on these building materials so that we could reuse it. On this group picture, on the back of the picture, you see the structure that we built with the reclaimed materials. And I wanted to show this picture to also acknowledge all of my team members. Not everyone is in the picture. For example, back then when we were building the structure, Iro Armeni was actually co-instructing the class with me that built this structure with our students. So each team member in my group is specialized in a specific technology ranging from AI to digital fabrication or extended reality and so on. And we really need to connect all of these technologies so that we can upscale the reuse of building materials so that it doesn't stay like a niche project that we do to show that we're good in terms of environmental impact of buildings, but that we can make this more mainstream. And so I really believe that the creativity that we need for upscaling circular construction lies in the art of connecting these technologies, connecting the stakeholders, connecting the people with each other. Now, maybe you recognize this city. I don't know if anyone recognizes it already. This is Paris. Maybe some of you might recognize this building. It's the Centre Pompidou in Paris. And I was fortunate enough to work for the engineering company that did the renovation of this facade with these famous escalators and these hallways with this beautifully bent glass. Unfortunately, because of changing security norms, we needed to throw away this glass. So I went on a mission to find a new home for the glass. So we had to carefully disassemble all of the building materials, the glass, store them, remanufacture them, transport them, and price this all, make this work, find a new home in several places for this glass. And here you see one of the results. This is designed by Maximum Architecture in Paris as well, and it won the Eiffel Award for reuse architecture. So here it was used as partitioning walls because that was a way of reusing the materials without having to deal with this changing security norms. Now, why do I care so much about the reuse of building materials? Well, let me show you this example of a building. Maybe some of you recognize it. I believe you are in Seattle, right?
Yes,
so
yeah.
maybe, yes. So I don't know if anyone in the, I don't see the audience, so you would have to tell me, Iro, if anyone is recognizing this building, because this used to be in Seattle, but it's been gone for a while. So maybe on, the students might
Can
not
you raise your hands if you recognize this building? I see one hand in the audience.
Nice.
Out of, how many are we, 40, 30?
Okay. All right. Can the person who raised their hand say what building this is?
Can you tell us? The King?
Yes,
The
the
King Dome.
Kingdom. Yeah, exactly. It's the Kingdom in Seattle. It was built in the 70s. And it was a really big thing. It was the biggest concrete dome in the world back then. It was built, designed to last 1,000 years. Maybe you can also think of the Pantheon in Rome as another concrete dome that has been there for 2,000 years. So technically it's feasible to last for thousands of years when you build concrete domes. But this is what happened after only 26 years, so in the year 2000 to the dome. So this is to show that today we are demolishing our buildings without any regards to the building materials and all of the embodied energy that went into making these buildings and these building materials. And that is, of course, creating a lot of problems. So what's wrong with the way that we build today? Well, we extract a lot of raw materials. For example, we mine about 40 billion tons. Ah, nice. Now I see the audience. Thanks for doing that. So we extract about 40 billion tons of sand every year just because desert sand is too fine for construction. The building sector is responsible for about 40% of all of our greenhouse gas emissions, and 1/3 of that is coming from construction material production. And we're also responsible for a lot of waste. 1/3 of all of our waste comes from the construction and demolition sector. And so that's because we build in what we call a linear economy model. We extract, we produce, we use our building materials, and then we dispose of them. What we need is a shift towards a circular economy model, where we use our buildings as long as possible, and then we reuse our building materials when we cannot use them in the buildings anymore, like we did with the Centre Pompidou bent glass. I'm saying reuse and not recycling because a lot of people think about recycling, which means that you bring the material back to the raw materials, for example, melting steel, which still uses a lot of energy, which often means that you're downcycling materials. So we are really working on the reuse of building materials so that we can reuse the material as it is, like the bent glass, for example, stays bent in this new project. And so it's all about finding the right match between a material that is available because a building is being demolished or renovated and a building that can design with these specific materials. Now, it's not only important for environmental reasons, but also for social, ethical reasons. When we look at the construction firms in the world, 75% of them have no payroll, which makes it a sector that is extremely prone to forced labor and child labor. When you reuse building materials, usually you reuse local materials because you're disassembling in a city and reusing that in the same city. You can track and trace your building materials much more easily. And so you are more aware of whether they were ethically repurposed, remanufactured, and so on. However, only 1% of building materials are being reused when we do the effort of dismantling a building carefully. So we need a better way of doing this matchmaking. Now, I saw that Martin Bucher is also in the audience, and he was working also in our lab together with us before he joined as a PhD in Stanford on creating a Tinder for reuse together with Pascal Emmenegger. And the idea of matchmaking started also of finding reused materials more easily. Now here I wanted to show images from Zen Robotics. This is a recycling facility, so they don't do reuse, they do recycling, but they look at construction waste and use AI to detect which materials are which, and the robots are then putting the materials in the right bins. So for example, putting all of the wood in the wooden bin, and then they can make wood chips out of it. So this is to help recycle. However, I think it's a shame that we only do this at the recycling stage, which when the materials have already become waste. And so what we're trying to do is to do this detection and this identification and this sorting of materials before they even get disassembled, before they even become waste. So I started during my postdoc at EPFL working on the city of Geneva, where we connected really with the past. We looked at archives together with Corentin Fivet, Thibaut Mini, André Stéphan, and Serena van Boetzele. We looked at the archives of Geneva from 1850 till today. and made a map of how the buildings were built and the embodied carbon legacy throughout the time in Geneva. And so from all of these patterns from the past, we can learn when buildings are being demolished, reconstructed, constructed, and so on. Now we're also looking at connecting with the future, and this is the city of Zurich, where we are based. And this is work from Deepika Raghu, who is also in the audience, I saw, who is a PhD student in our lab at ETH Zurich, and also worked with Eero Armeni in Stanford. Here we are looking at data from the city of Zurich and trying to predict also patterns of reuse for the future based on this data. So we have data from the city, GIS data on when buildings have been constructed, for example. We have data on what type of building is it? Is it residential? Are there apartments? How many floors are there? What is the building volume? And so on. So that gives us already quite a lot of information on the building stock in the city. And then we supplement this with image-based data. So we have historical photographs or social media images, Google Street View images. And then Deepika and her PhD really developed algorithms to understand how we can make a resource cadastre for circular economy. Using material detection with Google Street View image. So here you see a Google Street View image of a house in Zurich, and you can say, for example, this is a brick building, this is the number of windows, this is the area of each material in this facade that we can find. And then once we have identified buildings set for demolition or renovation, we can zoom into the building and use reality capture technologies for getting more details and more accurate information. So this is what we did with the Huber pavilions that I mentioned in my first slide at ETH Zurich, where the students did a LiDAR scan of this building. And here is another building on the EMPA campus, which is also part of an institution that I do research at, where the DFAP house was also scanned here by Matt Corden, one of our researchers, with a LiDAR scanner. This is a tripod LiDAR scanner that is quite expensive, but also gives more accurate information. So I think here is the results of this LiDAR scanning. I also wanted to test out more affordable technologies. So in a lot of more recent smartphones, they also say that they have LiDAR capabilities. So I was testing this out with my phone in this building that we disassembled with my team. But obviously the results are a bit less accurate. So we developed technologies to turn these point clouds into accurate BIM models, detecting where the columns are, where the beams are, and so on. So this can be found in Matt's paper in Automation in Construction. And then based on photographs that we have of the site, we can also detect which materials are steel, concrete, masonry, and so on, using computer vision. Now, this is a building called Maison du Peuple in Brussels, my hometown, designed by Victor Horta, who is a very famous Art Nouveau architect. And this building was disassembled in 1965. And then this beautiful structure that you see here was stored for about 35 years before they reused it in the Hortazaal in Antwerp. So this shows that when we actually care about the structures, when it's a beautiful structure, when people value it, when you give it an identity, then people actually store it for a long time before they find a new home. We LiDAR scanned it with the help of the University of Ghent and also did the whole process to also test it on less conventional structures. All right, so back to the Huber pavilions that we then disassembled for our course together with Eberhard. So they had these beautiful trusses here, and then all of the materials that we could reuse were then inventorized, like you see here. Now, for example, the windows, we weren't going to reuse that on our campus for the new structure, but there's a lot of demand for windows, especially, for example, from disaster zones or war zones where windows get shattered. And so one of my team members, Anna Boozer, started this initiative called Rewind that sends windows to war zones for reuse, because we throw a lot of windows away in Switzerland just because of demolition, because of changing performance norms, but the windows are still in perfect condition. Then the rest of the materials were also distributed among different stakeholders. So we really did this connecting with stakeholder work. This was the work of Elias Knecht in my team. And we did work with Brandon Byers also on the tracking and tracing of these materials, using different technologies to scan the information on this material. So here you see one of my students scanning or engraving a QR code, I should say, so that we can scan this. So this is to connect the material really with the information. It's not new. We did this already with brick stamps for centuries. You see here a Babylonian brick, a brick of the wall of Nanjing, UK bricks, that have the stamps of which manufacturer made the brick, which is good to know when you need to ask them for renewals, for example. Today we have more modern technologies that we can scan and that we can read a digital product passport from, so a passport that gives material information, dimensions, specifications, conditions, and so on. Now we built this structure with the remaining materials that weren't distributed to real buildings with the students. We even got the Swiss Architecture Award for it, but of course the other materials were used in other buildings in different parts of Switzerland. Now for connecting the materials that have been disassembled, we also use digital technologies. Here is an exploration of using extended reality for assembly and disassembly of these reused materials. Here is CNC milling for the making of the connections that are adapted to the exact shape that we needed for this dome that you saw in the previous image. This is Deepika actually conducting the CNC milling. We also conducted research on steel assemblies. This is the work of Ines Ariza in my team that worked together with Gramatio Kohler and the structures group here at ETH, where we looked at scanning reclaimed timber components, understanding where the weaknesses are and which parts need to be strengthened and how we can best connect them using a minimum amount of material with this robotic additive joining technique. Then Zane Carson is also one of my PhD students who is working on working with reclaimed steel and robotic techniques. And the idea is also to scan the reclaimed elements, understand which parts need to be strengthened, need to be cut, need to be reshaped, reprocessed, and then using also robotic tools to adapt these elements. So here is a video that shows this setup. You see a simple metal part with one weld on it. And this robot then scans and collects a point cloud. And then the point cloud is clustered and the object of interest is identified. The robot then repositions with an object detection algorithm running simultaneously to detect the welds. And then the weld is detected and another point cloud then is captured, which lines up very well with the previous point cloud. And then the weld is cut using a plasma torch. So this is to show the connection between these different digital technologies that we are exploring in the lab for repurposing, reshaping, and designing with reused, reclaimed building materials. So the ultimate aim is really to connect people with each other, connect people that have materials available for reuse because they're demolishing a building, because they're renovating a building, with people who want to design with these reused materials, but also with people who can actually disassemble these materials, people who can store these materials, people who can repurpose these materials, who have the tools to repurpose this, people who have the tracking devices, and so on. So it's really about connecting. The creativity is really the art of connecting. This is really essential for upscaling circular construction. and especially using all of these emerging digital technologies that we are exploring in the lab that are constantly evolving and improving so that we can make reuse something normal, something conventional, rather than throwing away building materials like we saw with the Kingdom in Seattle. Now, I mentioned some of the work that we did with Eero. We wrote a chapter with Eero and Deepika in the book that I recently published, A Circular Built Environment in the Digital Age. You can scan the QR code if you want to access the book. It's open access, so you can access it for free. And all of the other digital technologies that I mentioned throughout the talk are also described in the book. So you have a chapter per digital technology, so feel free to connect also using the social media handles or the email that I'm showing here on the last slides. Thank you very much for listening.
Thank you very much, Catherine. Are there any questions from the audience or from online, which I will have to check somehow? Yes.
What's the state of the art for sensors and material recognition? Like a laser scanner can only go so far because of the data it collects. But what else is available in terms of collecting data for material recognition?
Well,
did you get it?
Yeah, so what I understood from the question was that what is the state of the art of material recognition in the built environment? Did you mean in the built environment or?
Can you...
Specifically the sensors that are available.
Yeah.
With respect to the sensors that are available. Yeah.
Yes. Well, I mean, so the construction sector in general is quite behind compared to other sectors, I would say. It's very slow to adapt. So we have these talks about, for example, digital twins, which are a virtual replica of the physical building, and then information exchange between the virtual 3D model with the information and then the physical building, but often it's just basically a 3D model and this information exchange doesn't happen. So we have to constantly go and check. And so when a building gets demolished, we often have zero information about it. So there is still a lot of work to be done to kind of update what we know from a building, from the building materials, the sensors. This is not something that is being done very often. It's still very much at the research stage. It's not really put into practice very much. So that's why we're supplementing with all of the other kind of data that we have, the GIS data that I mentioned, the Google Street View images, and so on. And then also the scanning when we need more accurate data, more precise, and then we want to test. But then this is an investment, of course, to go and scan the building. So right now in practice, it's still more, still easier to just have an expert go around the building and writing down somewhat manually what materials are in a building. Because we are not yet at a stage where all of the scanning technologies and the detection of the materials and the inventorying of the materials are automated enough so that we can just trust it and do it in a cheaper way, I would say. So that's why we're developing all of these technologies also to make it more accurate and have more data also on the built environment that we can compare it to, that we can understand what we see in the images. There's also a lot of things that we don't see because they're behind, there's different layers of materials. That's why where we also did the archival work to understand what is a typical structure behind a wall, so that we can make predictions based on what we see about what is behind the things. So it's still quite a big field to be developed and to be explored. And we are hoping that the digital technologies that we develop can contribute to making the process a bit easier so that it's at some point so easy that we just have the information available.
Yes.
You introduced the concept of reusing instead of recycling. How do you measure and consider material fatigue? Or the component have some lifetime? And it can lead to some liability if something goes wrong with the used components. How do you measure, considering?
I'm not sure if I heard it correctly, but I think that your question was about liability and how we deal with the fact that you are having reused components and that we want to know how the liability works of working with these materials, right?
Especially because of the material fatigue.
Yes, yeah. Okay, yeah, this is a very good question. Right now, a lot of the reuse that is happening is often non-structural, like the glass from the Centre Pompidou, for example, was used as a partitioning wall. The windows are part of the facade. When we are dealing with structural materials, it's actually very difficult to find engineers who want to certify these building materials. So, for example, the structure that we built on the campus needed specific engineers who are experienced in designing with reused timber that can sign off the structure. These techniques are actually not new in the sense that we already have this kind of competences for assessing historical buildings to see if a structure is still safe. So I would say scientifically it's not new to assess it, but it's more a legal issue because right now when you build with new materials, there comes a warranty from the manufacturer, of course, that says exactly what the specifications are and what the material has been through. This is lacking for reused materials. So often we take bigger safety factors. We built in some other types of safety into the new structure. This is also what the material passports would be good for, to track and trace exactly what materials are in the components, what they have been through, what they were used for, and so on, so we can make an estimation of these things like fatigue. So it's a very good question. There is not a straightforward legal answer to it yet. But there is new stakeholders and in the connections of the different people that I want to match with each other using the matchmaking is also the legal experts who give new warranties to the reused materials.
Great, thank you, Catherine. Any last questions? Good. Catherine, thank you so much again for joining us.
Thank you so much for having me.
Yeah. One more round of applause.
Thank you very much. Thank you also for the questions.
Yes. I hope you all got inspired on different problems that we can implement computer vision at and have an impact on sustainability and the world. As now we go forward with the program, we are going to have a very short bathroom break. In 10 minutes, we will be back with Afshin Degan from Apple to present his work with respect to room plan and beyond. Then we will have the oral session for the papers that were submitted to the workshop. With that, 10 minutes break. See you here at 11:15.
Hello, test, 1, 2, 3. Can you hear me? No? Okay, great. Should I turn the camera on?
Are you trying to make?
Hello, everyone. Can I get your attention to sit down? Okay, once again, I'm very excited to present our next keynote speaker, Afshin Degan. Hello. He's a senior researcher and manager at Apple, who works on computer vision, and he leads a very diverse team of different of expertise with respect to be able to understand semantics and create the environment. And he's worked on a lot of Apple products that relate to the to the LiDAR sensor that's on there and how we can use it to generate these environments, and on many, many more things that he will discuss. I just want to say one thing, that I met Afshin when he was still wrapping up, or you were still doing your PhD.
Many years ago.
Many years
Yes,
ago.
yes.
And since then, he has had an amazing track of contributing to this field. And I am very excited to have him here today to discuss a little bit more about what Apple does, which also is, I think it's a great fit that, you can share this knowledge.
Absolutely. Very happy to be here. Thank you so much, Yiro, for the intro. And I'm super happy to be here sharing some of the work that we've been doing over the past maybe 5 years at Apple. I'm going to talk about 3D scene understanding at Apple. And I'm going to also talk about a little bit about the future work that we are doing in my team and what are the things that we are excited about, especially in this new area of large models. And I have some content also around Vision Pro, because recently we just had an update in WWDC 24. Okay. Before I dive into Room Plan, we know that there's many different ways that we can represent 3D scenes, right? One of the ways that we can do it is using point clouds, as you can see here. And one can attach semantic labels to the point clouds and make the semantic point clouds. Meshes could be another way of describing a scene, or semantic meshes. Even though they're very useful, especially for content placement, physics simulation, and also for occlusion, they're pretty large in size and they're very difficult to edit. On the other hand, we have parametric representation, that you can represent the same scene using a bunch of planes and boxes, which is very, very compact in size, and it's also very easy to edit. That was kind of the motivation behind building Room Plan, because we wanted something that is extremely lightweight. And also we thought that for a lot of applications, we don't need to build very complex representation using meshes. So that was where we started thinking about building Room Plan, and also some of the foundation of 3D scene understanding work at Apple. This was back in 2019. And of course, another motivation for us was leveraging the sensors that we had on our devices. We have the LiDAR sensor that was introduced with iPhone 12 Pro lines that enables our users and developers to experience their 3D world in a completely different way. And we were pretty excited about it. And a little bit of background about LiDAR: it's a time of flight sensor. So it emits beams from the sensor, and the time that it takes for them to hit the objects and come back, it allows us to measure how far the objects are from the camera. So let's have a look at the overall pipeline of how Room Plan works. And I want to talk a little bit about things that you see in this video. So the experience starts by scanning a wall in front of you. We capture the height of the wall, and you have this nice interactive UI that starts showing you what the sensor is sensing. So the purpose that we have with this UI was that we not only wanted to show the progress that the user is making during the scan, but we also wanted to guide the user to what to scan next. So we had many iterations with our design team on figuring out what is the right UI to have inside RoomPlan. And then you can see that we sense, let me actually go back a little bit. So we are sensing walls, doors and openings, major room defining furniture in the house, and also doors and windows. And you can see that the progress of the scan is shown in a PIP view underneath. And once the user is happy with what they have scanned, they can finish the scan through a series of post-processing to show this final dollhouse that can later be exported in and used in a variety of apps. And one of the sample example is Cinema 4D app, where you can export this USDZ, and you can see this power of parametric representation where you can manipulate any elements in the scene. You have this hierarchical representation of a room, walls, doors, windows, and you can easily modify and edit them if you want. Okay, with that intro, I now want to jump a little bit into details of what are the models and the different algorithm pieces that we use inside RoomPlan. So the inputs that we take to this pipeline is coming from an RGB sensor, a depth sensor. We love camera poses, so we take camera poses also. And we also run a semantic segmentation model on top of RGB to create something that we call semantic point clouds. The semantic point clouds then fed into this big piece of pipeline that we call local reasoning that consists of 3 pieces in there. We have an algorithm that is in charge of detecting walls and opening. We have one that is in charge of detecting doors and windows. And we have one algorithm that is in charge of detecting the 3D objects. And this is the part that we call local reasoning. And this also feeds into our scan UI. Basically, the output of these 3 pieces are fed into our scan UI to show the progress of the scan that is made so far. And then we take the output of this local reasoning over the period of the scan. We feed it into this pipeline that is responsible for doing the global reasoning. And then we create this final dollhouse. So the components in the local reasoning and the global reasoning are the same, but the input that they take are slightly different. And there's a reason behind it that we're going to discuss it in details. So now let's go over every individual pieces of the pipeline that are contributing into this, creating this final dollhouse that you see here. So the first piece of the pipeline that we mention is the pipeline that is responsible for detecting walls and openings. So we divided everything into 3 pieces: walls and openings, windows and doors, and 3D objects. And one might question, why these 3? And why not doing it all within one model? Of course, we can talk about it. But the motivation behind it was you can look at walls and openings from a bird's eye view, and they all turn into lines, right? So the problem can be broken down into detecting lines if you're looking at it from a bird's eye view, because walls are, pretty structured, as well as openings. Doors and windows, if you look at it straight from a wall perspective, they can be 2D bounding boxes. But objects in the scene, they can have many orientation, and they're true 3D elements in the scene. So we kind of looked at it from this way: hey, walls can be line detection, doors and windows can be 2D detection, and other objects in the scene are 3D detection problem. So that's why we broke it down into 3 different subproblems. But the inputs to all of them are the same. We use point clouds for detecting walls and opening. We project everything into an XY plane. So we have a much finer details that we try to keep along the XY plane, because we want to be able to detect very small wall structures. But we pretty much lose a lot of accuracy along the Z-axis. We don't keep a lot of information along the Z-axis because we don't really need much in order to detect walls. And then we feed this into an end-to-end line detector. Basically, there's a neural network that is responsible for detecting these parametric lines, given this bird's eye view of the semantic point cloud. And that gives us a rough 2D room layout. And we do some post-processing, and then we create this 3D layout from the 2D lines. So this pipeline is capable of handling occlusion, small structures. We do handle glass and mirror walls, despite having some limitations around the depth sensor. We can talk about them if there are questions around it. We do support rooms of up to 30 feet by 30 feet, especially in the first version of Room Plan that we released in 22. And we also have a measurement accuracy of around 1.6 inches. Windows and doors, as we talked about it, this can be a 2D problem. Basically, now we have the walls information. So from the previous pipeline, we detected the walls. And now that we have the walls, we can take the semantic point clouds and create this wall projection input. Basically, we take the semantic and the distance of each semantic point to its nearest wall, and we create this orthographic projected semantic point clouds into each wall. And now we have this very special input that we feed it into a 2D object detection that is trained on the specific data, and we detect doors and windows into a very rectified space. And once we have that, given the camera pose, we project the doors and windows back into the 3D space, and you get the doors in 3D. Of course, one of the challenges that we had to deal with here is the definition of doors and windows, and also dealing with occlusion, because windows often come with curtains, and they occlude a lot of parts of the window, and there are many different variety of doors. And for us to have a unique definition, a lot of it went back into proper data collection and proper labeling definition to make sure that, and proper labeling tooling to make sure we not only can well define doors and windows and objects, but we can also well label them. We needed to have the right tooling. And the last piece of the pipeline, which is maybe the true 3D processing component of the pipeline, is the 3D object detection. So this directly operates in the 3D point clouds. Basically, we take the semantic point clouds, we create a custom frustum view based on the current camera pose. And the reason we don't just directly take every frame RGBD and do object detection, and we create this custom frustum that has a wider field of view, is that some objects can be pretty big, and you might not capture the entire object in one FOV of the camera. So we needed to actually start accumulating RGBD frames. Let's say when we reach this custom 180 or 140 frustum view that we have, then we take this input, feed it into our neural network, and then we detect the 3D objects. So you can think about it that even though the RGBD is running, let's say at 10 Hertz, we run the 3D object detection at a smaller frequency, let's say 2 Hertz, because we want to keep accumulating information and then boom, feed it to an object detection and then get the boxes. But one thing that you see in this graph is that we have a local detector and we have a global detector. And the reason for it is, again, some of the objects are pretty large. And you have this kitchen island that you detected over time. You might have 3 or 4 different bounding boxes that might represent a very large kitchen island, or very large table in a conference room, or kitchen cabinets are another very good example of them, that you will not be able to detect them with one bounding box and one custom frustum. So you will need to somehow accumulate bounding boxes over time and have some smart post-processing to merge and combine that. So we did this post-processing and merging through both a neural network that we call a global detector, that is just a detector responsible for detecting large objects. The local detector supports, let's say, 17, 18 categories. The global detector only supports a couple of them or a few of them. And then we have this fusion that takes all these accumulated bounding boxes over time and fuses them all together and create this large, nice looking bounding boxes that we can show to the user. So one thing that you see in this pipeline is there's a lot of fusion, post-processing, pre-processing involved that you often do not see in a lot of academic papers, right? You see, oh, someone has prepared the data for me, give me the RGBD, and then I get it, and the benchmark looks good. But it's not the case when you want to actually ship a product that runs on 100 or 200 million devices in a day. So a lot of work needs to go into actually building a pipeline that is reliable and the output is actually useful, right? So we spent a lot of time actually trying to figure this out, and that was the very non-trivial piece of this. Another big learning was that running these things on device was not quite easy, and running them in an efficient manner on our neural chip, neural engine was not also easy. And the main bottleneck that we had to overcome was that we were dealing with point clouds. A lot of these hardware is designed to process images perfectly. They're like really designed for this parallel structured data processing. But when you're dealing with point clouds, they're extremely unstructured. And the neural engine that we had wasn't necessarily designed to support this unstructured data at that point. So we spent a lot of time trying to bring some of this modern architecture at that time, which was, I think we experimented with pointed plus architectures. We experimented with the voxel-based architectures, 3D convolutions that, again, at a time, the hardware wasn't necessarily super friendly toward them. So we had to work with our silicon team, compiler team, optimization team to make sure that we can bring some of those point cloud-based architecture into our Apple ecosystem and run these models very efficiently. So that was the second thing I wanted to mention. And for power optimization, we not only did power optimization at model level, but also did a lot of power optimization at system level. For example, you still want to have a real-time 30 hertz or 60 hertz UI shown to the user. You saw that scan UI that we have, but a lot of the models do not run at 30 hertz. A lot of the models run at much lower frequencies. So for example, our depth estimation runs at 10 hertz, semantic runs at 10 hertz, object detection run at 2 hertz, the wall estimation. There are different components that run at different frequencies. So that's another consideration that we had to take into account. Okay, this is again another thing that becomes very product driven. We said, okay, we have put all of these things together and let's give it to the people and have them scan a bunch of houses. The behavior that you see from people is quite interesting because someone might get really close to the walls and start scanning the walls with like 30 centimeter distance, right? Or someone might, they might confuse this with scanning every single object in the scene, and it just takes them, what, I don't know, 2 hours to scan this room, right? And they completely hate the experience. They're going to throw their phone away, right? This is not good. I don't want to use this. So we don't want to be too descriptive. We want to let the UI do the magic, but at the same time, we want to detect when we think something is going wrong. And we thought about these 3 things that happens most of the time, that, you don't have enough light in the scene. It's dark and people think the LiDAR is going to do the magic and I'm going to be able to detect everything. Sure, the depth works, but the semantic segmentation depends on the RGB. It fails, right? The other one is that the people think, oh, I can scan the room in 2 seconds, and they start moving so fast. You still want a reasonable speed because you don't want to get a huge drift in your camera pose, right? And you also don't want to be too close to the object. So these were the 3 things that we thought we need to have in our coaching UI. So when someone is in a dark environment or moving too fast, we have this tiny little icon that we show to slow down. And when you work with the design team at Apple, it shouldn't be too long. It should not be a long description. It has to be very subtle, but at the same time noticeable to give the user the indication that they need for a good scan. I want to show you guys another thing that I just thought about. Maybe let me pause it here. Let's see if I can get a good read of this. Okay, so on the right, you can see that we have this wall line that is perfectly aligned with the edges, right? This was a lot of work to get it right because, again, we want the UI to be, as much as possible, give a good impression of what you're scanning. If the line that you're showing is off from the edges, immediately people would think, oh, this thing is not accurate. Look, it thinks that the wall is 10 centimeters away. And we know that when you're dealing with pose, you're dealing with depth, these things are going to happen, right? And the LiDAR sensor itself has some limitation in terms of accuracy. But we still wanted to overcome that. And the way to overcome that was leveraging the RGB sensor as much as possible, because that RGB at least gives you very good detailed high frequency information about the scene. So we had a lot of tricks and hacks in order to get that UI right and bringing that accuracy that we usually lose from the depth and the pose back into the system, not by just data collection, training, labeling, but also leveraging the RGB in the best way possible. Okay, putting it all together, this is showing a scan of a garage and also the living room that I showed earlier, that you can see all the objects are shown. How much more time do I have? To move quicker. Okay, great. I can move a little bit quicker. And so that was Room Plan version 1 that we released in 2022. In 2023, we had a couple major updates. And the first one was that they introduced this multi-room support. Basically, in the first version, we only supported rooms of up to 30 feet by 30 feet. But in the year after that, we enabled this multi-room scanning. Basically, we allowed the user to scan the room via separate sessions or within the same session, and we use SLAM relocalization along with a bunch of post-processing to kind of attach the rooms together and do the merging and correct the imperfection as much as possible in the post-processing step. Another thing that you see here, the objects are now represented with more finer details. You can see the dining tables, you can see the bar stools here, you can see the office chair have a proper representation. You can see round tables, sofas are represented better. So that brings me to the next set of features that we released in that year. One was we brought in a more fine-grained representation of the furnitures. And we also enabled this non-uniform wall height support. So if you have a room now with slanted ceiling, we should be able to support most of them. And a quick sneak peek into the pipeline that we put together for supporting this object attribute. We take the 3D bounding boxes from the 3D object detection that we have. We back project them into RGB, so we get multiple frame RGB crops for those boxes. We feed them into a neural network that takes both the point cloud and also the RGB crop, and then we do the prediction on the attributes of the object. What type of legs do they have? What type of arms do they have, etc. But it's not enough. For example, if you have a dining table with 3 chairs being nicely scanned, 3 chairs having occlusion, like if I start scanning here, your model is going to get a lot of good visible chairs into prediction. So 4 out of 5 chairs might be very nicely predicted as dining chair. The one that is occluded, you might not get a reliable prediction for it. So you might detect it as a bar stool. That's not good, right? You don't want to represent in the UI for dining chair. But if you use the context, if you know that's a dining chair, if you know that, around the dining chair, usually you're going to see similar looking chairs, then we can correct it. That's where the context modeling come into place and the fusion. Okay. I want to talk a little bit about data. We released part of the data that was used in training Room Plan back in 2021. And I want to talk a little bit about what we did to collect this data. Of course, we wanted the data to be captured on large number of scenes with very wide coverage of socioeconomic situations. We didn't want it to go to 1 or 2 countries. Again, it's a product that we released across all our Pro devices. We wanted to have a good coverage. So we did data collection across many different continents, and a lot of this data collection happened during COVID, because when we started this before COVID, then COVID hit and all our data collection teams had to figure out and change protocols of how to sanitize devices, how to ship devices, which countries are opening up for us to travel to and collect data. People were not really keen to letting us into their house and allowing us to collect data. So a lot of challenges that we had to also overcome during the pandemic. And we also wanted a ground truth sensor that was more accurate than the sensor that we were using on our devices. Because if we label data based on the Apple LiDAR sensor, it's good, it's accurate, but we wanted ground truth that is even more accurate. So we ended up choosing Faro scanners, which is a stationary laser scanner that we did an experiment between many different sensors, and we found Faro to be the most accurate one, and we chose that. So the data collection, basically, we collected a wide range of sensors, such as wide, ultra wide. We also got the Apple LiDAR outputs out from our data collections. and you can reconstruct scene with this level of accuracies. Then we also ask our operators to place a stationary laser scanner or a FARO in different part of the scene and do this long 20-minute scan of the scene. And when you combine them, you get, of course, you know, the edges are a lot more accurate. You get more of the high frequency information in. And then we register these two together. So now you have RGBD, which is both coming from the LiDAR sensor, and you also have a depth that is coming from the stationary FARO scanner. And then we released this data set back in 2021, which at a time was the largest RGBD data set captured. And here's a comparison with ScanNet back in 2021, where we had a much wider number of sequences with much larger number of unique scenes. And we also released 450,000 RGBD frame register with FARO scanner, which is great for training, I don't know, monocular object detector, monocular depth estimation or depth upsampling and things like that. We also released our 3D ground truth bounding boxes. So over time, we have seen the adoption of room plan also in variety of apps, from interior design, home improvement, like Planner 5D. We also have seen this has also been used in Magic Plan and Polycam, and we are getting the number of apps that are using this has grown. And we also have our good friend also here that he is also using it in his company and app. I hope it's still going on until today. Now I want to talk a little bit about what we are working on now and what are some of the research direction that we are excited about. One of them is open set object detection and classification. We want to move away from this category specific object detection and incrementally extending the number of classes. So we are very much interested in being able to detect everything, classify everything, hopefully in an open set fashion. Here you can see some of the results of the progress that we have made. So we are pretty excited by the work that we've done in this front. So we are really trying to push the boundaries of research in these directions, at least in my team. Another area that we are very interested in and we are exploring is basically bringing these pipelines into this multimodal large language models, and basically enabling this agent-like use cases that can leverage this world knowledge or the baked knowledge into this large multimodal models. So these models can take the output of room plan along with image and videos, along with a text prompt, and perform tasks in a very intuitive manner for the user. For example, you can just ask them to show you the dimensions of the TV, and you can get responses back. You can use them in AR, VR experiences and place content in your virtual environment by using a simple text prompt. Or you can actually even use them to control your home accessories by just again using natural language queries. Lastly, I want to talk about Vision Pro. This is again another piece of hardware that we spend many years enabling different perception pipelines on that. It's a magical device, I would call it, with a lot of different sensor, and you know it's amazing that all of these are packed in this device, and it becomes a very special computing device that you can do a lot of things with it. Because of the nature of this talk, being focused on scene understanding and spatial reasoning, I talk a little bit about some of the capabilities of Vision Pro today. We have plane detection in terms of scene understanding enabled on Vision Pro, where you can do precise object placement, shape estimation, semantic classification. Of course, we also have scene geometry on Vision Pro, and you can also do a lot of things like realistic physics interaction with the scenes given the meshes. But this year, actually last week, we introduced room tracking, which now we are bringing room plan capability into our Vision Pro. That before we had this concept of the room using planes, but now you actually have the concept of the room using room plan technology, similar technology and models that I showed you before. Now you're getting this nice walls. You can see it here. You have the floor estimation, you have the wall estimation, but you also are getting the concept of the room. So you know which room you're in as you have the Vision Pro on and you're tracking. So you can imagine that you're walking from one room to the other room, and you can load the content of that specific room as you're transitioning between rooms. I think with that, I'm going to conclude the talk and take any questions, if any.
Thank you very much, Afshin, for a great talk. I will say there are questions from the audience. However, we will have a very short from online.
Sure.
Very short question. They asked if we can, if point clouds obtained from other equipment, such as not an iPhone or an iPad LiDAR, can also be processed with the room plan API.
Unfortunately, no.
Okay.
No, not today. Yeah.
Okay, short answer. And now we are open to.
I got this question from a couple other people in the conference, so maybe but I need to take this back. Yeah.
Yeah. Feel free.
Yeah, Brian.
Yeah, thank you so much for your great work. You definitely knocked the ball out of the park with your great work at Apple.
Thank you.
So I have one question. You didn't discuss the staircases.
Mm-hmm.
And that's like when we integrated the room plan, and still we do, the main challenges that we observe from customers is the inaccuracy whenever we have staircases, even like a couple of stairs, and they want to know how many stairs, like steps are there. And then latest version, you do have some concept of stairs, but you don't show it. And there's no number of stairs. So are you planning to solve that problem, and how do you solve that problem?
Good question. So stairs today, the way that we are handling them is it's one of the categories in our 3D object detection. So we detect the stairs and we give 3D bounding boxes around the stairs. One of the challenges that we had in detecting the stairs goes back into the definition of the annotations. How do you label stairs? I don't know if anyone has tried to like label stairs before or define the stairs, especially in 3D. Do you just label 1 step, 2 steps, 3 steps? What if you have spiral staircase? And you want that accurate definition, because you not only are detecting them, but you also want to show them in the UI to the user to kind of get a sense of where things are. So I think it is a complicated structure, and at the same time, it's an important structure, because it's a structure in the house that you want to know that stairs are there. So in the current version, I can share a little bit about what we did. We basically labeled the stairs with a bounding box without orientation, and we called every 4 step a bounding box if there are more than that. So if there are like 12 steps, we put a bounding box around every 4 steps. And today we only provide a bounding box that kind of give you rough locations of where the stairs are. But we don't go beyond that, because I don't think we have a good solution for it at the moment. But we do recognize that it's an important structure information. If you have some ideas also, I would love to discuss it, because we have faced some issues in labeling them, defining them, and also figuring out whether stairs should be best solved as part of the 3D object category, or do they actually need their separate kind of way of handling when it comes to room structures. Yep, I'll take this and then we go to the back.
What's the approach relatively to reconstruct the plane?
Yes.
You can leverage lots of priors, but for the dynamic object, 3D object, how do you create such a high quality meshing? Even if you have a complicated meshes, it's hard to simplify together. How do you for chairs? It has very wide shape areas.
Yes. Yeah. A couple things to share is I think data becomes an important part of this, and also what we observed is having consistent ground truth quality can become pretty important, because how do you, like if you look at a lot of the data sets that are out there. If you look at the chair bounding boxes or object bounding boxes, the boxes are pretty loose. They're not very tight. They might not necessarily follow a very consistent definition of the bounding boxes. So we have this very high quality labeling tools where the labelers can actually see the projection of the boxes both in RGB and also in 3D. And we also have this Faro laser scanners that can allow the user to really define the bounding boxes around where the actual object is. That's one. The other one is in the network architecture design. So yeah, when you go to voxel size, we use an architecture that is based on 3D convolutions and a voxelized point cloud space. So we defined from the beginning that our goal is that we want to be able to detect objects that have at least one dimension larger than this size. So let's say 10 centimeter or 15 centimeter. So that dictated our voxel size resolution. And the third one goes into how do you leverage and fuse the two different modalities. You have RGB that gives you this very accurate high frequency information, and you have LiDAR that can be sensitive. It gives you a good depth information, but at the same time, around the edges, depth maps are not very good. You know, you don't necessarily get the best edge information. So how do you fuse this two modalities are I think the key ingredients in trying to get this right. Yeah, and I think we curated like some of the largest data sets that exist, because I mentioned we did data collection across many different countries. Yeah.
Thank you so much. Actually, I have a question regarding the frame of the sensor. What it would be actually like this one?
Let me go here. So we have multiple pieces here. The RGB is running at 30 hertz. The depth and semantic run at 10 hertz. Pose is running 30 or 60 hertz. Yeah, pose and RGB might be 30 or 60 depending on which stream of camera we are taking, either RGB or super wide. So I'm not super sure about that. But in terms of algorithms, 3D object detection runs at, I believe, 2 hertz. And doors and walls and opening run at much faster frequency, about 30 hertz, because we want to give this real-time feedback to the user. Yeah.
And for the LiDAR, is
10 hertz, yeah. We get the densified Apple depth at 10 hertz.
Oh, that's great.
Yeah.
And,
the LiDAR sensor it has a different frequency, but the densified Apple depth in the ARKit APIs, you also get it at 10 hertz.
And, how many things you should like one or
I don't recollect, because from sensor to sensor, it might have also changed. We should probably check online on the details of the actual sensor. Yeah, sorry, I don't remember. Yeah, I'll take a question.
You mentioned for walls or layout reconstruction, there was an error of like 1.6 inches.
Mhm.
Can you elaborate more on what that number means, like the metrics? And also, if you do know, like kind of like a lower bound for how accurate the LiDAR can realistically achieve, like, is that still 1.6 or is that actually a bit lower?
That's a good question. So we tracked a lot of metrics, by the way. So that is like the one number that I showed, but we of course have precision recall for detecting the walls, but we also have the size error. We also have metrics that are at the level of rooms, like how successfully you reconstruct a room. Is the user going to be happy by just looking at the results from a room level, not necessarily individual component level? But one of the metrics that we thought people really care about is going to be around what is your measurement error when it comes to walls, especially if you want to actually capture this 3D floor plans, that error is going to be important. So we basically created this balanced data set across different wall sizes, because your error can be different depending on what the size of the wall is. If you have a data set with a lot of 1 foot corner walls, or you have large walls. So we created this balanced validation data set and testing data sets. And that number that we report is the average wall size error across that balanced data set. And I think there's a tech report that we have put out that we also shared numbers on precision and recall accuracy of detecting the walls correctly. And that is also something that you can check out online. There's a
We'll
question.
take one last question.
Oh, okay, so
Sorry.
sorry,
but,
you picked then. You picked the last
no.
question. Yeah, maybe I'll take a question.
So what I've seen there,
I hope it's not a hard question. So
but it looks like it's hyperrectilinear. Do you deal with curved walls or walls that become
Okay.
ceilings? Or is there a plan to deal with that?
You see, we do support curved walls here. You can see one example that I showed here. But the curved walls that we support, we detect the presence of a curved wall, and then later on we do some Huff transfer curve fitting to actually get the exact location of the walls. So the curved walls do not go through this process. The model detect lines. For curved walls, we detect much smaller lines, and we do a Huff transform fitting to get the curved walls, but we do support curved walls. That was like a no-brainer from the beginning that we had to support them. Yeah. Good question.
If anybody has a very short one.
Okay.
What other software is complementary to RoomPlan or that? I mean, you mentioned ARKit. Is that
So RoomPlan APIs are released via ARKit. So we release a set of APIs. So all RoomPlan is a set of APIs, and we have sample app codes that people can use and write their own codes. There are a lot of companies that are using and building apps on top of RoomPlan, and Ryan Alimo actually is the CEO of one of the companies that is using RoomPlan APIs in their own apps. So if you want to go at a user level or application level, there are several apps that are using those APIs and bringing additional features on top of those APIs and try to overcome some of the things that we didn't release or we didn't provide via their apps.
so RoomPlan and ARKit?
Yeah.
Is pretty much the world.
From Apple perspective, those are the two pieces. Yeah.
Okay, great. Thanks.
Okay.
Great. Thank you so much
Thanks.
again. You will join us at the panel discussion.
Sure.
So you can ask more questions then. So come back in the afternoon for that. And there are a couple of questions on the chat online if you wanted to reply to them there.
Okay.
As you sit down.
Sure. Yeah.
Great.
Yeah, I got kicked out.
promised
Sure.
that, so-
It's good.
Great. So video and presentation. Are you sharing on Zoom? Yes. Yes. Oh, we are sharing. I'm not seeing the. We are not sharing this this side on Zoom. Let me do it again. Okay. Thank you. Good to go. Yeah. Hello, I'm Mira, and I'll talk about automatic defurnishing of indoor panoramas, which is a work we did at Matterport. So we set out to automatically defurnish panorama images, which means to digitally remove all furniture and non-structural items from them. This ability to reimagine a space without physically modifying it enables many applications related to the built environment, like virtual staging and planning of renovations and reconstructions. To solve the problem, we need to replace furniture with empty space consistent with its surroundings. And the recently most popular technique for such in-painting has been Stable Diffusion based, which works impressively on natural images, provided a well-dilated mask, but may not work as well on man-made environments. In particular, it is prone to hallucinations near shadows and light reflections, and it has been trained for relatively low-resolution square images, which exacerbates the hallucination problem for other resolutions, aspect ratios, and camera models. Another method for in-painting is Llama, which focuses on large masks. And for panorama in-painting, LGPN-net first estimates a layout of the space, while our approach doesn't need that. So with this in mind, we develop an approach that maximizes the available image context by working directly on equirectangular panoramas without need for mask dilation. To this end, we fine-tune Stable Diffusion in-painting on real unfurnished panorama images, and we make sure that our in-painting is robust to mask inaccuracies and lighting effects. We also develop a blending technique that maximizes high-frequency detail. So we start with pre-processing the high-resolution input, which we crop to a 3:1 ratio, on which we run semantic segmentation, from which we estimate a binary furniture mask from a predefined set of classes. We then pad and roll the image in order to maximize image context and place the region to be in-painted as centrally as possible. Finally, we downscale the input image to a height of 512 pixels in order to fit into a Stable Diffusion in-painting pipeline. To fine-tune, we collect a dataset of 160,000 equirectangular panoramas of real unfurnished spaces, into which we render synthetic furniture and shadows. To fine-tune, then we train with masks that only cover the furnishings, but not the shadows, so that we learn to ignore light effects and also to remove some of them near the masks. And we also perturb the masks in order to simulate semantic segmentation inaccuracies. We only perform low-rank adaptation of the UNet, and the entire process took about 96 hours on 8 GPUs. At inference time, we only use 1 GPU, on which we run 10 diffusion steps with the prompt empty room. And to initialize the latence for in-painting, instead of pure noise, we use a weighted combination with 3% latence based on the input image blurred under the in-painting mask. Our entire pipeline takes 12 seconds, out of which about 3.5 are for in-painting. After that, we have post-processing, which uses super resolution to restore the original image size. We undo the padding and rolling. And finally, we apply our custom blending, which takes as much high-frequency detail from the original panorama, and also makes sure to include pixels that are very different and might have gotten hallucinations. Finally, we compare to other methods that use mask dilation to ours without dilation, and here we only show the in-painting component of our pipeline for fairness. You can see on the top row that LGPN-net and Llama create a lot of blur under the mask and are unable to propagate context, while Stable Diffusion on the bottom left does well, but may hallucinate near shadows, while our approach does great. And please see our project page for more comparisons. Of course, there are some out of distribution cases where we still get hallucinations, and sometimes faraway regions create what appears to be structural changes, which can be remedied by using more views or geometric cues such as depth for controlling the in-painting. And the natural next step is to extend this to 3D for more applications related to 3D digital twins of buildings. So thank you for the attention, and please come to our poster. It will be poster 40, and then there is no Q&A right now, so you can go to the posters and speak to the authors. And now can we have the second paper to present, a two-stage masked autoencoder-based network for indoor depth completion? Please come. Thank you so much.
Okay, thanks. Our task is indoor depth completion, and the method is a two-stage mask autoencoder-based network. In the opening, as we know, scan to beam is precise translates the scan and the point cloud digital model into beam models. And the indoor 3D reconstruction is correct to 3D digital representation of the building. But there are many challenges. As we know, about 15% dips are missing in Matplotlib 3D datasets. So the dips completion is a very important task. Focus on using part of dips data in the real sense to obtain more dense and completed dips data. There are many reasons, such as the limited distance and the material and the lighting condition. However, the last model and the methods often suffer from the dynamic environment lighting conditions. So, as we know, the mask autoencoder can only apply particle authorization to reconstruct the whole image and learn the robust features. So we consider can we say the missing dips patches as masks? Means that can we use mask to simulate the missing dips patch? So we propose a network two step. One is pre-training encoder, which aims to learn the effective lantern representation, and decoder based on token fusion to complete the whole dips. It's a whole method. We divided them two stages. One stage pre-training. As we can say in the original dips, there are many missing value in the white area. So we mask them and I think the original RGB image, and then we pre-train the method. It's a safe supervision learning. We communicate the load function according to the truth dips where the pixel value larger than 0. In the second stage, we fine-tune the whole model based on token fusion and communicate the loss function in the whole image. Its result means that our pre-trained model is better than the traditional method, but our fine-tuned model without pre-training is achieves the super performance on the Matplotlib 3D datasets. In the figure, many methods are only smooth the missing area, but our method can learn the structure information, such as especially in the edge area. Another application is the indoor 3D reconstruction. We use the SL datasets and ORB-3 to reconstruct the indoor environment. We add the dips completion or not to compare the results. As we can say, the dips completion is very important in the 3D reconstruction. So the dips completion task also aligns with our topic. Okay, thank you.
Great. This will be poster 41. We follow that until we end up in 49. Next is the ARC2S dataset benchmark and challenges for learning exterior architectural structures from point clouds.
Hi. So good morning, my name is Kalong Chen, and I'm pleased to present our work on H2S dataset. So it's a benchmark designed for learning exterior architecture structure from point cloud. Project is a collaborative between the Chinese University of Hong Kong and Hong Kong Metropolitan University. I would like to extend my thanks to PhD supervisor or organizer and an audience in the workshops. So to improve So architecture segmentation is a crucial field in such as urban planning and constructions. Despite all the advancement in LiDAR technology and the availability of point cloud data sets, so there's a remain significant gap in detailed annotation of exterior architecture due to the lack of primarily due to privacy concern and the high costs associated with data acquisitions and annotation. To address this challenge, we introduced H2S. So our dataset consists of photorealistic 3D architecture located in Hong Kong, so with diverse building purposes. All raw models were derived from a public dataset from Hong Kong Land Department. To explain the preparation process, we will illustrate with an example model. Specifically, this model serves as an instructional material for human-in-loop annotation. The rationale for such human-labeled workflow is to ensure high-quality annotations by leveraging the expert knowledge and improve the model through continuous feedback. For our team to identify and to train the qualified annotator, they were invited to test label with the model. In the first stage for model preparation, we employ the UV texture mapping to our candidate model. Then we subsample the point from the mesh to generate point cloud. Finally, each point were annotated with one of the semantic classes correspond to the architectural element. The quality of annotated model was checked by our team one by one and returned to annotator for revision if any mislabeled. For our experiment, we benchmark our dataset using both convolution-based and transformer-based segmentation methods. We compared two with two CV evaluation matrix. Looking at the result, we conclude that convolution method perform better than the transformer in learning architectural exterior. Meanwhile, our analysis revealed two challenges. First, we found that segmentation performance varies significantly across different classes, with dominant class like wall and window achieve higher MIU score than the minor classes like beam and column. Secondly, we observed the inconsistent in annotations due to the semantic gaps. As shown in the figures, complex objects like ceiling and beam were mislabeled. So in conclusion, H2S dataset are pioneering work for detailed annotation and segmentation of exterior architecture exterior. While our benchmark have highlighted several challenges, they also underscore the potential for further advancement in BIM modeling and smart city applications. And thanks for your attention. And here's the GitHub link. Sorry.
Okay. And you also present the next one. Yeah.
So to continue, given the challenge and potential use case discussed in our first verse, so we asked how we can leverage this data set to improve the BIM and realize scan to BIM automations. To answer this question, we are pleased to present our second work, a unified framework for 3D reconstruction of the built environment. Again, I would like to extend my thanks to the workshop and also my PhD supervisor. So scan to BIM workflow has become increasingly prevalent in construction industry. It uses 3D laser scanning or 2D photogrammetry to capture the as-built and as-is conditions building to create the BIM. However, there's a research gap for unified framework for the digitizations. Our object is to introduce the SR BIM, a semantic reconstruction architecture aimed at automating the BIM modeling, addressing the error-prone and time-consuming aspect of the scan to BIM works. Our framework is built on 3 core components. So the with the trained point transformer version 2 segmentation model, the MFS module for reconstruction and refinement, and the BIM reconstruction pipeline. Together, 3 components streamline the process from initial segmentations to the creation of semantic enriched and visual appealing BIM model. Here's the overview of our SRB. In the first stage, point transformer version 2 is implemented for the 3D segmentations. It embeds input channel with an attentional group and process the point cloud feature through encode and decoding stage. The result is a set of output labels for each point to achieve the scene classifications, followed by the partitioning, which divides point cloud scenes into distinct segments. In the next phase, we introduce MFS module, which handle the mesh reconstruction and refinement process. It begins with surface reconstruction to create the initial mesh, followed by calculating the density. Then we apply the quantile filtering to remove the low density vertices, and finally smoothing to transform the segment into regular coherent mesh. The BIM reconstruction phase, we map the refined segments into the IFC schema. Each segment is assigned with a unique context identifier and mapped to the specific IFC predefined classes. For segments that do not match the IFC schema, they are mapped as IFC building element proxy, allowed for consistent semantic representations. Additionally, we apply the partition-based color coding to assign distinct color to each object entity. We tested the framework across various datasets, including the indoor scene, exterior architecture, and open landscape and urban scale environment. Looking at the result, it shows that MFS module enhanced the visual coherence of the built object, as demonstrated in the transition from original point cloud to the refined elements. We further validate through the histogram and reviewed improved the further density distribution after filtering and smoothing. Our results show that our framework could generate BIM model with accurate representations. Final BIM model are color-coded as semantic enriched for easy navigation and error detections. The final BIM are formatted in an OpenExchange IFC file, which have a wide compatibility with popular BIM platform. The BIM model consists of color-enriched IFC objects that inherit all attributes and definition of the IFC classes. Furthermore, each object is instantiated, which can be further reused and modified in another BIM project. In summary, SR BIM provides an efficient way to transform the reverse scan to BIM. Looking ahead, we are planning to expand and refine the SR BIM for enhanced segmentation performance and parametric modeling. So thanks for attention, and I'm happy to answer any question that you have, and you can find more detail in the GitHub link also.
Thank you very much. Do we have the team for enhancing polygonal building segmentation via oriented corners?
I'm joining remotely, yeah.
Or online?
May I share my screen?
Okay. Is the team online maybe?
I am online, yes.
Okay, great. Do
yeah.
you want to share your screen if you have it, or I can give you remote control?
No, I prefer to share my screen if.
Okay, then I will
yeah.
stop sharing from my side.
Okay, thank you.
Whenever you're
Yeah.
ready.
Can you see it?
Yes.
Okay. Hello, everyone. My name is Mohammad Moin Sheikhul Islami, and I'm going to present our paper, Enhancing Polygonal Building Segmentation via Oriented Corners, which is a mutual work from York University, Canada, and Jade University in Germany. Polygonal building segmentation is an important step in tasks like city modeling and mapping. And here our goal is to automate and enhance the quality using AI. But the problem is that deep networks usually output raster segmentation instead of vector. So to deal with this problem, there are two approaches adopted in the literature. Two-step methods try to first segment the buildings and using deep networks, and afterwards in the post process, they try to vectorize them. However, this can lead to some artifacts like unnecessary and redundant vertices and irregular shapes. On the other hand, the direct methods try to directly predict polygons, but they are hard to train and can lead to unrealistic edges and suffer from missing corners. So our proposal is to use oriented corners as a mid-level auxiliary representation for helping us with more regularized shapes, and also using predicted corners, we can inherently come up with more simplified polygons. Eventually, with the help of a GCN, we can directly output polygons. So we define orientations for each corner as actually we define two orientation vectors for each corner in clockwise and counterclockwise directions, pointing toward next corner in the building. And we formulate the orientation in the form of a pair of cosine and sine values, which enables us to enforce some regularization terms, such as orientation consistency in edges, where vectors should point to each other within each edge. So as our baseline, we use Mascar CNN, and we add some corner head. As you can see, it predicts a heat map as well as offsets, and the loss functions are weighted binary cross entropy and L1 loss. Also, we have an orientation head, which predicts 4 values per each edge pixel. And the loss function here is also smoothed L1 loss. Afterwards, we take the oriented corners as geometric features and concatenate them with semantic features to feed it to our next module, which is GCN. But before that, we need to initialize our polygon, which I mean, in the initialization module, we take predicted corners and masks, and by matching those, we can remove the blunder corners, add the missing ones, and connect the corners to come up with the initial polygon. And finally, in the GCN, at each step, at the GCN sample the features corresponding to corners and iteratively refines their position. The loss function here is a biprojection loss, and also we have two regularization terms, orthogonality loss, which punishes inner angles which are not orthogonal, and an orientation consistency loss, which has been already described. For our experiments, we used 2 data sets. We actually, for our ablation study, we used crowded a small data set. You can see how each module has the effectiveness of each module. And also you can compare it with HISEP, which was the former SOTA, and we outperformed it overall, but however, we see a gap in the performance in large ones, which we realized is due to actually ROI resampling artifact in Maskr CNN. Here you can see the performance on Vegas data set. And here you see how oriented corners can capture the architecture of the buildings. And this is a visual comparison with HISEP over different instances. To conclude, the proposed method demonstrated that the polygonal building segmentation could improve through enhanced semantic features by oriented corners and initializing building shape with predicted corners and regularizing the building shape by GCN. Thank you for listening.
Thank you very much. We will go now to the next presentation, which is about window to wall ratio. Great. Okay, let me also share my screen somehow. Zoom. I'm very terrible at Zoom, apparently. Okay, share screen. Share screen number 2. Oh, here it is. You see my mouse somewhere? Okay, great. And this one?
Yeah.
No, this seems as the other screen. We want desktop 2 here. Share. Yes. Sorry. I don't know why it's so complicated. And then hopefully anyway, do you need the
Yeah, maybe let me find my way. Oh, the mouse is still stuck. Let's see. Oh, here we go. Awesome. Okay, perfect. Thank you so much. Can you hear me? Perfect. Okay, well, great to speak to everyone today. My name is Zoe DeSimone, and today I'll be talking to you about window-to-wall ratios detection using semantic segmentation. This is work done together with some of my colleagues in the architecture and in CSAIL departments at MIT, Shayandeep Biswas and Oscar Wu. And just to get us started, window-to-wall ratios are the window area over the facade area in buildings. I don't know if this is updating. There we go. That changed. Perfect. All right. So window-to-wall ratios are the window area over the facade area in buildings, and they're key to assessing building performance, such as the energy consumption, the daylight conditions, and the ventilation of buildings. And particular research has shown that these window-to-wall ratios can actually have a really big impact on building energy models by up to 45%. However, the data to set up these environmental simulations is typically not available. So what ends up happening in practice is people use a standard 40% window-to-wall ratio. And to this end, there have been a lot of different research projects and papers looking at detecting these window-to-wall ratios automatically using computer vision. But in particular, these prior methods have typically fallen short in detecting complex window shapes. They approximate the whole image area as a proxy of the entire facade area. And they also have trouble handling cases where photos are zoomed out or taken at an angle. So to address some of these challenges, we developed a semantic segmentation dataset, and we also trained models to detect windows and walls concurrently. And finally, we developed a corner point detection method to reproject the images to frontal parallel views. So in our study in particular, we used a dataset comprising of 2,800 images of building facades, and we analyzed the distribution of these window-to-wall ratios across the dataset. And we found that the mean window-to-wall ratio is actually 15%, which is well below that 40% window-to-wall ratio that's used in practice. So it confirms that we should not be actually using these rules of thumbs that exist in practice, but we should actually be using much more sophisticated methods. And another thing that we noticed is that the raw data set we started consists of primarily JPEG images of building facades and then JSON annotations of windows. And while we initially tested a SegFormer semantic segmentation model, which happened to have a window class prediction, we actually found that the interior windows were detected really well, whereas exterior windows were sort of like a completely different set of problem. And so in our project, we created a new data set using the Segformer model to segment the building facade, so the pink regions that you can see here. And then we applied those window masks onto Segformer in order to create a new data set that also contained those exterior windows. And then we use this new data set to train two different models, fully convolutional neural net-based architecture with the ResNet 50 backbone, as well as a Segformer model. And in this work, we showcase how these models can be trained with limited resources. In particular, we only use 10% of our data set due to computational constraints of our research. And after each epoch, we computed the intersection over union metric, which you've seen in a lot of the research this far today. And from our preliminary results, we can see that the best performing FCN and Segformer model achieved similar IOU scores of approximately 65 and 66%. We also evaluated different things like the robustness of these models under different conditions. So here, for example, we can see that the model works really well on square windows. It does have some issues with glare, and it also has a hard time understanding when a window is a window and when it's actually a door. So some trouble there. And we also evaluated the robustness of the model under different times of day and different lighting conditions. And while it performs pretty well under different time conditions, we can see that the different levels of zoom actually make it a lot harder to detect the windows. And so this actually reflects some of our data set limitations, which is most of our images do have a more zoomed in image. So this could be augmented in future work just by looking at the data set scales. Another challenge that affects window-to-wall ratio is image perspective. So most of the real life images that we have of these buildings are taken at an angle from below. So this adds a lot of complexity to our task because window-to-wall area are actually distorted in these images, and so we might compute them incorrectly. So in order to fix this issue, we explore different perspective transformation techniques. In particular, we address this in our work by reprojecting the images to a frontal parallel view by using a 4-perspective transformation in OpenCV. And just to sort of touch back on prior work, while in prior work, there's mainly a lot of perspective correction and cropping to estimate the wall area at the beginning, and corner point window detection. In our work, we introduced a semantic segmentation model, dataset, and window models in order to segment these images. And we also use perspective reprojection using a corner point method after those semantic segmentation models are used. And some of the remaining challenges that we still are hoping to address in future work are looking at different reflections in windows, looking at high window-to-wall ratios, and figuring out if we can detect doors and windows much better. Yeah, so looking forward to talking to everyone at the poster session. Thank you so much.
All right, so our next speaker is so it's going to present an Expedia's spatial mean radiant temperature mapping net framework using VitoSlam and semantic segmentation. Yeah, from Liang Wei from CMU.
Hi everyone, I'm Wei from School of Architecture at CMU, and it's my honor to present our work. So a little bit background. Thermal comfort is crucial to our well-being, productivity in built environment, and mean radiant temperature, also called MRT, is an essential parameter that evaluates thermal comfort. However, it's less known to layperson. It actually converts the heat transfer between the human body and the actual surroundings into a temperature representation. So probably you can be sitting at a location where the air temperature could be totally okay, but you are exposed to direct sunlight or radiator heat, which makes you very uncomfortable. And also the mean radiant temperature current existing methods, they have several drawbacks, like the black globe temperature showing on the right-hand side of the picture. It takes a really long time to respond to the surroundings, and it's impossible to use that for like a large-scale spatial mapping of MRT evaluation. And also in the middle for the surface, there's another method which we evaluate the surface temperature of the six surfaces in the building environment, which could subject to very large errors due to the point-wise temperature measurements. And below is the equation for calculating MRT from the surface temperatures, which takes the surface temperature multiplied by F, which is the view factors of the surfaces to the viewpoint, which is the human being for our case. And the goal right here is to create an end-to-end MRT spatial mapping framework that can calculate the MRT measurements at any location in one shot. And also we're trying to introduce semantic segmentation techniques, try to retrieve more details from surfaces instead of just using one temperature to represent the entire surface. And here's a framework of our methodology, includes 4 steps. So the first one is design of the camera array, in which we use a thermal infrared camera, takes the temperature measurement, surface temperature measurement, and also the RGB camera, tracking camera, take care of the visual SLAM part. And we use a specialized tracker board made by materials with different emissivities, trying to use that to do the stereo calibration between the thermal camera and the RGB camera. And then we use a few measurements conducting the visual SLAM, which we use the RType map. It's a very renowned open source framework. And to create a point cloud, and also with the stereo calibration result, we can create the thermal, the temperature point cloud as well. And between the frames, we constantly evaluate and identify and measure the surface temperature on different features. For example, this one, we grasp the window from the surface, and then we use the grounding dyno. It's more flexible, open vocabulary identification framework to get a feature. And then we use the segmentation segment anything model to segment that and calculate the surface temperature of that part individually. And the 4th step is to take the detailed information together and calculate the view factors of the surfaces and features towards the person using the ray tracing method. And the results here we have the baseline surface temperature method compared with our result, and our result shows more detailed information of the room in terms of the mean radiant temperature. You can see close to the exterior window how the temperature distribution is different, and we also evaluate our method with the reference method is the black globe from on 4 spots, and the results show that the arrows are within acceptable range. So to conclude, SegMark can achieve more detailed and high resolution MRT field mapping, and also it's validated against the reference method. And the arrow complies with ISO 7726 standard. And however, compared to the in terms of the spot measurements, it doesn't show very compelling advantage in terms of the accuracy compared to the surface temperature method. And that's it. Please come to the post session for more details. Thank you.
All right, so one more slide. Yes, so we would like to welcome the next speaker about zero-shot construction object detection. And this will be presented by Mariam Soleimani from Louisiana State University.
Hello, everyone. My name is Mariam Soleimani from LSU, and I will present this paper on behalf of my colleagues. Oh, that was very fast. Okay, it's okay. I will be presenting my paper entitled Zero-Shot Construction Object Detection through Knowledge-Based Feature Integrators. ZSCO-DET, that is the abbreviated of this name, is a framework that can be a groundbreaking advancement in construction management, especially to transform safety and efficiency in the construction industry. You know, construction sites are dynamic and unpredictable, making it difficult to monitor and ensure safety. We often encounter new and unobserved objects that challenge traditional detection systems. This is where ZSCODET comes in with its innovative approach to zero-shot detection. Zero-shot detection aims to recognize and localize objects that have not been observed during training, assisting in improving accuracy and efficiency in detecting new objects. By enabling the detection of previously unobserved objects, this technology can revolutionize processes related to construction project safety, quality, and modular design. That plays a significant role in enhancing worker training and inspection systems in the construction industry for safer construction operations. In this regard, there are two major approaches. Mapping-based techniques attempt to map extracted visual features, a technique which suffer from bias towards observed classes when dealing with scenarios involving both observed and unobserved objects. To address this bias issue, employing generative models shows improved ZSD performance, zero-shot detection performance. Despite this progress, the performance is still limited by challenges like interclass similarity and intraclass variability, and we have a gap here. Overcoming these fine-grained challenges remains an open issue for further enhancing zero-shot object detection capabilities. Regarding our methodology, zero-shot construction object detection is an end-to-end network, including an object detecting module and also including an object detection module and the knowledge-based feature integrator, or KFI. For zero-shot construction object detection, KFI is composed of multiple components, including construction knowledge graph, as well as multimodal graph fusion to understand complex relationships between objects. We also have the local feature diffusion module, abbreviated to LFDM here, which enhances feature diversity, crucial for detecting a wide range of objects. The dataset used for this study encompasses a wide range of construction objects in indoor and outdoor construction environments, including tools, vehicles, and safety equipment, organized into a detailed hierarchical structure. Here you can see the distribution of objects among different classes. We have 73 classes here. We tested the proposed framework on a comprehensive construction dataset and the Pascal VOC dataset, which is a famous public dataset, to evaluate the real-world applicability and effectiveness of our framework. Our results show significant involvement in mean average precision across both datasets, which outperforms existing state-of-the-art methods in zero-shot detection. We also did an ablation study that further validated the importance of each component in the proposed framework. In conclusion, the proposed framework represents a significant step forward in construction object detection. Further work will focus on refining the model and integrating it with the latest language models to further enhance its capabilities. Thank you for your attention.
Thank you very much. Okay, our next Our next speaker is Mahdi Banyani on real-time ergonomic risk assessment in construction sites through spatial temporal graph convolutional network, please. And also from Louisiana State University.
Good afternoon. My name is Mahdi Bunyani from Louisiana State University. I'm excited to share our research about ergonomic risk assessment in the construction site, a project that aims to enhance safety and productivity in the construction industry. The construction industry is affected by work-related musculoskeletal disorders, significantly affecting worker productivity and safety. Traditional ergonomic assessment have a limitation, particularly in terms of accuracy and real-time applicability. Advances in computer vision and 3D pose estimation offer promising solution to these challenges. One of the most challenges in ergonomic assessment is dealing with noisy image or overlapping and missing key point data in the construction site. Accurate and robust key point prediction is essential for effective ergonomic assessment. Our objective is to develop a model that enhance extraction 3D posture from 2D images for enabling real-time assessment. For our experiment, we use 4 data sets from different perspectives. Also, we use these 4 data sets to extract comprehensive 2D and 3D posture key point data. Also, we use mean per joint position error for the evaluation metrics. We extracted a spatiotemporal feature by applying a spatiotemporal graph convolution network to extract the dynamic of dynamic in human movement to learning both 2D and 3D features simultaneously to extracted continuous and accurate ergonomic risk assessment in construction site. Our method have a 3 module. One of them is a CNN module that extracted a spatial feature from our image, and after that we use graph convolutional network and GRU module to extract a key point from temporal perspective. For the GRU module, we define a key point data and connection based on heat map extracted from the CNN module. And after that, we use variance-based attention to applying Gaussian noise to extracted key point data with to overcome the challenges about occlusion or missing key point data. Our result showed that our model have a advancement in the performance over the state-of-the-art method in the evaluation metrics of mean per joint position error, and also qualitative example of output of our model show that our model can extract all key point data from the body of worker in the construction site. Our results show that our proposed model have a robustness about the noisy image and missing key point data. Also, we have a real-time processing and prediction in the 3D data. For the future research, we have to refine the model to extract more comprehensive feature to capture different feature in the different domain of construction site. Also, this research have a potential application in construction safety to extract ergonomic risk in the body of workers. And finally, thank you for your attention.
Thank you very much.
Thank you.
Okay, so now we have our final talk, which is BEAM model for deep learning based parametric IFC reconstruction from KU Leuven and Bruno Kessler Foundation, Fondazione. Do we have a presenter here? Yeah.
Good morning, everyone. So I'm Sam de Geiter from the KU Leuven, and together with the Bruno Kessler Foundation, we take part in the challenge that we will present later also. So in this presentation, we will shortly introduce our framework for creating scan-to-BIM, a BIM model from scanning data. In our first step, we use the Point Transformer version 3 and point prompt training for first semantic segmentation of all the data for a first indication of the classes. Later on, we noticed that the column detection of this semantic segmentation models was not quite that good. So we used the top view of the point cloud to train another YOLO version 8 model on column detection on the floor plans. This combined with a decision module that computes the probability of detection being a column, focusing on the detection, the probability of the detection, the grid. So columns are located on a grid, so it computes how much columns are on the same grid and the distribution of the columns. Later on, we filtered all the detections and we created instance segmentation of all the points. From this instance segmentation, we took the lowest plane as floor and the highest plane as ceiling. For the wall reconstruction, we computed the wall geometries based on the planar planes that we can find in each other's neighborhood. And we use a decision function to compute the connections between the different walls. So we have a geometry reconstruction first, and afterwards we will do a topology reconstruction for the joining of the different wall geometries. For the column reconstructions, we fit a rectangular shape into the column points to reconstruct these columns. At the moment, we can only find and reconstruct rectangular columns. For the door detection, we use the wall detection to create an ortho image of the walls in the point cloud data, as you can see here in the images. And then we use the grounding Dino object detection, which is an open world object detection algorithm. So you can just give one word to it and it will search these objects in the images. And we found that it is pretty good in detecting these doors. So it will detect doors that are open and doors that are closed. But one of the main disadvantages of this is that due to occlusions, lots of other holes in the walls are detected as doors. So we put some conditions on these detections where we calculate the probability of a detection being a door based on the height, the width, and the distance to the ground based on the wall between the ground level and the ceiling level. Afterwards, we can reconstruct these door geometries based on the size of the bounding box, but also based on the point cloud data where we do a ray tracing through the wall from both sides. Thank you for your attention.
Okay, so that concludes our oral session. And thanks to all the I'd like to thank all the speaker again. And then for actually, there's some really nice work here incorporating the latest state-of-the-art approach into building reconstruction. So next up, we have a lunch break as well as the poster session. So the posters are in the other building, unfortunately, Arch building. And then we are poster 40 to 49. I'm sorry, it's a little bit of a walk, but it's probably good. You can try to first grab lunch and then go for a stroll and then see you there. And then I think we reconvene in this room at like 2:15, 2:15. Yep. All right. Yeah. Thank you very much, everyone. Thank you very much. See you in the afternoon. Yes. Yes, for the people on Zoom, sorry, I forgot to unmute. We are starting the afternoon session, and then we are going to start with challenge winner presentations. This year, so as we mentioned in the beginning of the workshop, in the opening of the workshop, we have both 2D challenges and 3D challenges. This year, we only had one entry in the 2D challenge, so that's a little bit not that great. The result in terms of IOU is 56.3%, which actually regressed a little bit with respect to last year's results. But I think some of the F1 scores actually got slightly better, so that's a good change. And so we will basically have this one presenter, and afterwards we will have the results from the 3D challenge. Where we will have like the top three, like the first place, runner up, and third place. We'll have 3 presentations for the 3D challenge. Seems like 3D is much more well received than the 2D challenge here. So here we will go with then this first presentation. This is from Longyong Wu, Ziqi Li, Meng Sun, and Fan Xue. Is that the presenter is the presenter remote or in person?
Remote.
On Zoom?
In Zoom.
I think they are hearing me fine. Oh, speaker. Okay.
Hear them.
To hear them. Okay. Is the presenter on Zoom?
What? Can you hear me?
Yes.
Oh, they can share their screen.
Okay.
Yes.
Yeah. Could you maybe share your screen instead of using our screen for this presentation?
Oh, okay.
Yeah, you can just share screen on Zoom. Great. All right, so you can take it away then. You know that. Your presenter view. Maybe you can try to share your other screen.
Oh, sorry. Sorry.
Great.
Yes, this works. Yeah, we are muted.
Oh, no, we're not. Whenever you're ready, you can start.
Okay.
Okay. Wow. Good afternoon, everyone. Today I'm excited to share our work at the 2D challenge, although it has one entry for this challenge. Many thanks to our workshop organizers' contribution to prepare for this scan to beam challenges. We're from the Faculty of Architecture, the University of Hong Kong. Is there a possible solution that I can use the present view and the Zoom is using the full screen?
Yes, you can first start presentation and then go to Zoom, share the screen that is your presentation and not your presenter view. So first start the presentation and then go to Zoom. Yeah, just start from the current slide. Fine.
Yeah.
Yes, this is actually already good from our side.
Okay.
Yeah, you don't need to do anything. This is already good.
Okay.
Yeah, just keep going. Just keep your presentation. Keep going with your presentation. You don't need to do anything. It's already good.
Oh, sorry.
Yes, just keep going.
We're from the Faculty of Architecture and the University of Hong Kong. Our team have 4 members. My name is Wen Yong, and the other 3 members are Liz Qi, Sun Meng, and Xue Huan. Our research interests include building reconstruction from point cloud rendering and its application in construction, digital twin construction, simulation-based optimization, and data processing. Then floor plan is actually the most commonly used media to present the indoor layout in architecture, engineering, construction, and operations. We have a great amount achieved floor plans for existing buildings. Besides, the collecting cost of this floor plan is relatively low. This could be very helpful if we want to collect a lot of floor plans to implement some data-driven ideas. Applications such as scan to beam, scan to floor plans, or scan with beam, or the comparison between scan beam are discussed a lot of in both literature and practice in recent years. Our pipeline could directly divide it into 2 parts. The first one based on 2-dimensional pixels, encoding 3D point cloud to 2D images, and predict line segment with help of LCNN. The second one facilitated the point contrast to estimate the semantic information and then estimate plane planners. The first one could guarantee the intersecting line segment enclosed because of the resolution have been reduced, which could offer us a watertight polygon. However, this method missed some structural lines due to the information degeneration in the encoding process. Though the second one combine both of the structural lines, the complete structural lines and the watertight polygon, which could produce a 1 + 1 is larger than 2. And the pre-processing step is same as the last year. We use the non-occupied cluster to estimate the rooms. This year we use LCNN network design for edge detection in normal photos, which is faster than the 2022 method. And the planet detection, we don't choose the Ransan as we use this planar detection method, which utilize a recursive algorithm. The advantage of this algorithm is that it can stably estimate in a small planners, which is suitable for built environments with occlusions and missing point clouds. And also this is that we have also try to use segment aliasing to estimate the rooms using the density map. This method was proposed by Li Ziqi. And also to fix the master operation by different class. He also tried to use the graph theory and depth first search to solve this issue. And this is the results of this year. This is the mean intersection of a unit which is larger than 80%. And for the discussion part, there's some question about the evaluation system, like I have tried to merge some line segments this year, and you can see in the center of the graph, and because use the unweighted bipartite match, and note the biggest one to match the biggest one using their area. So may cause the score to fluctuate to make the result fluctuating. In the left is 80%, but in the right is only 25. I guess this was caused by the unweighted bipartite. And the second one is two results from same building, 2 floors from the same building. They have similar structure, but the floor two, but the second floor with watertight estimate results would get a very lower result than the unwatertight one. And thanks for your attention. Hello, anybody have any
Yes,
questions?
sorry, yes, is there any? We have time probably for one question. Do you have any questions? Okay, so maybe after the challenge we can talk, and then we can connect with you, and then we can discuss some of these issues in the 2D evaluation metrics.
Oh, so thank you, thank you.
Yeah.
Because I found the bipartite use unweighted, but the IOU calculation use weighted IOU. So I don't know why.
Okay. All right, so we can talk about this offline. Thank you. All right. And present this. How do I? Oh, here. Oh, sorry, that's not here. Okay, so right, so that is 2D challenge. And then here we have the results from the 3D challenge. So this line is actually not right. So the year of 2022, we have a different test set. but I think the test set between 23 and this year is actually the same. So this results are comparable. So as we can see that for winner of 2023, we used to have a IOU of 43% and F1 of 0.56. And then this year, we definitely improved in terms of IOU to 45%. I think one thing that is significantly improved is the column IOU. So that was done much better than last year. So these are our top three entries, Hong Kong University, KU Leuven, and then DFKI. And so, yeah, we like to congratulate the winners. And then our first presentation, I believe, is a recording. And so we'll play the recording. And then the author said they might be online on Zoom to answer the questions. So here.
Good afternoon, colleagues and friends. I'm Frank Xue. We are a team from the Faculty of Architecture, University of Hong Kong. So the title here I would like to share is how to handling the occlusion in the scatter beam automation. We have a pretty long name for the pipeline. For short, it's Space Code. And about our pipeline, usually we say the scatter beam has 4 steps. And the first step is the point level semantic segmentation. And the second step is the general architectural elements detection. And the third is detailed beam objects detection. And we're happy to see that the CV4AEC workshop is great in covering 3 steps in this workflow. Although we do not have the details requirements for the door handles and hinges for the very detailed door objects. And we know that the third step is very often the most time-consuming part. And finally, we will have the open beam and the city information model applications based on the scatter beam results. And this year, our focus is trying to handle 2 of the common challenges faced by the LiDAR data processing. So we know that in the common LiDAR scans, we have the clutters and unwanted environment. You can say the noise, and also have unbalanced building types, as well as openings. Because we have movable parts for openings, like the doors, lift, and the windows. Sometimes they are closed, sometimes they are open, sometimes they are semi-open. So this leads to the multiple and sometimes uncertain of the points have been scanned. Also occlusions, that is a But this year we try to force the deep learning to predict the previously non-existing points, but we do the completion of the voids. Therefore, there's some newly added points for the deep learning models to focus on. And next, we think the graph deep learning as well as the newly proposed Kolmogorov.
I'm sorry.
Neural network could be even more useful. And we also recommend the workshop to consider to linking the JSON format into the IFC and OpenBeam to trigger the applications regarding the building structure envelope as well as the services. Okay, that's all. Thank you. Any questions?
Right. Any questions, both from the in-person and the remote audience? Sorry, we lost you the Zoom for a couple of minutes before we discovered the issue. Right. If there is no, oh, there is a question. Yes.
How well is the filling in, I guess?
So let's see, first of all.
Let's see actually if the speakers are online. I think they
actually,
are.
I'm online.
Yes. Did you hear the question?
Yeah, but the voice very low. I cannot hear clearly.
Okay, the question is how well does the fill-in algorithm work, right? Yes, yes.
You mean the fill-in algorithm?
The filling, like you have this incomplete elements and then you fill it in, like you're trying to complete it, I believe. How well does that work, do you think?
Yeah, I think it works very well for the planar objects, especially for the walls and doors we focused in this challenge. And also the planar feature as well as the missing points on planes are relatively, characteristic. They have very good features to attract, and we do not need to waste too much of the computational power. And these points are pretty worthy the time to, with around 5% of extra points, and then we have the complete geometry of the 3D objects. Otherwise, the initial proposal has a low quality, and then the final output model also will be impact. So yeah, I think the overall filling these points, completing the planar whole plane is worthy the step. Yeah.
Okay, thank you very much. Any other questions? All right, thank you very much for being here as well as sharing the remote presentation. Okay, let's go to the next speaker. And
good afternoon, colleagues and friends.
Sorry, this is still the same. The next number 2 group is from KU Leuven, and BEAM module for deep learning based parametric IFC reconstruction. Thank you.
Good afternoon, everyone. Yeah, it's a little bit the same presentation as earlier, but I'll try to tell something more about it. So first, we participated in this challenge together with the Bruno Kessler Foundation and the KU Leuven. I'm from the KU Leuven. And it's the first time we do such a challenge. And we started by doing simple 3D semantic segmentation on the point cloud data. So we semantically segmented the data using Point Transformer version 3. But when you see, can you see the mouse? Yes. So when you see in this data, there are a lot of problems still on the data. Like here, you see the columns are not quite well segmented as we should expect. Therefore, we implemented another column detection step where we actually take an orthogonal picture of the point cloud from above, and we trained it a YOLO version 8 object detection model using RoboFlow to detect these models from the top view, these columns from the top view. As you can see in this image, he detects some columns. It actually works pretty well. And then we compute the likeliness of the objects being columns. So we take into account the probability of the detection, the gridness of the columns. So it takes the different detections and looks where are grids into the building, because mostly columns are located on a grid, and the 3D distribution of the columns and the points on the column. Here in the image below, you see the likeliness of a column, so how greener it is, or how more likely it is a correct column. Later on, we take the input of this semantic segmentation step and the column detection, and we start an instance segmentation. So we are going to cluster all the points together for instances, so we can later reconstruct the separate instances for BIM to create BIM model of it. For the floors and the ceilings, we take the lowest cluster of points in a planar surface and the highest cluster of points to create the reference levels for the further reconstruction. We will also use it to model the height of the walls and the columns, so they are just from the floor to the ceiling. For the wall reconstruction, we will use every instance and we will detect the planar planed surfaces in these clusters. And we will also try to find matches with closely by clusters. Then when we detect two planar planes close to each other, we will model the center axis of the wall, and we will then extract the depth and the length of the wall. The height is, as I said before, just from between the two levels. To detect the outer walls, we will use array casting from outside of the scene to detect the outer walls. This will be later used in other steps for the door detection in this case. For the columns, we use the clusters of the different columns. It's a normal DB-scan clustering algorithm, and we model them using Randstad fitting on the dominant plane, and then we draw a rectangular column out of it. At the moment, it only works on rectangular columns. For the door detection, we use the detected walls, and we are going to make an ortho image of each wall from the point cloud. And then we are going to use the grounding Dino object detection, which is an open world object detection algorithm, to detect the different door occurrences. As you can see in the image, the doors are pretty well detected, so it finds doors that are closed and doors that are open, so that are not present in the data set. We will do this from both sides of the wall to exclude doors that are just standing open against another wall, because that was one of the challenges to extract these. Additionally, we put some constraints on the detections. So we put a constraint on the height of the doors, the width and the distance to the ground to exclude a lot of false detections. For the door reconstruction, we then used the bounding box, but also array casting on the point cloud to find the openings in the walls. And we extracted the width and the height of the doors this way. And I think that is my presentation for today. Thank you for listening.
Thank you very much. We'll be able to field one question if there's any. Yes.
Maybe can you share a little bit more on how you reconstruct the outer walls? I know that's sort of a common problem because it's sometimes very hard to tell on the over top scan because you don't get external scans. Do you have what problems like? Can you just elaborate on like what do you find difficult out there?
Well, for the wall reconstruction of the other walls, it's indeed very difficult because you will only have one face of the wall. So when we have one face of the wall only, we determine the normal and we just do an offset of, I think it was 10 centimeters to the outside, and we assumed it was 10 centimeters for the moment.
All right, thank you very much. All right, thanks the speaker again. All right, our third place speaker is from Humantech, Scan2Beam Digital Twin Generation Pipeline. Yeah, please.
Thank you. Hello, everyone. I'm Jason Rambach from DFKI, and I'm happy to present to you our method for Scan2Beam that we used in this challenge. So I wanted to introduce quickly the team. So it's an interdisciplinary team. We have Fabian, who is from the civil engineering side from the University of Kaiserslautern in Germany. And Mahdi and myself, we are from the computer vision side from DFKI. The pipeline is not much different than the rest of the participants, I think. So there are a lot of similarities. We also start with semantic segmentation, deep learning-based semantic segmentation. Then we have some density-based clustering for the different elements. Then the walls are treated differently. So we try to fit planes, and we try actually to find 2 planes in order to get the thickness of the wall. And well, and then we fit bounding boxes around the objects. And as a final step, there are some post-processing algorithms that we use to try to merge the walls, close some openings, basically make it a watertight reconstruction. Yeah, so it's actually the second year that we participate in this challenge. We're quite happy because, well, our main competitor is ourselves, so we are happy that we were able to increase by 5% our score this year. Yeah, I will not go into details on all the parts of the method because of time, but I would like to just talk quickly about some improvements that we made this year that helped us improve the score. So on the semantic segmentation, we also switched to point transformer v3. Another differentiation was that this time we used all the classes in the inference, not just the classes that are used for the challenge objects. Another yes, big challenge, as you saw already, are the doors. So how to handle the doors, because if a door is open, you might get some points on the frame of the door and some points on the leaf. So we tried to solve this in the point cloud, not using 2D images. So there are 2 approaches to this. One is to try to find the leaf of the door and try to rotate it to align it with the wall. Another option is just to look for openings in the wall, so along the walls by taking a histogram at a specific level and checking the density. In the end, what we do is a combination of both approaches. Yeah, as next steps, we will try to improve the performance on outside walls. And incomplete walls, we struggle a bit with the columns, especially the ones that are inside walls. We want to improve the segmentation even further because that is probably the most crucial part, is the base of the method. Yes, and well, we continue to use or to adapt. We're going to adapt the pipeline to apply to different problems in our project. So we want to use it also for construction progress monitoring, construction site object localization, and also move towards Scan2BIM, so Scan2BIM for bridges, basically. Yes, finally, if you would like to know more about the Humantech project, is a large European project where we try to bring computer vision and robotics to construction. So you can follow this link if you would like to know more. Thank you very much.
All right, thank you very much. any pressing question? We are really running a bit late. So yeah, thank you very much. Okay, so I guess you can take over then.
Okay. So now we will go to our next keynote speaker. Let me stop sharing and oh, I always lock my screen. Caitlin, are you with us? Oh,
Yeah.
wait.
Yes, I am.
Okay.
Can you hear me?
Yes, we can hear you very well.
Great.
Okay, so so everyone, I'm very excited to have with us today Caitlin Miller. She's a professor at MIT at both the Department of Architecture and the Civil Engineering department, and her work focuses a lot on computational design and how we can use algorithms in order to create more optimized structures and forms for the built environment. I will not say more. I know Caitlin for quite a few years now, and we have interacted in different ways. And I am very excited that this year she was able to really make this workshop, even if it is online. Caitlin, the floor is yours. Thank you so much again.
Thank you so much, Iro, for inviting me, and apologies to everyone that I'm zooming in, but I'm really excited to share some of my work with you here today. As Iro said, I'm faculty at MIT in architecture and civil and environmental engineering. I run a research group here called Digital Structures, which is an interdisciplinary research group of graduate students and other researchers working across architecture, structural engineering, mathematics, computer science, mechanical engineering. And we're united by an interest in promoting performance in the built environment. And we do that in a way that is expansive, where we're interested in discovering new innovative ideas for form, material, space, that at the same time substantially reduce the use of material in construction. We start with buildings like this that are some of my favorite from around the world that show many different possible ways to do this, to use material very efficiently in order to create new ideas and really expand the visual palette of architecture. And I start with this because for me, a really key motivating principle in my work is that pursuing performance in design and construction is not a limiting technique. It's not a way to reduce the potential of creative authors like architects, but it's really a way to expand what we can achieve as humans and really discover new ideas that we wouldn't be able to find otherwise. It's also an imperative in today's context in the climate crisis. You probably know that the AEC industry is responsible for about 40% of global greenhouse gas emissions, and a growing percentage of that is due to so-called embodied carbon emissions, the emissions associated with extracting and transporting and producing the materials that we use in buildings. Not only is this a really large percentage of overall greenhouse gas emissions, about 10% total, but it's also one that has substantial variation across the built environment. This is an example of work from Catherine, who was speaking today in this workshop earlier. And what she found during her PhD, looking at many buildings around the world, is that there are variations in embodied carbon of up to 14x. So not 14% more, 14 times more. These are two Olympic stadia built 4 years apart out of the same material. The Beijing Olympic Stadium uses 14 times as much embodied carbon per seat as the London Olympic Stadium because of how the material is allocated in space. It's really a question of design. And to me, this really brings forward the point that performance must play a role in design. I'm interested in doing that through formalized processes like design spaces, which link an understanding of design decisions with performance. So in this simple example of a design space for a truss, if I change the geometry of the truss, the amount of material I need to support the given load varies, sometimes dramatically. And of course, I could find the optimal solutions in this design space using algorithms that have been well known for more than a generation at this point. But in fact, those algorithms are almost never used to design buildings. Optimization is very rarely used as a fundamental design technique. And that's because it's very hard for us to express an objective function that fully covers all of the goals of architecture. But the design space contains more than just a single optimal solution. And in fact, I think it contains many really good ideas. And so we can still use the idea of a formalized design space, but relax the idea of just pure optimization to find solutions that are very good here, 10%, 20%, 30% worse than the very best solution in the space, but that also allow us to incorporate a broader range of goals related to human experience, construction, context, culture, etc. Part of my work is about exploiting that potential to bring the human into the process of searching the design space for great ideas. This is a tool that I built that allows us to do that for trusses, where the tool produces ideas for designs. They're evaluated in terms of how much material they need to be constructed. And then the user interacts by selecting the designs they find interesting, which then the algorithm uses as seeds to essentially do interpolation and some randomization to generate new ideas that are both high performing and diverse and that incorporate the feedback of the human user. To me, this is a really interesting approach because it shows that there are a wide variety of high performing solutions, again, that can be discovered in this design space, some of which are quite different from each other. So in this case, the designs are improving in performance from left to right. All the way on the right are designs found through history, through analytical methods to be materially optimal. But in the middle of this graph are also designs that are not the optimal solution to any analytical problem or to any objective function that I can write down, but might actually be really exciting new solutions that are both highly materially efficient and also more generally relevant to the human task of architectural design. In my work more recently, I've been excited about how we can apply similar thinking to more complex problems by harnessing advances in machine learning. So for example, generative modeling or generative AI, such as variational autoencoders, could be ways for us to learn new design spaces that are relevant to the built environment. So for example, in this case, we took this 36-dimensional hand-coded parametric model for this roof truss and found a low-dimensional representation of it in this latent space, a 2D representation. We map that latent space over a performance landscape. So we can evaluate all of the designs in this space to find a new space of potential solutions that a human can explore. So we don't necessarily need to optimize, but we can search through this space intuitively in a human way and really achieve very large variation and really find new ideas that we couldn't find by ourselves. Of course, we can also use machine learning to improve our ability to estimate performance. Here, we're using a surrogate model, so a supervised learning model based on training data that estimates not only a single scalar version of performance, but an entire field. Here, we're essentially estimating the solution to a topology optimization problem, like a field over a surface that then gets translated into geometry that could be built. And so then that's all connected to a latent space. So in real time, we start to have tools that connect engineering, simulation, and design exploration in one framework. I'm also excited about the potential of machine learning to expand the interfaces that we use in design. So can we use techniques such as sketching, which have a lot of benefits in terms of connectivity to human users and a naturalness of how we work, and use those sketches to access a latent space that's already trained. So here we're predicting the performance of those sketches and projecting them into another sort of variational autoencoder-based latent space so that we can interpolate between ideas. So now we can discover new ideas we haven't thought of already by searching these pre-trained continuous spaces. We can also work with increasingly diverse representations of geometry for buildings. So here, we started with a synthetic data set of several thousand massing models for buildings and using new learned representations, in this case, a neural implicit representation. So learning a signed distance field that represents a compact version of this design. We can construct latent spaces that can be interpolated as we're showing here, or latent spaces that can have performance landscape mapped over them so that we can do things like optimization. In this case, we're mapping the performance of how well the building has access to views of the sky view factor. But we could map many different performance metrics on top of this to start to access new ways of understanding performance and design. I'm really excited about how wild data could contribute to some of these ideas, which is challenging because it's poorly structured and highly varied, but also more realistic than synthetic data in terms of what humans actually want. So one source of wild data that I think is really exciting are competition entries that individual human designers have submitted to the same challenge. On the top is a very old competition for the Tower of London from the 1890s that engineers submitted entries to. On the bottom is a competition for jet engine brackets that was conducted about 10 years ago. We worked with the latter data set. We simulated all the designs that people submitted in finite element analysis software. and also started to use, again, these neural implicit representations to explore a new continuous design space across these discrete concepts. So here we're demonstrating that we can interpolate again between two individual designs provided by humans to generate new concepts that combine the benefits of both, that blend between both. We can even expand this idea to kind of a new interface for design, where maybe instead of encoding a design with a parametric representation or some kind of explicit modeling technique, design is achieved by blending between discrete concepts that come from 3D point cloud scans or models that we make on our computer or sketches. If we can put all of these representations into the same latent space, we have many more handles by which we can generate design. So here we're interpolating across 5 discrete design concepts with various weights that a user can control to generate new ideas. So that was a very quick whirlwind of how I'm interested in using modern AI techniques to improve design. The rest of my presentation, I want to talk more about construction. Because what I found in my 10 years of doing this research is that while we have a lot of potential with these computational design techniques to expand high performance architecture, we often have challenges in construction because the resulting designs embody substantial complexity compared to traditional construction and design techniques. And so I'm interested in exploring how advances in robotics, digital fabrication, and related technologies could provide a pathway to economically achieve these low carbon structures. In general, it's true that as structures become more efficient, they often become more complex. And so here's an example where a lattice kind of bridge structure is morphing in order to reduce its strain energy, which means improve its stiffness. And as we do that, every bar becomes different in length. Every node has a different geometry of connectivity. This would be a nightmare to construct through conventional means. And any savings that we can conceptually or theoretically achieve through material reduction would be wiped out by the added cost of the construction complexity. This has really led me to pursue techniques like digital fabrication, which dramatically transform the economics of what is hard and what is easy, or what's expensive and what's cheap. So for example, in this technique in which a robot is extruding a material spatially, so this is a 6-axis robotic arm, it can create a spatial truss in which every node is different, every bar has a different length, and it's indifferent to whether that's all the parts are the same or different. The code is only slightly different to execute. And it allows us to push towards a new kind of aesthetic for architecture that could potentially be economical or just as economical to build the efficient version. We can push that further by looking at questions like topology. So instead of morphing a lattice, can I use something like topology optimization to prune the lattice to find the most efficient connectivity for transferring load in a structure? Of course I can. These techniques have been around for a long time, but actually fabricating them, again, becomes quite complicated. Using modern advances in task and motion planning from the robotics community, we can start to automate the planning of how to extrude or assemble these complex structures. So accounting for things like collisions and the overall sequence and the stability during construction. We've developed techniques to account for all of that, to automate the planning, so that a structure that's very complex, like this topology optimized bridge or beam structure that I personally could never build by hand, and I think in general it would be quite complex, can be built quite simply by a robot in a small amount of time. And we've gotten this so fast in terms of planning that can now be an input into the design process. So we can automate by automating or algorithmically defining construction planning, we can account for construction natively as we're designing new ideas. I'm really excited about that idea. I'm also trying to apply the same thinking to much more everyday cases that have large impact on the climate crisis. One area is concrete, which is the most ubiquitous construction material in the world. It's how most of the built environment is made. And it's almost always used in an incredibly wasteful way, where usually more than half of the concrete in construction is not necessarily structurally, but is really just there for ease of fabrication, because it's easier to make flat, large rectangles than highly articulated shapes like the one shown on this slide. We've developed a technique in my research group to find ways to carve away unnecessary material using constrained optimization. This technique accounts for modern concrete mechanics and meets building codes in all countries around the world. We do that by parameterizing the outer boundary representation of a concrete element, and then sectionally checking shear and moment resistance and overall deflection along the length. with an objective of minimizing the total embodied carbon due to concrete and reinforcing steel, subject to these structural mechanics constraints. And it allows us to achieve large savings across a range of techniques, including different ways of fabricating these elements. And so in this case, we worked with partners in India to fabricate formwork for this structure using elastically bent steel that was laser cut on a machine they already had. This was a technique they were already using to make formwork quite regularly, so it was very easy for us to parameterize our system to meet the types of formwork they were able to use. And we've shown that these types of highly optimized beams can be tested, meet building code, perform as expected, produce kind of new aesthetics and new potentials for architectural interiors where the structure is really celebrated rather than hidden. We've developed open source, easy to use tools so that architects and engineers can apply similar thinking or use the same technique in a number of circumstances, but then we've used those tools also to generate a lot of data about these reinforced concrete structures. So this is a large sample of the design space where we're looking for different spans, for different depths, for different concrete strengths, different applied loading, et cetera. What's the range of embodied carbon? Which designs are feasible? How does that kind of map across the design space? And with that large data set, of course, we can also build a predictive model. So here we've built a pretty simple MLP-based surrogate model that takes in these kind of salient engineering parameters that an architect or an engineer might have. And the output is variables that describe the geometry of the optimized concrete system. And the benefit of that is we go from several minutes to an hour to optimize an element to instantaneous optimization. So we can really start to compare scenarios instantly. We can see how much carbon we can save by going from a flat slab to this shaped slab, for example, in many different applications. We can test out many scenarios. We can also integrate this into interactive, immersive design environments. Here is an experiment where we're using a VR tool to in real time sort of change some of these parameters and visually inspect the results and see the carbon reduction. Here's another version where as we're changing something like the allowable width or depth or strength, we can immediately see both visually how this looks in the space, what the optimized structure looks like in the space, but also what the carbon savings or difference in carbon would be because the surrogate model is so fast. We're also working on building these structures at scale. So we recently were able to build a prototype that uses these shaped concrete structures in Mexico with partners, where we 3D printed fired ceramic blocks to integrate with the concrete beams to create what's called a block and beam or Vigueta y Boveda system, combining kind of traditional techniques and digital fabrication to achieve a prototype for affordable housing that uses about half as much carbon as the traditional version of the system. And our students who worked on this are currently collaborating with partners in Mexico on commercializing this technology. We're also looking at other ways to make formwork for these efficient concrete structures with advanced technology. Here, we're using additive manufacturing to create circular, repurposable formwork out of minimally processed earth. So we're 3D printing earth. There's no cement added, so that the earth can be used 10 or 20 times in a row by being re-moistened and re-extruded. It takes only a few hours to make the formwork for this concrete system. It takes longer to make the rebar than it does to make the formwork in this case. So the complexity of what we can achieve is large. It also introduces new aesthetics and new kind of new tectonics of the architecture from the 3D printed earth. We also are using a lot of imaging techniques to try to calibrate whether what we've made matches the geometry we expect from our optimization technique. We're also using this to create kind of more complex 3D forms with similar earth and 3D printing techniques with more complex tool pathing to achieve very lightweight, highly efficient and inexpensive concrete systems. The last area of work I wanted to talk about relates to applying similar ideas to circular design and construction in the built environment. And by that, I mean making use of undervalued salvage, waste, or reusable elements as structural components in architectural structures. My first experience with this was working with these tree forks, which are waste products from from forestry, but also more generally from kind of many environments. This is an example right near my house where I live in Massachusetts, where they were clearing a ridge covered with invasive Norway maple trees to make room for a new construction project. Normally, when trees are taken down, if they're not actively part of a forestry project, they're chipped to become mulch, which is used for landscaping. This is severe downgrading because the mulch decays in a matter of years. So all the carbon that's stored in the fibers of the wood is released into the atmosphere. We asked instead our colleagues at the City of Somerville Urban Forestry Group if we could capture or reclaim some of these pieces of wood, in particular these tree forks that have very little utility in conventional forestry, but which are excellent structural components. Every tree fork in a tree is a natural cantilever, so it has a built-in moment connection achieved through a really intricate internal fiber structure within the wood that we could not make with any manufacturing technique available today. The complexity and ingenuity of the fiber topology is something that is far beyond our current additive manufacturing techniques. And yet normally these tree forks are treated as garbage that have absolutely no value. Our idea was to use these therefore as moment connections in a structure and to accept their variation and irregularity as assets that could be used to inform a design. We came up with this idea of a grid shell structure where all of the joints are rigid moment connections that are achieved by mapping the tree forks onto the design. And then we developed a technique in which we explored this design space of the overall form to decide on a shape that met our aesthetic goals, but also matched our inventory of tree forks as well as we could. A lot of this is centered around a very efficient matching algorithm that achieves optimal assignment between an inventory of found materials of parts and a target, which is our design. So a lot of this relies on finding an efficient and compact representation for both the inventory and the target. In this case, we represent the tree fork by this medial skeleton representation. We also work on a kind of correspondence or alignment using something called the iterative closest point method. We put all of this in a large cost matrix and use the Hungarian algorithm to find the optimal assignment between the inventory and the target. For most problems that we work on, this happens in real time, and so the design can be quite interactive and fast. We can also then automate all of the tool pathing for downstream fabrication tasks. In this case, we wanted to remove all the bark from the wood pieces because the bark otherwise can cause degradation. So we used this bandsaw connected with a robotic arm, and all of the instructions, even though each piece was different, the instructions for doing the tool pathing were automated. So it was pretty straightforward to produce this irregular kit of parts that could then be assembled, like a Lego kit, except with organic variation in a short period of time without any complex instrumentation or technology on site. The assembly is really guided by the joints themselves. So the irregularity of the original tree branches is really the part that locks the system together in the end, which results in a new system that reconciles these goals of design quality, efficiency, and availability. We've been continuing to work with tree forks because it's a really interesting problem and people keep sending me more tree forks. We did another version of this project where we wanted to remove the robotics element and instead investigate mixed reality systems to achieve the assembly. So here, we used a much more traditional joint inspired by traditional carpentry called the scarf joint. Used this kind of filler material to temporarily hold the parts together and then drilled and doweled the connections. This was achieved by undergraduates with no construction experience, aided by the mixed reality. It took a lot longer to do the assembly, but we didn't have any upfront robotic machining. So in the end, it was a similar time and very low tech in terms of what we needed to achieve this. We've generalized this idea that reuse in general can be thought of as this optimal assignment problem for many different types of inventories. And we've been experimenting with a wide range of irregular materials that can be assembled into new types of architecture using a very similar algorithmic pipeline. So from tree forks to concrete fragments or rubble to waste glazing units, all of them can follow a kind of similar process of sourcing, characterization into fixed length vectors, and then using this optimal assignment to match to a target. We've connected this idea into a toolkit that we're using in our own research and with students at MIT called the Digital Circularity Toolkit, which is a really modular, interactive, and fun framework for doing this type of matching work on a really wide range of problem types. Most recently, we've been exploring the same problem, but from a different perspective. So instead of doing this matching We are wondering whether we could use reinforcement learning to achieve a similar objective, but with the benefit of more generality and more flexibility in terms of the user definition. So here we similarly have an inventory and a target, but our target is much more fuzzy. It's just a gesture of a curve that the user inputs. We train a policy using a reinforcement learning framework to identify incrementally elements from the inventory that can be used to achieve the target. So I won't go into detail about how this works, but we were able to set up and train a policy that works pretty well so that for many different input curves, we can find, and for many different inventories, we can achieve a high quality match. We've also been experimenting with this kind of digital circularity in our teaching. So together with a colleague, architect Sheila Kennedy at MIT, we've been developing a pedagogical framework called Odds and Mods, looking at this idea in architecture. This last semester, we focused on brick, of which there is an enormous amount of waste. At every brick factory, 10 to 15% of the bricks that are produced are immediately thrown into a waste pile for various reasons related to visual defects, but not their structural performance. And many brick factories have these enormous waste piles that are visible from high up in the air in satellite imagery. These are our students investigating this waste pile, where we're working with techniques like 3D scanning to create digital twins of these inventories, and then connecting them with algorithmic workflows to identify not only possible ways to use the inventory, but really opportunities of what this irregular waste inventory gives us that we otherwise can't achieve with standard components. And so there's always this compromise between a sort of open blue sky design and working with an inventory. But in general, the students and we have found that it promotes a lot of new opportunities in design and connects to a lot of these technologies. So to conclude, I'm very concerned about the climate crisis and the role that architecture and AEC in general play on this. I think advances in technology related to geometry, data science, machine learning, robotics can empower better ways for us to blend between the systematic performance-driven design, free creative processes driven by humans, and affordable and efficient fabrication and assembly processes. Thank you very much.
Thank you very much, Caitlin. We're gonna open up now for questions. There might be some online.
Just for slides.
Okay, sounds good. Does anybody have any questions from the room? Yes, please.
I'm curious on Caitlin's thoughts on the constructability of the truss structure with the T's. It seemed like the students were really struggling to hold up the structure in its intermediate kind of state. I don't know if you thought about some kind of a way to hold everything up while it's being constructed.
Caitlin, were you able to hear the question?
No, I'm sorry. Can you repeat it?
I will repeat it, yes. And please let me know if I forget anything. It was a comment about the constructability, and it seemed that when the students were putting together the structure, they had, it seemed that it was a little bit on the heavier side. They have trouble making it stand. Am I saying it correctly, what you want to say? Yeah.
And if she's thought about a solution.
And if you thought about a solution to make it easier to build.
To hold up the pieces.
To hold up the pieces.
Are you talking about with the tree forks?
Are you?
Yes.
Yes.
Yeah, I mean, we definitely can account for that. I mean, in some of our work with assembly planning, we look at questions like that. Like we look at the weight or the mass of the individual pieces, the deflection of a partially completed structure under loading. So yeah, all of that can be accounted for. I think the question comes down to how much you know about how something will be built while you're designing it. In our current paradigm, at least in the United States, it's very hard because the typical contract structure separates the builder from the designer completely. So the means and methods of construction are completely separate from most designers. And so you can't account for how something will be built. In the methods that I'm working on, we advocate that that's really a problem, and we really should we really do need to understand or test different forms of fabrication directly into the construction processes. And yeah, we have a wide range of ways to do that.
Great, thank you. Other questions? I have another question in the meantime, Caitlin. I'm wondering, you mentioned also at the end the importance of the climate change and the issues with our industry, the AC, which stands for Architecture, Engineering and Construction, for people who are not familiar with the term. And I was wondering, what are your thoughts on how can people who research computer vision help with creating methods right now that can help with that for your domain and from your own perspective?
Yeah, I mean, I think there's a number of relevant applications of computer vision. Some of them relate to topics that are slightly outside of my field, related to operational performance of buildings. That's another huge topic. I think there are some talks in the workshop related to this. So how do we measure the amount of energy that a building uses during its operation? A big part of that is understanding details of a building that we might not know. And so using computer vision, for example, to detect properties of a building as you are already, could feed into things like building energy models in order for us to better characterize and understand the built environment. Those things could also be used in design in order to test retrofits or similarly, those techniques, as you may have seen, could also be used to identify building materials that could be salvaged and reused. So there's a lot of interest, I only showed this very briefly, but in digitizing geometric and material representations of unknown materials, of creating digital twins of unknown materials so that they could be considered in a circular economy.
Great, thank you. Any last questions from the audience? I'll wait the awkward 7 seconds.
I have a question about the new generative form finding models. Hi, I have a question about these generative form finding models and how they compare to traditional topology optimization algorithms in case of many different load cases, which is in fact always a problem in civil engineering. Do they perform better? Probably in case of hundreds of thousands different load cases.
I got the sense that this is a long question, but I couldn't hear any of it, so I'm sorry. Hopefully there's a summary.
Can you please come here because it was a long one and I cannot repeat it.
Right.
If you do this kindness.
Again, or?
Yes, please.
Yeah,
It's here.
it needs to be here. The question is about these new generative form finding algorithms models you showed and how they compare to traditional topology optimization models in presence of many different load cases. They probably in opposite directions act.
Yeah, that's a great question. My sense is that it's really impossible to get everything into a topology optimization problem formulation. Like even if you did many load cases, your material model is wrong, or I mean, this is kind of a philosophical thing. So I think in many cases, a larger design space based on some kind of generative model is going to be more interesting and more relevant to most design applications than some vision of every single design we ever built being the result of a topology optimization. I think it just doesn't feel realistic to me, and it feels like overly constraining to force everything into that formulation. So yeah, I think but I've never seen a very strong direct comparison, probably because it's quite hard to actually get all of those load cases and all the other things into a topology optimization.
Great, thank you so much, Caitlin. I hope the experience was smooth. The hybrid is always a little bit hard to work with. With that, again, let's give a round of applause for Caitlin for this exciting presentation. Great.
Now we'll go to our next and last speaker, Amber Xiang Li, who is a postdoc scholar at Cornell University, working with Professor Noam Snavely. Amber, do you want to, in the meantime, connect while I am sharing? Great. She did her PhD at the Multimedia Lab at the Chinese University of Hong Kong. And she works a lot in 3D computer vision and generative modeling, and a lot with also neural representations or neural fields, where she will present to us today about her exciting work. Amber, the floor is yours. Thank you.
And also share. You are on, but you share screen, yes. And your
This works well.
Yeah, it works.
Hi, everyone. Good afternoon. Yeah, thank you, Hiro, for your introduction. And my name is Wu Xiangli, and I was a good member. Yeah, so one of my line of research interests here. Okay. Yeah, so I might just keep going. Right, so the rendering quality of NeRF is high, producing continuous and sharp virals, and it's compact because the whole scene is embedded into several layers of weights and biases. So lots of previous works on NeRF have demonstrated remarkable results on objects or small-scale scenes. So it's tempting for us to also use it on built environments as well. And we spotted several unique characteristics of built environments that can be challenging compared to modeling objects or small-scale scenes. For example, built environments can be large, like cities or neighborhoods. They are also complex and compositional, populated by various of functioning components, and the configuration or layout of the scene are also structured and regularized. And there inevitably will be dynamics like moving objects and changing lightings. So eventually our goal, or we expect our method or model to render the scene with high fidelity and efficiency. And also we want to be able to manipulate the model as well. And on top of manipulation, it would also be desirable to support creative tasks like scene generation and stylization, etc. So as a start point, we made some attempts on using neural fields to model large-scale real-world city regions, and we resort to object photography as the source of multi-view observation. So directly throwing these kind of imagery to neural radiance fields do not work very well. With the purely MLP-based NeRF model, rendering results tends to be blurry, and training and inference speed are both slow. This is because that to train a NeRF, we need to densely sample points in space to get their density and color from the MLP, meaning that the MLP needs to remember the mapping between every single point in the space, which might be doable for small objects, but not very feasible for large and complex scenes. And a more ideal solution would be to learn an explicit feature grid that is physically aligned with the space, such that local features are optimized for only a small neighborhood. So we try to using learnable features organized in voxel grids to model the scene. But despite rendering results became sharper, showing more details, we can still spot floaters and noisy colors in this video. And the number of parameters also increased drastically compared to using NeRF. However, there might be a way to not using that many parameters. So we observed that the vast urban scenes are usually flat, and the variations along vertical direction are limited and relatively simple. And there's plenty of empty space between buildings or above the ground. So to save memory and storage, we factorize the 3D scene into a plane and a vector and adopt a multi-resolution feature plane to better align with different scene granularity. We propose a dual branch two-stage training strategy that combines the advantage of MFP-based NeRF and voxel-based representations. So in the first stage, we fastly optimize a cross density and appearance feature grade over the scene, and then use the estimated scene density to guide the resampling of NeRF, such that these samples can effectively concentrate around scene contents and skipping the empty regions. So with these more accurate samples, we proceed to the second stage of training, where we further optimize the grid feature and jointly train a NeRF model that takes positions and viewing directions as input, as well as the spatial features curated from the grid. And our method delivers sharper and cleaner rendering visuals whilst maintaining a faster rendering speed, which can support real-time streaming requirements. But still, despite our effort on saving the number of parameters, which are the tensor factorization, and using Fourier embedding rather than high-resolution grid feature for scene details, we still find that modeling a large-scale scene is memory-consuming and linearly grows with the scene size, which is not ideal. But in fact, when observing the real-world urban planning data, we can see that that these urban scenes are actually composed of recurring scene assets specified by some layout plan, right? And diving down into the streets, we can notice that it contains a large amount of repetitive objects arranged in structure layouts. And in practice of gaming and filming industry, artists tend to create digital scenes by creating and repeating different assets or assets groups. And this inspires us to think that maybe there's a way to abstract a large-scale scene into a more scalable, flexible, and also interpretable representation. And what we need is to identify repetitive or analog scene contents and having them sharing a common set of feature or parameters, and use a layout file to indicate the pose of scene contents. To do this, we need a floor plan that is clean, sharp, and also informative with object views. And recall that in our previous work, we factorized the 3D scene into a horizontal plane and a vertical feature axis. And the derived feature plane is actually a physically aligned neural floor plan of the entire scene that can be used like a real floor plan, but not as semantically meaningful. So to make it more interpretable and controllable, we jointly optimize a semantic field along with the density and appearance field, and merge them together into a RGB dino plane such that it contains category, function, and appearance information of objects. Subsequently, we can do object detection on the density feature plane, obtaining bounding boxes from the plane around the objects, and use these bounding boxes to crop out feature patches on the RGB dino plane, and to do object clustering and categorization. So in the end, each asset or object in the scene is associated with a category and its bounding box position, size, and orientation. And we can also continue to construct an asset library from the scene to store object features for future usage. For example, for the same repeating chair instances in the scene, we only need to store one feature patch as a template and simply deploy it into the desired position at usage. And this framework and scene compression approach can be very useful in real-world applications like interior design, urban planning, and simulation, which requires flexible, intuitive, and user-friendly editing of the scene. And here are some demos on real-world drone capture citywide data. So with our approach, we are able to model scenes spanning about 15 square kilometers and skyscrapers of more than 600 meters. And we can also flexibly change the layout of the city. For here, we select one, here's the target building, and we crop it out and duplicate several times. And we can also do some applications such like previewing a construction site with different building candidates. We are also able to do some creative tasks here, like twisting or spinning this building landmark. And and can also change the lighting and season of a city neighborhood. Furthermore, we can also bring the city into some animation world with the help of currently AIGC techniques like Animative and so on. So throughout these previous explorations and experiments, one of the insights we gained is that for large artificial scenes, explicit representations are more scalable and interactable than implicit representations. But implicit representations can be more adaptable, robust, and semantically informative. So following this instinct, we have been working on finding better 3D representations for built environments. And recently, the occurrence of 3D Gaussian splatting has revolutionized neural rendering. And compared to NeRF, it is faster to train, to render, and is more flexible, touchable, like point clouds, and also being more scalable and memory efficient whilst achieving SOTA rendering quality at the same time. It has multiple advantages that we desire for scene level modeling, especially for the built environments or large scale scenes. However, when experimenting with 3D Gaussians, we noticed several artifacts caused by redundant Gaussian primitives overfitting the training wheels. And this can be easily observed from the depth rendering. As you can see, the flickering in the depth map. And 3D.js also appeared to suffer in textureless regions like walls and floors in the indoor environments, and less observed regions, for example, caused by occlusion or model viewing directions, which can be very common in city images. And we deduce that this is because of the fact that optimization of 3D.js lacks restrictions on geometry or structure. It has the tendency to create redundant Gaussians to overfit every training view and every viewing direction, leading to noises and artifacts and novel views. So more ideally, we want to have some kind of mechanism that can adaptively be active or dynamically produce Gaussians according to the view direction and viewing distance. And meanwhile, we want to maintain a good scene structure to organize Gaussian primitives in a structural way, and further reduce the redundancy and the memory usage by compressing local primitives into latent features and decode at rendering time. So towards this end, two of our recent works have been trying to improve the distribution of Gaussian primitives. So in the first work, Scaffold.js, we initialize anchor points from the sparse SFM point cloud and use them to distribute local 3D Gaussians. And the anchors are associated with latent features that predicts opacity, color, and orientation of Gaussians on the fly based on viewing direction and distance in the viewing frustum. And in the following up work, we further proposed a dual branch system to improve both the rendering and reconstruction quality. So here we explore using Gaussian primitives, this Gaussian branch, to guide the learning of a sign distance field or neural surface, and use neural surface to further regularize and constrain the distribution of Gaussian primitives. Just a bit of results with Scaffold.js, we end up with much fewer primitives, saving memory and storage. And at the meantime, we can handle view-dependent effects better by preserving scene structure and geometry and being adaptive to viewing directions, where 3D.js creates these small auxiliary Gaussians to express view-dependent effects. And here are some examples on real-world scenes where we are better at modeling the less observed background regions and thin structures and textureless areas in this indoor scene, and also view-dependent effects like reflections in the mirror. There are some rendering demo of Scaffold.js. So our rendering has less blurry floaters, and the depth map is more stable and smooth. Here is an indoor scene rendering as well. So on the right is our rendering results. You can see it's more cleaner. It is cleaner and sharper, and the reflection in the mirror can be reconstructed very good. To just make it more intuitive, we plot out the training process of Scaffold.js, and the upper curve here is the growth of the total number of primitives during training, and the lower curve is PSNR. And we can see that 3D.js grows primitives fastly, whereas ours remains a steady and controlled rate. Whilst we can achieve higher PSNR and also converge much faster than 3D.js, because at this time we don't need to frequently prune misplaced or overcreated Gaussians. And as a bonus, we can cluster and visualize anchor point features in the scene. And it appears that they are well aligned with scene components and also conveys semantic meanings to some extent. For example, points on this ruler are clustered together, and we can also identify like tables and bookshelf and handrails very easily. So the effectiveness of learning structure-aware 3D Gaussian primitives further inspires us to incorporate neural surface into optimization, which is a stronger indicator of scene surface and a concrete representation for versatile applications. And here, results show that we can achieve better reconstruction results on complex indoor scenes where previous approaches fail. Yeah, so basically this is today I want to share. And just a little bit advertisement is that our Scaffold.js has been accepted to the conference as highlight, and our poster will be on Friday. So if you see this sticker around, you should be able to find one of our authors nearby. So if you're interested, welcome to talk to us. Thank you. Do we have any questions?
In one of your works, you mentioned RGB Dino features.
Yes.
Could you explain how they were generated?
So it's still reconstruction. We reconstructed the so basically it's still NeRF. We reconstruct scene appearance as well as a set of inferred semantic feature map. So we run Dino on training images and use NeRF to reconstruct these images. And eventually we can get a semantic field called a Dino field. And we merge it with the RGB field. So together they can both provide appearance information and functional or category information.
Any other questions? All right, if there's no other question, is there any question on Zoom? No. Okay, let's thank the speaker again, please. Then next up, we will have our panel discussion. And so Dr. Mike Holton will
That's the part if the panelist goes on too long, the mic's just automatically cut out, so.
I
think that's a good strategy.
We also have Caitlin online. Caitlin, can you hear us? Are you able to participate?
Yeah.
Okay, great. We'll see how we do that. I will pop you up. Sorry. We're still setting up. Okay. Here we go. Caitlin is online.
There should be a couple pens along there. Do you mind passing the pen along? And did you get the memo? So first.
Caitlin, hopefully there's not gonna be too much double audio when you speak. Because I have a mic right on top of the speaker for people to hear you in the room. Can you speak and say that you're okay with the sound from your side?
Pass them up when you guys have it.
Sorry, you want me to speak?
Just to as a test, is it
Oh,
okay?
okay,
Do you have a lot of return from the audio here? No, you're good. Okay, the audio is good.
Can we get that extra notepad? Are you down there? Piece of paper? Oh, not there. It's down there. Okay, we're good.
Okay, we're good. Okay. How about we
Okay.
introduce?
Okay. All right. Well, thank you all for sticking through. We're almost to the end of the workshop, but we got our most exciting part of the workshop. We've got a lineup of superheroes here in the both AAC and computer vision. We're here to have a lot of fun in this panel session, but also a lot of good, serious discussion. Those are the two best combination of putting together. So before we get too far into the panel discussion, just want to kind of go around and give each of the panelists a chance to kind of formally introduce themselves. I know some of them introduced themselves throughout the day as they gave their talks, but people have changed and kind of come and gone throughout the workshop days. So just we're on the same page. So why don't we start with you since you just spoke to us?
Yeah, my name is Yunbo Xiaoli, and I'm postdoc at Conantec, and I work with Professor Noah Slavely. My research interest is in 3D modeling of built environments or large-scale scenes, including cities and rooms and buildings. That's it.
All right, thank you.
And this is Afshan. I got my PhD back in 2016 and been with Apple for 7 years. And we started the 3D scene understanding and perception team at Apple, especially when the LiDAR sensor was something that we know we want to put in our products. And we've been very interested in seeing how much we can push this and make these accessible at a scale that wasn't possible before.
Awesome, thank you.
Have to get rid of my jingle bells. So my name is Derek Lichty. I'm a professor of geomatics engineering at the University of Calgary, and my research focuses on photogrammetric and LiDAR methods for imaging metrology. So for close range precision measurement of the built environment, like industrial settings, but also biomedical applications.
Thomas Chernowski. I got my PhD back in 2020 from the University of Texas at Austin. I was an assistant professor at Arizona State University for 3 years, where I ran the Edifice Lab. We were focused on creating immersive digital learning experiences for the builders and stewards of infrastructure. And now I head up the machine learning team at Integrated Projects, where we're automating the scan-to-BIM process.
All right, thank you, panelists. And I realized oh yes, yeah, Caitlin.
Hi, everyone. I'm Caitlin Mueller from MIT in architecture and civil and environmental engineering.
All right, thank you. And I realized I haven't introduced myself because I know myself pretty well, but I'm Mike Olson, a professor at Oregon State University. They're all making me feel really old. I've been there for 15 years now. It's hard to believe. I feel like I just got there and still in my 20s or something, I think, right? But I do a lot of research related to LiDAR technology and civil infrastructure applications. My natural habitat is being out on a landslide, doing scanning on a landslide, tracking movements, looking at coastal erosion and all those sorts of fun problems. All right, so this session it's meant to be interactive. So to get us started, I asked the panelists kind of at the start here to basically come up with their ideas, since they're all superheroes. How can computer vision save the built environments and fix our problems? And if I can get you guys to pass up the remaining answers there. You want?
Wrote 3 words for you.
All right.
Yeah.
Well, oh no, you just gave it away though. All right, so the audience. Okay, yeah, and Caitlin, if you want to write up an answer to that on the chat as well. So how can computer vision save the built environment and fix all of our problems? So we'll give Caitlin just a minute to do that. And I
And
think
is my answer secret or public?
it's secret. We're going to make them guess who said what.
Okay, so I'll just write it to you. Okay.
Although it's going to be a little hard because I'm probably going to be looking over there and reading. All right, give us just a moment. Got some pretty good answers here. Okay, I get another one there too, so we'll mix that in. All right, Caitlin, have you had a chance to put you on the spot? Sorry.
No, it's a secret message, so only from that computer.
Only from this computer, but I think if I show it here, you guys will all see it, right? I said the problem is I don't think I can see the Zoom over here, so we're gonna move you over here for a minute, Caitlin.
Hybrid never works.
Well, that worked. It doesn't have.
Okay. All right, the moment you are all waiting for. So the first one we're gonna do is says computer vision can make things faster, better, more efficient. So do we want to read them all first and then decide, or do you guys want to decide as we go? What would you prefer?
Just go over all of them.
All of them first. All right. Answer number one, computer vision can make things faster, better, more efficient. Number two, just to make it a little more challenging, there's a bit of overlap. Improve efficiency, reduce waste, faster, better, and more efficient. The next one is by providing high quality models to permit informed decision making. The next one is computer vision is the path to algorithmic links between the physical and digital worlds, which would be imperative for us to understand our present and imagine better futures. The next one is by filtering and hiding most of the data collected in the built environment so as to avoid overwhelming professionals in the built environment. And then the last one we have is latent features are all you need. Well, sounds like a Beatles song there. All right, so those are our questions. So we got to, it's the audience. Who said what? So first one, improve efficiency, reduce waste, faster, better, and more efficiently. Who would have said that out of our panelists based off listening to their talks today? All right, got a couple votes for the remote person.
Thinks it's option. Cool, who thinks it's Derek? Sorry,
Thomas.
Okay.
Yeah.
So thinks it's okay, so it seems more so that people think that it's Caitlin.
I think it's Caitlin. Well, I can tell it's not Caitlin. This person also gave a hint with it, but I almost refrained from doing the politician 1, 2, 3 at the start there. I almost gave it away myself.
The both of them, like, I gave you 2 papers.
Yeah, and I realized I put them together as I was shuffling. I did a bad job. So one was computer vision can make things faster, better, more efficient. The other is improve efficiency, reduce waste, faster, better, and more efficiently. All right, the next one is by providing high quality models to permit informed decision making. Votes for Caitlin. We're still going to throw you in there because he had to be a few pieces of paper. All right. All right. Is Thomas going to own up to it, or is Derek? This looks like Derek's handwriting to me.
That's not handwriting, that's scribble. That's mine.
Generous. I'm trying to be generous here. All right. That was Derek. Thomas was the only one who put his name on it, by the way. All right. Latent features are all you need. It was Amber, right? Amber, I got your name right. Yeah. All right, and then last one, or no, sorry, we got two more. So next one was computer vision is the path to algorithmic links between the physical and digital worlds, which will be imperative for us to understand the present and imagine better futures. So, Caitlin? All right, there, I think everybody could see I was reading the screen there, so I think I gave that away, but we'll get you back on the screen there. So Caitlin's back with us. All right, and the last one, by filtering and hiding most of the data collected in the built environment so as to avoid overwhelming professionals in the built environment. So that was actually random panelist number 52 out there now. That was Thomas there. All right, a lot of great words of wisdom there from our superheroes who are here to save the world and solve all the problems that face us in the built environment. So now's your chance as an audience to ask questions. So as soon as you're ready with a question, raise your hand. I've got a whole ton of questions to keep you here all excited until we're ready. Your questions will be much more exciting and interesting than these ones. But do you guys kind of think through your questions? I'll kind of ask our panelists the next question. So one kind of challenge that I see, particularly in the integration between the AEC community and the computer vision community, is that on the research side of things need to be flashy. They need to be exciting. They need to be the newest, the state of the art, right? Well, you have that kind of 80-20 rule, right? You can get to that 80%, but then after that, it's a lot of tedious work that shows very minimal improvement after that, right? But in order to get to the levels that are needed for the AEC community, you've got to kind of reach that higher level and you've got to kind of continue through those. And so you had mentioned in your presentation about with Apple, right? You're releasing everything to the market, getting it out to millions of users. Everything's got to be really worked out. So the flashiness, kind of was the first steps, but then after that, you kind of have to work through some of those issues in the transition. So what advice do you have in terms of more effective tech transfer of kind of helping get through that part of the process so that the researchers can still be involved with their innovative ideas and still be kind of excited in that stage that maybe sometimes feels like a bit more of the grunt work part of the process? Somebody's got to answer it because you don't want me blowing hot air all day long here. So
I mean, I can give some of my thoughts about this. I agree, this is a really hard problem, and some of the things that are really important to deploy these technologies are not interesting research questions, especially not in computer science. I think they could be interesting research questions in AEC academia, though. And one of the ideas I have only minimally tested so far would be to get AEC industry to participate in some of this work by providing data. We have a huge problem where we have very little data, poorly structured data, et cetera, which is really important both to prove out these methods and to actually make them work at any kind of scale beyond toy problems. And if industry, I have this hypothesis that if industry were more invested because they were provided data, they would be more active partners in the tech transfer process as well. So that's a direction I'm interested to explore. Personally, I'm interested in using this design competition model to try to engage industry with data and see where that can go.
yeah, that's a great idea. If it's using their data, it's more likely to produce results that they're interested in, they're vested in it, they're excited for it.
Yeah,
Great.
I'd agree with that definitely. And the collaboration is really important to make sure you're solving a problem that's of interest, not just of academic interest, but also getting students, so the trainees who are eventually going to be out in the market using it and leading it, developing their own, getting them involved very intimately in that process, not just the research, but also the tech transfer process, so they understand that earlier than I did when I had to go through a startup company and tried to learn by the seat of my pants. Definitely.
Yeah, great advice there. Any other panelists have any inspiring thoughts before we go to the next question?
Could you just maybe repeat the question in summary? Were you asking how do we get people to be excited about doing grunt work?
That was the short version of the question. So the question is, I think it's easy in research to get excited the next shiny thing, right? But from going from that shiny thing to where it actually can be used in practice
Oh,
by
yeah, I
people
got a good
is
answer.
a lot of grunt work.
It's,
All right.
It's profit sharing. If the company is willing to pay the people doing the grunt work for their effort, they'll be excited to do it.
So continue with the grunt work. Still can't get around it. All right. Any other thoughts on that before we jump to the next? All right. And feel free to raise your hands when you're ready with a question. Yes, I got one back there.
So, do you think like it's a solved problem, or it does not matter, or it matters less about how the person takes capture? It's also about different devices that we have, like variety of devices with variety of reliability. And what are the problems that are still left in capture guidance?
Was it directed to probably your talk?
I
You think?
think, yeah, so I think capture guidance becomes important when you want to go to, I would say, a large group of people. Like if your work is very specific, you're interested in capturing very specific type of data, and you can train people to do that, then I think that becomes less of a problem, because you want to just go and capture 10 different factories and you can train someone how to do it. I think it becomes a problem when you want to put something out there where lots of people are going to be using it, and it's really hard to like train people, and no one is going to read instruction. That people just want to launch something and just start scanning and assume that things are going to happen. That is where things becomes pretty difficult. The things that at least we have learned is that people, that first 5 or 10 seconds of any capture experience is going to be extremely important in keeping the people engaged and making them kind of understand what they are doing. So coming up with intuitive way to like guide them into what they need to do, or like it's that first 10 seconds is going to be extreme. I think we had also some issues when we wanted to collect data itself, because when we wanted to collect data, you would send people to different countries and you hire people to capture data, and we didn't have room plan at that time to tell them, oh, run this UI is going to help you. There was nothing, so we had to like make sure that we had good description or good tooling for them to review their data afterward and make sure that it's good and healthy to upload. Because if you spend thousands of dollars in getting this space and you have one shot in collecting data, and if that data is faulty, then all the money is gone to waste. So I think it's depending on the audience and the scale that can be pretty different. Yeah.
Yeah, very thoughtful answer. Any other panelists want to weigh in on that or share any thoughts?
I can weigh in.
Yeah.
So we at Integrated Projects at least require guidance in the capture process because of resource constraints. So we have very tight turnaround times for laser scanning a building. Often a customer will approach us and we're out in the field within a day or two capturing that building. And we usually only have a single day to capture that building. And so there isn't a whole lot of time to plan. We don't want to capture more data than we need. So oftentimes we're using a mixture of laser scanners, mobile scanners, tripod-based scanners for the areas where we need higher accuracy. And all of this needs to be done very quickly. And the people that we're sending to site oftentimes aren't career reality capture professionals. These are sometimes people that only just entered the industry this year. And so any kind of guidance that we can provide is hugely valuable.
Mike.
Yeah. Yep.
I have actually a good question for you. So what sort of, so there's people, because it's interesting what you're talking about, the people that you send out don't necessarily have the knowledge of the training. They're new to the discipline. So what sort of training do you think, what do you think is necessary? What do they need? What are they lacking?
What are they lacking? Pretty much everything except for the laser scanner, because that's all they really have. Maybe they've gotten some guidance from and training from the vendor that sold them the laser scanner. And then, you know, some of them have watched a few YouTube videos. Maybe they've done a few projects on their own. They found their own customers and they reach out to us and they ask to join our scanning professional network. We do some vetting, and of course, we would love the most talented people. But when you're operating on a global scale, sometimes you just don't get to pick. If that's the only vendor that we know in that particular region of Mexico or wherever we're scanning, then, you know, then that's our only option. And for some of our higher profile clients, for the projects that require really high quality data, we'll fly someone to the location. But oftentimes the project isn't that demanding, and whatever that person that just entered the industry is able to collect, that's sometimes sufficient.
Okay. Well, the reason I ask is that, like, Mike, you know, the discipline that I come
Oh,
from.
yeah.
And I have contacts in industry in Alberta and Canada, and they will show me data sets that have been collected by people who don't necessarily have training, the proper training, the proper background. You know, it's a mess there.
Yeah.
So the technology is there, it's democratized to a large extent. Anyone can use it, but they're lacking, you know, the skills that we hold here in geomatics engineering about orientation and errors and registration and stuff like that. And I'm just wondering, like, sending a trainee to do a 4-year engineering program in this isn't necessarily viable. But what I'm curious about, what sort of information can get out there that is going to meet the needs of those sort of people.
So one thing that I'll say is I'm involved with a organization called Reality Capture Network. You may have heard of them. They just launched an organization that is designed to come up with content for certification. So we've just started to assemble committees. The committees are going to deliberate and spend a year developing educational content. And at the end of the year, we'll be bringing it together into a series of modules. Initially, it probably won't be sufficient for certification, but that's the end objective, is to have kind of the minimum viable education to get someone performing at, you know, some level, acceptable level.
Right, because I imagine that's important for the industry as well.
100%, yeah.
Yeah, that's the committee, right? Or you're on the committee?
So I'm on their advisory board.
All right, yeah.
But if anyone is interested, reach out to me. We're always looking for expertise.
Yeah, I was gonna put in a plug for the committee. That's the name of that
It's the
committee.
Reality Capture Network committees.
Yeah.
That's the organization.
Yeah, no, I think it's so true what you mentioned here is that importance of survey control. I remember early on, I made a mistake in my LiDAR class. I realized I wasn't emphasizing survey control enough and the importance of that, because no matter how accurate and nice things look at the beginning, people use those data more and more beyond the initial intended use. And one student raised their hand after I gave a lecture on LiDAR, and they're like, wow, does that mean we don't have to be like the people out in the you know, roads taking measurements with the scopes and everything? Because we got all these devices, we can push the buttons. I'm like, oh no, that work becomes even more critical because all that data hinges on the accuracy of those. So thank you for your questions and comments. Great discussion there. All right, we'll go here in the front and then we'll go to the back there. Yeah.
Yeah, thank you so much for all of you. It's a great talk. So I have 2 questions, if that's okay.
All right, we'll let it slide. We're still early in the session, so we can pull it off.
First question that I have, by the way, I'm Ryan Alimo. I founded a startup doing scan to BIM funded by NSF. So we have done lots of scan to BIMs with iPhone and with LiDAR scanners. And what we observed so far was the output is the problem. So Revit, that is owned by AutoCAD, Autodesk, doesn't allow you to do a lot of automation, right? So that's why you need, in the end, human in the loop to fix lots of different things. So what's your takeaway right now from the panelists, that how we can resolve that issue? Because they're close, you know, they don't want you to do maybe the automation, and now you are going 90% of the, you know, work, but you cannot give that exact format to the end customer. And that's why it makes it slow. So maybe with RoomPlan, you get it, but it's USDZ. It's not exactly what they want.
Yeah.
It's not RBT. So what's your takeaway and recommendation in this way?
Great question.
That of my league.
So there's no easy answer here. Autodesk is loved and hated by the industry for the reasons that you've mentioned. We currently are exploring kind of open source formats. They also have their problems. I would say our strategy right now is to just hire Revit wizards that can kind of dance around the API, and we're making do at least for now, but we're hoping that the industry starts to slowly move away from Autodesk. So yeah, anyone that wants to move away from Autodesk, please do so.
My second question is more regarding Amber and maybe Abshin. So we see the emerge of, Gaussian sliding and different things right there. The problem with their phone captures are they're blurry, right? Lots of images that you take during a scan with room plan or with the other mode, it's resized for better memory efficiency. At the same time, it's blurry. How do you address this? What's your recommendation to overcome this obstacle? And the same problem is for Francis that he had the earlier talk. So he cannot do the open mass 3D, right? When the images are blurry. So, and most of the clips are trained with very, polished images, internet images. So what should we do when you have imperfect images with different angles and different, blurriness?
So we can kind of roll back a bit. So if you have blurry or motion in the image, then pose will be a problem. You might not get accurate pose. So that's one way we need to solve it. Like we can use some more advanced tracking techniques like tracking key points and use them as the anchor of the scene to solve more accurate pose. And there are also some work I think is handling like deblurring using Gaussian splatting. And that can handle blur image, kind of do deblur, right? And another way is to actually learn a dynamic Gaussian space field. Like you allow your Gaussian to drift away a bit to capture the actual dynamics or blur in your scene. So in that way, you can recreate a 4D dynamic field and you can freeze the time, then you get a static scene or allow the time to flow as you want. Yeah, you can actually expand the problem to make it more diverse instead of trying to actually recreate a absolute static scene from your blur capture.
Okay,
And
that's
if
been,
you
yeah.
add something to this, you can to try to prevent the problem from happening to begin with, right? I think that maybe goes back to the capture UI and scan UI and having the proper guidance and feedback to the user so they don't end up wanting to get a scan of the room in 5 seconds and just move so fast, because regardless, it's going to be a problem, and whatever you do is just band-aiding the wound, and I don't think you can fully address that. So I would say probably trying to resolve that at the capture is probably the first hope, maybe either through training or better scan UI. Second, pre-processing some recommendation that Amber said is pretty useful. And either try to deblur or do frame selection, pick the frames that are not blurry. Yeah, I think that would be like my sensitive problem that you have to address in pretty much any pipeline that you build. I don't think it's specific to like room plan or any reconstruction pipeline. Pretty much everywhere.
The possibility might, I'm not sure if you're a fan of foundation model or large model. I mean, you can use a large amount of data to gain scene prior that can essentially have the ability to blur the scene, right? You kind of want to reconstruct it to a noisy state, but before that, you might arrive at a static state. So there is some prior work like big prior or some other things that explain this aspect as well. And you can also make the synthetic some blurry data and use a deep blur result as a reconstruction goal and train the model to try to reconstruct a clean version from the blurry data as well. So there's multiple ways to solve it.
Yeah, thank you. All right, let's go to the back. Wait patiently. Thank you.
This is a question on actually producing 3D constructions from the scan. So, for the better part since I've been in computer vision, we focus on explicit representation of everything along the way. Your estimated planes, doing Landsat, where you're trying to estimate your fusion point clouds or mesh point clouds. There's this kind of end-to-end trend with like Duster, Master, those types of just directly predict whatever the result is. And this kind of gets back to Francis Engelman's talk this morning, where you know, we had this mesh representation with flaws in it. To what extent do you feel like if your goal is something beyond, you know, so WinPlan is an example, you're not a mesh, it's a low poly representation of a room with some boxes or some CAD. You just directly regress. Like, you see that being a trend or a direction, I guess, to be less verbose, is the explicit representation of the scene becoming passe, like a research trend direction, or, you know, group yet? That a clear question? That was too complicated.
Yeah, let me see if I can summarize it for Caitlin and those on Zoom, because I don't think they can necessarily probably hear it back there. But kind of a lot is in the trend in 3D modeling. We've traditionally gone with methods like RANSAC to fit geometric primitives, reduce things down to shapes. But there's also kind of a trend towards working with mesh-shaped objects and basically creating surface mesh around all the objects, which has both its benefits in terms of flexibility, but also its flaws in how it represents the objects, increased memory storage and computation. And so I think your question was, is which direction is the trend going, and, you know, how are we going to be representing these different objects maybe into the future? So, okay.
I can give my opinion to that. I don't know if you're asking me, but
Well, I think I got the question wrong, but I'll let you answer it, and then we'll let you rephrase the question.
well, okay. Well, I mean, my take is there's no one perfect representation. We want to do a lot of different things with models that represent buildings and similar things, and there are always going to be different representations that suit different tasks. So like doing simulation versus doing rendering versus doing design versus doing construction. I'm personally constantly converting between representations, and I don't believe finding the one perfect solution would be beneficial. I mean, I think instead the trend towards these differentiable pipelines or differentiable conversions between representations is really promising. Like the more we can make it lightweight and easy to go from one representation to another, the more we can start to compose different forms of evaluation into our design processes, the more we can learn from different types of information. So I would advocate for not trying to find a single representation for all purposes.
Thank you, Caitlin. Did you want to add on to that? Since I muddled your question a bit, so I'll let you.
So oftentimes you have group formers, as an example shown, where you're trying to get a floor plan. Now, oftentimes you got a floor plan, you're reconstructing a 3D model first, and then you're taking something from that 3D model in order to try to extract like this next layer of insights, as opposed to directly saying, you know, can we just get this floor plan as a direct output? So is that explicit modeling that intermediate representation of a 3D model versus whatever format fits, whether it's some sort of BIM model or some sort of layout? I guess is there a foundation model trend in that direction that we should be paying attention to, or is the explicit intermediate representation still as valuable?
Okay. Yeah. Thank you. Thank you for stating that. Panelists might want to weigh in.
I have some thoughts on that. Yeah. Especially because I think at least we are very interested in looking to see whether we can skip some steps by using, like, let's say, models that have a world knowledge or can do more things. I mean, before, if you look at a lot of things, when we wanted to do a lot of vision tasks, we would build this bottom-up pipelines to say, okay, let's do reconstruction, let's do plane estimation, let's do semantic, associate planes to semantics, and now let's put the plane together to figure out what object they are. And now you want to use that to estimate whether this chair is going to fit in the space. Can we actually feed the RGBD to a multimodal large language model and ask the question directly, can I fit this object here? So I definitely see a trend in like people exploring this, you know, skipping a few steps and directly trying to like solve the problems in a one shot through or zero shot through this large models, it's definitely something that like we are also exploring a lot. But I don't think that's fully going to replace the explicit representation. There's going to be still use cases that you want that explicit representation, but really depending on the final use case, whether you want to do some reasoning on top of that, whether you want just that explicit representation shared with, I don't know, someone to just get ideas about the space. Based on that use case, I can see both worlds are going to exist. But I do expect that foundation models are going to be useful, especially when you want that higher level of reasoning on top of those representations. You might not need that intermediate steps anymore.
Amber.
Actually, I think there's some attention on like tuning large language model or large vision language model to solve spatial reasoning. So there's one called spatial VLM. I'm not sure if you've heard this from Google, and it fine-tunes a llama model on like 3D point cloud data and use it to do spatial reasoning, like measuring or trying to tell the metric height or distance between two objects, whether one robot will fit into the gap of some space. So there's some like attention on that.
It works very poorly.
Oh, really?
Yeah, I think the results are not that great. I mean, and the metrics that you define, the error that you define is like very large. So I think definitely that's very early on. You know, the data sets are not quite there. I mean, but I think it's a very great example of people trying to do that and trying to establish a benchmark to just directly solve this problem through a foundation model. But if you want to really compare it with getting a measurement through, let's say, an expert model that is designed using depth, it's still a wide gap between what spatial VLM from DeepMind, Google, yeah, versus an expert model can do. I think it's still pretty large, but whether it's going to stay large, I don't think so.
Thank you.
Great question. Other questions? All right, looks like I got another one.
I
Right.
have a question from the speaker online. So
Okay, Caitlin, this one's for you. Can you hear him okay? Do you want to come up and ask it from the podium, maybe?
Yep.
Just that way, I think that'll be easier for her to get it.
So what remote sensing data set did you use? You showed some data set. Was it like a SAR data, or was it just like a Landsat data set, RGB? So what did you use for your research that you showed for remote sensing?
I'm not sure. Are you talking about like the building massings or?
Yeah, yes, the satellite data result you showed.
Yeah, it's
Not-
actually, she's hearing through the laptop.
I'm not totally sure which, the data sets that I've worked with are either synthetic, meaning we generate them ourselves in CAD and then do point sampling on them. Or in some cases we use various forms of scanning, and we're kind of agnostic to which type because it's not my area of expertise. So we've tried many different, you know, commercially and publicly available tools to do that. But I'm not sure if that's your question. Am I answering the right?
No.
I can ask it offline.
Okay, yeah, maybe a follow-up
Okay,
email.
okay. Sorry about
Probably
that, yeah.
a little easier. Yeah, no worries. All right, yes.
Kind of gravitate away from Autodesk as the industry for RCN. Where do you want everybody to go?
So
Anybody from
I-
Autodesk in the room first?
Yeah, explain yourself wherever you are.
Sorry, I got some good friends that work there.
So I don't really care where we go, but wherever we do end up should be in a playground that is a little more agile. Because doing anything in the Autodesk ecosystem is just so slow. Because Autodesk as an organization is so unresponsive to the people that live and work in their world. And so that's where I would want to go. Whoever is willing to create it. I know there's an initiative by an organization called the Open Company They're behind things like Blender BIM, which is an IFC-based tool. That's, it sounds great, but, without the resources of someone like an Autodesk driving, participation, it's hard to kind of keep people fed for their development work. Yeah, I don't know is, I guess, the short answer.
Yeah, at some point the writing will be on the wall for him to say, hey, you can't keep doing these
I
old
think eventually a
workflows.
startup is going to disrupt
Yeah.
their world, and they're going to be sorry.
Yeah, so at some point they should rebrand and say, hey, here's the tool to clean up all the automated stuff. You do the automated stuff, we can clean it up real quick and we're good. But
moving there already?
yeah,
Yeah, there are a few players that are, causing Autodesk some stress. I know Revisto is a company that's kind of entering that design space. They've been more so focused on coordination of all these data sets. But yeah, I don't know.
we'll see. All right, there was a question back there and then we'll go with you.
Scalable methods of building models, right? And so using things like satellite imagery and spatial imagery to build 3D models of buildings. Are there downstream applications of models that with that much accuracy, or are there no other examples which are immediately possible from those models, or do we need those accurate models to be done for the building?
Yeah, so for Caitlin online, he's asking about kind of the scalability of models that are maybe generated from Google Street View that maybe aren't quite as accurate as the highest accuracy models. Are there downstream applications that could be supported by these? Did I more or less get that? So I don't know if any panelists or Caitlin wanted to tackle that one.
Well, what accuracy can you achieve with these models in the first place?
Yeah, that's a good question. Yeah, what
can? Sorry?
Sub 5 meters.
Sub 5 meters.
Meters is possible remote sensing right now.
0.5 meter.
Yeah.
Is what's big at, yeah. No, I mean, you can get 0.5 pixel, but a 3D model will still be, I guess, the most.
Yeah. Short answer, I'd say, yeah, there's always applications in visual, some forms of asset management. Sometimes just having an image of what's there is better than nothing at all. But the key is having the metadata to support it, to say that this is what it was collected with, this is how much you can trust it. Because I think that's one challenge is people oftentimes they go with the cheaper data set. And, we see this countless times in mobile laser scanning, right? They go with the lowest cost system and they collect their whole statewide network. And then it's like, well, we really wanted a few things at a little higher accuracy. Can we squeeze it out? And the answer is yes, there's a lot of room for innovation, but at a certain point, there's only so much you can squeeze out of it and have confidence that you actually got a good result, right? So I think it's important to beforehand get everybody in the same room to say, these are the applications, these are the accuracy requirements for the applications. So what's going to be our best value in this particular data collect?
Sub 5 meters.
I can add something to that. Oh, sorry.
Yeah.
Yeah.
For forestry, they're happy a lot of times with that.
And just knowing having an inventory of trees or something like
Yeah.
that, that's going to be fine, but anything more than that, no.
Yeah, because Caitlin had some thoughts there. So
Yeah, I just wanted to reinforce what you said about error estimation. There's a ton of applications in urban building energy modeling and more generally in kind of urban characterization. So like, what's the embodied carbon in the whole city? If we could estimate what all the buildings are made out of from Google Street View data, or et cetera, et cetera. But what's potentially dangerous is that pretty high impact decisions might be made using that information. And if that information is wrong, we don't have a good sense of our sensitivity to error in terms of the downstream decisions. And so I think being able to qualify or quantify the uncertainty in these representations is really important for those applications, because unfortunately, at some point, the downstream application users don't care or don't know how to assess error. And so they'll just take it as ground truth, and that's quite dangerous, I think.
Yeah, very dangerous.
The visual appeal of these data sets is too much and it clouds the issue.
Yeah, and that's what gets them burned. I mentioned earlier this morning, we're doing a lot of interviews of DOTs, and that's one thing that came up that really stalled their adoption of these technologies was they got in early on with the vendor that said they could do it all. Turns out they couldn't do it all, and the data did not meet their requirements. And so after that, they said, we're not touching this stuff. And it takes a decade to get them to start the conversation again. You almost have to cycle all the employees. So you have to be very careful in kind of how you present your results and in which context, you know, in a forum like this. Yeah, great. These are great research results, but if you oversell it at the wrong time, you know, that can be a problem.
I've heard the words laser scanning doesn't work or photogrammetry doesn't work.
Yeah.
Because of that sort of
Yeah.
experience. Yeah.
And well, it was the person running it. All right. You had a question. Thanks for waiting. Oh, yeah. I thought you had your hand up. Yeah. Oh, sorry.
We can take pictures, we can scan, but it's all surface level information. What type of like constraints are you guys seeing in your field? Because you don't see any of the internals.
Yeah.
But is it severely limiting what you guys can do with the application? Are you guys seeing other types of technologies that maybe look through the walls and give you information behind it, other than laser scanning or just general imagery?
Yeah.
What are you guys seeing to try and like, pass that barrier?
Yeah, great question. I'll repeat it real quick for Caitlin. So Caitlin, he's asking about, you know, we do a lot with basically superficial technologies, for lack of a better word, laser scanning, photogrammetry. We're seeing the surfaces of the walls, but we're not able to see behind the walls. And it's kind of curious what sort of technologies the panelists have had experience with in terms of being able to quote unquote open up and see through the walls and kind of see the guts and the piping and electric systems and everything underneath there.
So the method I have the most experience with is just temporally distributed data collection. And so during construction, you know, when they put up the rebar or the internals of the walls, you scan before the drywall goes up or before the concrete is poured. And then you repeat again once the drywall is up or the concrete is poured, and then you merge all of these temporally distributed point clouds or images together into something that is more complete. But there are also, you know, sensors, there's radar, you can use thermal. I've never really seen X-ray used, but I imagine that might be used as well.
I think it's possible to use mmWave and
Oh, sorry.
just signals probing and reflection through on the wall. And I know mmWave can penetrate wall pretty well. Yeah, but I don't have much experience on that. I just had a friend.
Yeah. Awesome. Caitlin, you had a...
Yeah, no, I love this question. This is super important. And I agree, you know, in some ways, these surface representations are like superficial. So my biggest experience is with thinking about what the structural system is behind a surface. Sometimes we've done that by building predictive models where we synthesize or otherwise acquire a bunch of training data. Maybe they're not even a learned model. It's more like some deterministic model where, given the outer boundary representation, we have reasonably good ways of estimating what the structure is on the interior. And like, so we do that quite a lot. For example, if we know the exterior massing of a building, can we estimate what the interior structural system is from the information we have? But that's not necessarily repeatable. I'm personally really interested in applying like non-destructive testing methods together with some of these techniques. So doing kind of frequency or vibration analysis, capturing that with high-speed video, inferring things about the materials or the interior structure from that. I think there's been some really interesting research in that, and I think that could have a lot of applications, at least in the mechanical, understanding the mechanical behavior and properties of systems.
Yeah,
there's
thank
also
you.
a lot of work on CT scanning for, you know, for like timber and forestry and wood. So just interior imaging seems very expensive, but there are probably some applications where that could be valuable, especially in the reused material space for finding defects, etc.
Yeah, Mike, I was going to mention that as well, with CT for forestry and some of the other experiences I've had with ultrasound, but it's very short range, trying to measure thicknesses of cast iron and steel. But I think GPR came up here somewhere, and I've got a colleague, a friend of mine in Hong Kong, and he's interested in the infrastructure below
Yeah.
And he does a lot of research in that, but it's a very complicated inverse problem because you need to know the distribution, the density of objects there. So trying to make that inference as to what's actually there based on these noisy measurements is.
Yeah, you kind of got to know what's there to do
That's
the
right.
inversions and stuff with it. Yeah.
Exactly, which is exactly the case with the CT scan. You have to have a distribution of what's in the head before you
Yeah.
can reconstruct it.
Yeah, I worked with a biomedical engineer. His name's Mauricio Serracini, and he was looking for a Da Vinci painting long before the Da Vinci Code and all that in Italy. And so he was hitting the buildings with all sorts of technologies. Some of the ones mentioned, but thermal, basically reflectometry was one of the best ones for getting it. He did do some X-ray, but the challenges is a lot of energy that's required to get it. And a lot of times what you need to do is scan small windows at a time. And so to, here he's looking behind a painting. So, I mean, it's painstaking hour after hour to just get the images and then stitch them all together to make sense of it. And so I think as Thomas mentioned earlier, really the more we can do this, just to have a standard on a construction site, having a fleet of scanners and just continuously scanning that site, collecting that data, collecting it before the pipes get, buried and everything. That's the best way to have that record of what was underneath and kind of see that progression so that you have that in the model. Because it's a whole lot harder to do it after the fact, but there are some promising technologies and eventually we may get there. But
I saw a startup at GeoWeek, and their catchline was crew sourcing. So as the pipe goes into the ground, get the workers to capture the imagery.
Yeah.
And then you can reconstruct the 3D model where the sewer is or the water main, whatever.
Yeah.
So exactly what you're describing before you bury it.
Yep. There's snaking technology and camera systems that can log like how you're moving it through and have accelerometers on it, but that's not a fun job to do, especially in sewage pipes and so on, right? So all right, other questions from folks? All right, Ryan.
So lots of work has been covered for interior scan to BIM. However, in practice, we see that the exterior is very important, like we talk about floor plan, but section and elevation are important too. And most of the work for the exterior are kind of like customized. So what's your vision to do the automated scan to BIM for exterior, like balconies? What do you consider from the 3 different types that you introduced? Or what's your idea about this automation for exterior?
Yeah. This was a question I was going to ask you, Ashvin, too, about extension of the Apple LiDAR to outdoor exterior scenes and some of the fun things there. So I'll point to you as somebody to respond to it because I was curious to hear your thoughts as well. Good question.
I think with outdoors comes some limitations. I think some of the sensors don't work as well in outdoors compared to indoors. I think that's one of the limitations. I think the LiDAR sensor, at least on our devices, still work outdoors, but there is a degradation of quality. And I think that is the main factor, but I also think that when you go to outdoors, the whole data collection regime is going to be different. And I think you're dealing with a lot more unconstrained environment than indoors. So the problem can become significantly harder. So I thought start with indoors to solve it, and then we'll move on, or it's gonna be an incremental stage. I think still this technology can be used for, like, let's say the technologies out there can be used for scanning your patio or balcony, and I think but even though they are not necessarily trained to do so, but there might be some accuracy degradation.
Yeah, I might add to it that the advantage of the exterior is you have